So these parallel things were happening. The professionals were developing and using speckle interferometry, but it was really amateurs that were developing the first robotic telescopes and robotic observatories. By the towards the end of the 1980s, this is the Fairborn Observatory up on Mount Hopkins. By then, we had 4.8 meter fully robotic telescopes, 7 telescopes in all, and it was quite a time series photometry factory, all automatic, and it was really, I think, the first remote access, so the astronomers could send in requests over modem. This is actually before the internet, and the observation would be made for them that night and then sent back. And also, so in the late 1980s, the European Space Agency launched Hipparcos. So this was and it was up for 2 or 3 years. They observed about 100,000 nearby stars, doing astrometry, getting positions and separations over about a 3-year period. It was a really great project. And then this was after 2000. This is Florent Losse. So he built a 16-inch telescope, and he decided he wanted to do speckle interferometry. You can see in the picture there. Can you see my cursor?
Yeah.
Okay, so here's a early CCD camera. So this was after they came out. Then the problem with CCD cameras is that it takes several seconds to read out a frame. You take like 10 seconds, the early cameras. So if you're trying to do hundreds of short frames, you spend 20 milliseconds with the exposure, and then you spend a minute reading it out. And so he would actually, to get an observation for just one star, would take him a couple hours to get the 100 exposures or so and read them out. So it was very inefficient, but it did really good. It got good speckle results. They were published right in there with the professional astronomers. And so I was very impressed with what he would do. I started seeing his results showing up. Who is this guy with with a 0.4 meter telescope? Tracked him down and got talking with him. I did meet him years later in person. So this was about, I think 2017 in Double Star Conference in south of Barcelona. And so the top picture, that's Bob Argyle on the left, that wrote the book on literally on the double star observations for small telescopes, and a somewhat older Florent Losse on the right. And down below, this was the gathering of astronomers, including some interesting astronomers from Russia. And at any rate, it was quite the meeting. And I got very enthused about it, so I decided I wanted to try to do it myself. And there was a camera called a Luminera, and here's the Luminera camera. This is an S-Big CCD camera. This is an S-Big CCD camera down below, and the Luminera camera, and behind just a flip mirror. And it was, as CCD cameras go, it was a somewhat faster readout. So that was kind of nice. You can see this was my 10-inch Meade robotic telescope, and you can see the SciTech control system there. And this was a reconstructed image there using autocorrelation. And so at any rate, but I wanted to see how the big boys did it. So I went to Kitt Peak, and that's Joe Johnson on the right, a star student of mine, and that's Brian Mason from the Naval Observatory. So this was his run on the 4 meter at Kitt Peak, and you can see here's the his speckle instrument, and so this switches different lenses in the front and filters, and then this is an intensified CCD camera. And by intensifying it, then you can read the CCD out much faster without getting lots of noise.
Hey,
The
Russ,
problem is yeah,
I think you're in the mode where you can see the incoming slide, and we can see that too. Can you somehow zoom in on the one that you're trying to show? Then your mouse agrees with what you're talking about. Right now, your mouse is on the opposite side of the screen.
He's in presenter mode.
You're in presenter mode or something.
oh, I see. It's not in the full screen mode. Uh, Is it still the wrong way?
Yeah, that didn't change it.
Okay, but are you getting the full slide and you just can't see my cursor?
And now your cursor's in the right window. So,
Yeah.
so that's the one you need to be on. Yeah, so now you're pointing to yourself.
Okay, well, let's skip the cursor. I don't really need the cursor. Is the slide showing up as a full screen
Yeah.
slide?
We can see the entire slide. It's not taking up the full screen because we do see a smaller version of the next slide in the upper right.
Oh, that's okay. So what we're doing is we're getting,
If you click on slideshow, maybe there's an option for that.
yeah, and they,
Yeah, I think, yeah, if you do that, there's probably a option for presenters mode or view as
let me
well.
do the normal.
Normal, there you go.
That's it.
All right, that should do it.
Okay, and now is it showing the full screen?
Oh, goodness. No, it's saying I didn't change it either. Oh, well.
I think if you hit if you go back to that previous screen, there's a picture that present screen you were just on. So down the bottom, looks like a monitor with a line through it. I think that will give you full screen.
Yeah, and I didn't see that. Doesn't show on mine.
On the image you were just on, it had a.
Yeah, it's something you can see, but for some reason or other, I can't see it.
Yeah, I would think normal we should do it.
You would think so.
Yeah.
Back to slideshow and
Yeah, try the slideshow in between record and animations. The next line up. It's right about in the middle.
Oh, yeah.
Click that and see if that okay, now go full screen.
Did that work?
Okay, none of us know what to do.
You just pull down to the menu.
Yeah, so I just say keep going. I mean, this is not a showstopper by any means.
Okay, I'll just keep going. Yeah. Well, we didn't quite get it sorted out. Okay. So anyway, after sitting in a run with Brian Mason, I thought, well, that's cool. So I went on another run. This was with Elliot Horch on the 3.5 meter wind telescope at Kitt Peak. It's a very modern telescope with, you can see the activators on the primary mirror there. And his camera, if you can look at the lower right there, it's a huge camera. It had two IXon $80,000, they must weigh 20 pounds each, monster camera. And while I was there, went over and looked at the 2.1 meter telescope and kind of that might be a cool telescope to operate on. And so then I started looking around there. Was there any smaller cameras? And I found that there was Andor made I would call it a Luca S electron multiplying camera. So it's like their big ones. It was front illuminated with a TI chip. And instead of $80,000, it only cost 14,000, and it was a whole lot smaller. And so to make a long story short, I was able to get a grant from the American Astronomical Society for $7,000. That was their max. And I talked Andor into selling this one at half price. It had been a kind of a little demo camera for them. So we then had an EM-CCD camera that we could use. And so the first thing we really did is to try it out. And so Dan, can you go up to the mic there and tell us about how you went down to Rowville the day before I got there and what you did?
Yeah, so I did. I went down a day earlier, and unfortunately, I didn't bring any Scotch tape. That was my big mistake. So I had gotten on eBay some Renishaw tape and reed heads, and so I had a hacksaw and a file and a drill motor and some drill bits and taps and a spring or two. And I wrapped the Renishaw tape around both axes with a spring. And unfortunately, what I found out is that the machining of this mount, it wasn't made to have encoders there. So it was not centered. The part that they turned wasn't centered on the axis. And so that's where I needed the Scotch tape. And fortunately, the neighbor has some Scotch tape. And so I also brought a dial indicator. And so I spent a lot of time dialing it in, and I finally actually got it to work. And so we made a telescope model, and we were able to easily find stars, because the other thing is, if you look at that Barlows, looks like there's 3 Barlows on there. Is that right, Russ?
Yeah, it was 2 or 3. It was definitely stacked Barlows with very high magnification, very small field of view.
Yes, it was extremely small. And so when we made the model, I think we had to like find stars, and it's kind of hard to find the stars. So I wrote a script that made a box and got a bigger and bigger box. And then as soon as you saw the star, you would click something, and then it would start tracking on that star. And that's how I think we made the model that way. Or maybe we had made the model with a camera and then put the camera on the Barlows. I can't remember actually. But then we had the first night we got I can't remember, Russ. I'm going to let you take over. We did an amazing amount of observations.
Yeah, so when we would move to a star, it wouldn't be there. And then Dan had written this little square spiral search thing, and it would go around, boom, boom, and as soon as we saw the star, we would stop it. But yeah, so here it is. Perfect question, Dan. So this was what we observed on that first night, and we actually had to quit. I don't know, it was like 1 o'clock or some sort. The solar batteries were running out, and Dave told us not to dare go below 24 volts. But if you look here on the column about halfway over the row column with the Greek symbol rho, these are the separations. And so this was on a 20-inch telescope, and some of these were half an arc second separation, and we'd been used on double stars, we were doing good to get 10 arc seconds and rarely 5 arc seconds. This was boom, way below the scene limit. And 2 of the stars we have found we've discovered 2 new triple stars. At any rate, it was papers and it was very exciting. And so, of course, one run out at Rowville deserved another run. So here was run number 2. And this is Eric Weiss in the upper left and one of my star students. And you recognize Bob Buckheim there. And one of the things we did was used a, it's kind of like the double slit experiment. The upper right there, you can see there's a bunch of equally spaced slits in the mass that we put over it. And I won't go into it, but there was a funny story. We used that for calibration and things weren't matching. It turned out we had the filters labeled wrong. We got the right filter with the center frequency, and then it all worked out. But at any rate, that encouraged us to, yeah, we can. So we decided we want to do ourselves a bigger telescope. So I actually put in for time for observing at Kitt Peak, and the reason some amateurs got our time at Kitt Peak was that we went in advance. So there's Tom Smith and tried out, made sure everything fit and so forth. We did that, and that really helped on the securing the time. And so then we had 2 runs at Kitt Peak. The first one was in the fall of 2013, and down at the bottom of the telescope there, you can see that little camera shining. It's kind of shining at the end of the telescope. This is the control is a old linear dials. It's a fun telescope to operate. This is Kent Clark, the editor for many years of the journal Double Star Observations. He was just tickled pink to come to the run. There's the camera at the bottom of the telescope again. And that's John Kenny and some of his students. And there we are in the upper right, the control room, sitting down in the kind of green shirt is Mark Trueblood. And behind him is a graduate student of mine. And real close up of the camera. And even on the 2.1 meter with its long focal length, we needed a Barlow, so it had a Barlow. And there we are in the control room. Lower right is students at Cuesta College, my students, and they wrote up some of the early papers with the results from Kitt Peak. And that deserved another run, so that following spring of 2014, ran again. You can see Wayne Green in the background, Dave Rowe, Reed Estrada and Chris Estrada up front there, and the John Kenny and others. At any rate, that was the second run. And while we were at Kitt Peak, the solar telescope had never been used for speckle interferometry, and we thought we could rig it up to get speckle results, and we did it. That up in the upper right there, that's Pat Boyce and Richard Harshaw. And lower left is a setup for the camera, and there you can see some of the speckle results that we got on. As far as we know, that's the first and last time with speckle interferometry on the solar telescope at Kitt Peak. Lots of these things written up in this special issue of the JDSO that's online. And at any rate, it's volume 11, number 81S, if you want to look it up. Then we took the EM CCD camera. I spent winters in Hawaii, so we started observing at the half-meter telescope at Leeward Community College. It's right on the Pearl Harbor there. You can see the ships out there at Pearl Harbor. In the lower right, you can see there's the setup. It was a manual flip mirror between a that blue wide field camera and then through a Barlow to the EMCCD camera. And this we took up the camera up to, this is the 2-meter telescope on Haleakala. And if you look right in the middle of the picture, you can see the EMCCD camera pointing out. The guy in the lower left there, that's J.D. Armstrong, astronomer at the University of Hawaii Institute for Astronomy in Maui. At any rate, it was unfortunately cloudy for a whole week. Our chance for it, but we never got any images. We got on the telescope and then just got wiped out by weather. But we didn't give up. So this is 2014, I think. So this is a engineering test of the speckle camera on the 100-inch telescope on Mount Wilson. And the telescope, again, with a Barlow, the telescope wouldn't bring it in the field of view, so you would have to go up on the ladder and flip the mirror to an eyepiece, and the operator would fish around for the star. But we were able to get some results. And then I used the camera. This is the Fairborn Institute Robotic Observer. This was in California, and this is with students. Here's a couple astronomers from China, professional astronomers. Their Institute for Astronomy in Shanghai is bigger than the Harvard Smithsonian Center for us. It's the biggest collection of professional astronomers on the planet. Anyway, we hosted them for a few days. That was fun. And then we had started having some more. We had lots of meetings, but we had some particularly just on speckle interferometry. So this was back at the U.S. Naval Observatory a year, maybe, I think a year later. And here's Brian Mason on the left and Bill Hartkoff on the right. Here's the controls for the 27-inch refractor, the historic refractor at the Naval Observatory. They're still doing speckle interferometry. Bill's retired, but his office and spot has been taken over by Rachel Matson. And I visited them this past June. They're still going at it. And we had a very nice workshop, a 3-day workshop at Lowell Observatory, and went out. So I organized it with Gerard Van Bell, who's now, years later, he's now the science director at Lowell. He's number 2. And at any rate, we went out to the 4.3 meter Lowell Discovery Telescope, which is just up the road from us from here in Payson. This is in Happy Jack, Arizona, about halfway to Flagstaff. And we actually made some speckle observations one of the evenings of the workshop. That's Richard Harshaw down below there. There's our group standing in front of the 4.3 meter cell. And we're going up to October 11th. I'm a high school teacher and students and some of the VIPs from Payson. We're going up there for a visit and doing some speckle observations with Gerard Van Bell again. And then this is my observatory back in California. So I was interested in trying to automate speckle interferometry. So a really bright student at Cal Poly, super with software, Alex Tyke. He developed the software to automate observations with this EMCCD camera. And there you can see the EMCCD camera kind of the middle right, and down below it, there's the flip mirror there that you can go to a DSLR that we use as a real wide field camera. And this is my study, and our first automatic speckle observations. Very shortly after that, Alex got hired away, big time pay, off to Sweden, and at any rate, he was just too bright for us. And the software never got documented or anything, and kind of wasn't able to use it. But so that was the end of automation for a while. We did other things. This is a aperture mask at the Borne Institute in California. And there's a little motor that could turn the mask around, it rotate the mask, and it allows you to, has a diffraction pattern that gives a dark spot. If you get the mask rotated the right spot, you can then get very large delta magnitudes. And we explored some other things. So this is a meeting actually at Mount Wilson. And left to right there, that's John Kenny, Brian Mason, Niels Turner, myself, Dave Rowe, Alex Tyke, and Reed Estrada. And we were kind of discussing, where can we take some of this? And Dave is talking there, the mathematics behind speckle interferometry and things that you can do with it. And so one of the things we were interested in is getting a larger aperture telescope on the cheap. And so essentially, if you do several telescopes and you get the mirrors phased, then you can get the resolution of a larger telescope, the distance between the two mirrors. So a graduate student at Cal Poly developed the trick was getting the mirrors positioned, within a wavelength of light, better than a wavelength of light. And so we did 3 spherical mirrors. Those who remember Tong Lu came to the Altaz Initiative several times. He did 3 matched spherical mirrors. We put that in a rig, and then each of the mirrors needed 3 things to do the tip tilt, and so there needed 9 of them, and the graduate student built 9 of these. And what it is, it's a very high precision stepper motor with a very, very fine tooth that can just move it just a few microns at any rate. And we haven't done it yet, but I really want to do this. Is called a sparse aperture mask, and you can about double the resolution. You lose photons, but you definitely pick up resolution. So I'm going to put one on FIRO, but they use it on Keck. They use it on the 4 8-meter VLT telescopes down in Chile, and it's up on the kind of a poor man's version of on the James Webb Space Telescope. So you can see the patterns, not quite totally random, but it's close to it. And so kind of back to the Altaz telescope, away from speckle for a minute. So we started the Altaz initiative. We wanted to know what was it on the large mountaintop professional telescopes that we could bring down to our telescopes. So Dave Rowe and I made some visits, Tom Smith and I, to telescopes in the US. And then Dan Gray and I went over, spent some time in Hawaii and visited the telescopes up on Mauna Kea. So this is the Subaru telescope, which was direct drive. We were very impressed with the direct drive of this big monster telescope. And so the Altaz initiative, one of its great claims to fame is the development of direct drive. So there upper left is one of the Altaz initiative meetings. And Dan built the control system, and Dave Rowe wound the coils in his garage and put the thing together. So that's the first test motor on plywood. And then the lower left is students, my students, actually two teams. This is one of the teams at Cal Poly built this, the Cal Poly 18, as we've called it. And the upper right there, it was in Dan's shop. So how long did it take you to get it working? And it was, it was problems, right?
See, Richard Berry had a lot to do with that one.
Yeah, and Richard's there. Why don't you two tell us about the straightening up the Cal Poly 18?
Well, before Richard got a hold of it, we got it here in our shop. Well, it was a different shop, but same company. And it was basically impossible, in a state to make it work. But we used a lot of epoxy and we got it to work. And we had a test out here. I think you came down, didn't you? For some of the testing here?
Yeah.
Yes.
Yes.
Yeah, Richard came down here to this shop from at that point he lived in east of Salem. Where did you live? East of Salem?
Lions.
Yeah, Lions. And so we spent a few nights here and we got it working pretty well. And then we took it down to Richard's place and he did so much work and he's got it's still up, I believe, isn't it, Richard? Your website
I think so. I don't know. I haven't taken it down on purpose.
Yeah, I think it's still there. I think I looked at it within the last few months. And it's a great thing and it works, but it wasn't for Richard. So he basically, it's mine now and it's in my observatory and it's almost ready to work, but not quite. And I need some more time.
Well, one of the lessons of this, if you have students and that do senior projects or even master's degree students, the thing about students is once they leave, they're gone. And if you have a project that they have to do by some deadline in order to get their degree, they're going to get it done, whether it's done well or not. But Howard, what do you do on the Cal Poly 18? Because you contributed some stuff on it. Tong Lu contributed the primary mirror. I just did my normal thing of scrounging up from all sorts of people to donate to it.
Yeah, I made the mirror cell, which was a lot of fun. It's the first time I used magnets, spherical magnets in a mirror cell, which I've done ever since. And I worked on the secondary mirror holder, which was pretty unique. It was I think it was a 6-inch, it's the length of 6-inch diameter aluminum tubing, fairly thin wall with a elliptical with a cutout so the light cone could reach the Newtonian focus. It was pretty unique. I've never seen that done in another Newtonian telescope, but I worked on that a little bit. But mostly it was the mirror cell.
Yeah. Anyway, that was a great project, and the important thing is then it led directly to the plane wave instruments, their first professional research telescope, the CDK 700. And so and Dave spent a couple of years really. He's really good at managing engineering teams. And they just they FEA'd the whole thing. It was just a really well designed telescope. This was their first light when they were still in California, and by then the magnets and the coils are all professionally done and so forth. I mean, that was really nice telescope. And here's one of the CDK 700s. There's now over 100 of them worldwide. This one is at Great Basin Observatory in Nevada, and it's Dave worked out so we could switch ports on this. This has it has the two Naismith ports, and so we did speckle interferometry on one and then the wide field camera on the other, and Dave worked out the equations to translate the position from one to the other. It was a little bit tricky, but and then we eventually got app for NITA, a guy in Belgium, Nick Hardy and Leon in Germany wrote an app for NITA to automate a speckle interferometer. So finally got it successfully automated and made observations for over a year on the 1 meter there and a 0.6 meter down at El Sos Observatory out. And it's not far from CTIO in Chile anyway. We got lots of data that we've been analyzing. Rick Wasson did some really fine speckle photometry, kind of pioneered that field. And so this is last year in June. We've been observing, quite some time, but this was the first speckle run, kind of a production run. And so on the left there, that's Tom Meneghini, the director of Mount Wilson Observatory. He's just been wonderful to work with. And on the right there, that's Leon from Germany, putting the camera up on the 60-inch. And this is just, we have got results on 50 closed binaries, and some of them are quite close, down below 0.2 of a arcsec. You can, if you look on that list, you'll see some down to almost down to a full 1/10 of an arcsecond. And then really lots of papers. It was just a great run. And here's just an example of one. And so this is a separation of 0.24 arcseconds, or if you like, 240 milliarcseconds. And you can see it's magnified. You can see the speckles, excuse me, the pixels. And so this is on Desmos, some analysis. So this is the orbit. And if you look at the lower left, you can see that the recent observations, the TOC observations, those are Toca-Vinen on the 4.1 meter down in SOAR telescope in Chile. And then you can see on the far left there, it says MWO 2023. That's our observation. Well, it's clear that the orbit, which was published in, I think, 2009, is inadequate. Things are going off track. So here's a new orbit going through it. And if you look, you can see our one at Mount Wilson is slightly off the new orbit. The new orbit goes very nicely through the 4.1 meter observations. We're off. Each of these squares is 10 milliarcseconds. We were off about about 5 milliarcseconds compared to Toca-Vinen's 4.1 meter observations. Okay, and I want to show now. Let's see if I do this.
In June of 2024.
Can you hear that?
A dedicated group of students,
Yeah.
educators,
Okay, I'll
and
just get full
amateur
screen.
astronomers took part in the Society for Astronomical Sciences Symposium and conducted observations using the 100-inch and 60-inch telescopes at the Mount Wilson Observatory. Here is a glimpse into that week.
Okay. I think we needed some up-tempo music like that. That was great.
Yeah, let's see again.
Yeah, that was a nice video. Thank you.
There's a question.
So is that your presentation? Are you ready for questions?
No, a couple more slides here,
Okay.
and then I'll be finished. Okay, so I need to share. So you can see the slides okay again?
Yeah.
Okay, so this was on the 100-inch. This was the equipment setup, and essentially we had a QHY camera behind a 2-power power mate. There's the picture of the camera on the 100-inch telescope. This is on the refractor focus on the side of the telescope, and but it's got the full 100-inch aperture. These are the double stars, known double stars we observed. There's one with about 100 milliarc second separation. There's one with 60 milliarc second separation. This is the Gaia satellite. It was launched in 2014, but it's only recently that we're really getting the good results from it. And this is the array on the sensor, and close double stars go across the field, and they confuse the system, and to make a long story short, they have a classified what they call non-single stars that are mainly binaries. They're able to get orbits from Gaia, but there's a whole bunch of stars that they can't get it. Yeah, I'm going to skip through that. And so here's 5 systems we observed on the 1 meter, and we've discovered new triple stars. New double stars on that list. So we're going to have another run in October. The camera, the QSY 600, it's not very efficient. In fact, most cameras aren't very efficient in the IR, and we were mainly looking at red dwarfs, binaries, and so we needed a camera that was much more efficient. So this is the ASI ZW ASI 462 mm, and it costs $250. And it's so good that Andrei Tokovinin down on the 4.1 meter SWORD telescope, he stopped using the $80,000 Andor cameras, and he now uses this $250 ZWO camera on the SWORD telescope, and we're going to use it on the we got a run coming up in October on the one, and we're going to have a wide field camera. So this is the full frame wide field camera we're going to use, and this is the a motorized flip mirror to go between the wide field and narrow field. Dave Rowe has come up with Orbit's addition to his speckle toolbox. I don't have time to go through it, but we're able to use it to come up with new orbital elements. It's really great, and it kind of completes the speckle toolbox. It just kind of does all the speckle lengths you need. And in just a couple slides here, so in the future, we're planning on getting time on the Gemini telescope, the 8.1 meter Gemini North, working with Zach Hartman, a professional astronomer. So we're going to apply for time for some of the telescopes. And then we're working with Chara. We're going to apply for time on Chara too. And I think we'll get time on Chara for some really close binaries. And this is the last slide. So we have a run the 29th, 30th, and 31st of October on the 100-inch. We still have some room in the monastery. So if there's people that want to join us on the run down at Mount Wilson with a new camera system, be most welcome. So at any rate, so let me stop share, and that's it.
Okay, thank you. We have a couple of questions in chat. Do we have any questions here? No? Okay, let's go to the chat. Okay, rid of that. Okay, great presentation. This is from Alan. What is the smallest separation in a double star accurately measured by speckle? Any other fields of research speckle can be used for? And are speckle techniques used by space telescopes at all, or just on ground telescopes, which have to deal with seeing issues? Okay, so more than one question.
Yeah, so the last one's the easiest one. The space telescopes don't have the atmosphere, so they don't need speckle. Although, as I was showing, the James Webb Space Telescopes can use sparse apertures, which is something we can do at the ground. So there's besides double stars, binary stars, there's everything speckles used for. The 3.5 meter Air Force telescope on Haleakala, for instance, does daytime and nighttime observations with speckle interferometry to look at satellites like Chinese new satellites put in orbit. The 6 meter solar telescope in Haleakala, they use speckle interferometry during the daytime to get clearer pictures of the fine detail on the solar image. It's used for asteroid binaries. So there's other uses for speckle. And then this first question was what's the closest you can get? And so so on the 4.1 meter SOAR telescope, well, the 8.1 meter telescopes, both the north and south, they're equipped with speckle instruments on the telescopes all the time now. And so you can just request time on them. And they're good 10 to 20 milliarc second separations, depending on the wavelength you're operating in. And if you want to go more closer than that, then you have to go to an array like Chara.
Okay. Okay, and then John asked, how was the 100-inch in practice compared to the 60-inch at Mount Wilson, given how the 100-inch has the extra optics now for visual observing?
Yeah, so it's an interesting question. So there's a couple of dimensions to this. One is the ease of operation. The 60-inch is much easier to operate than the 100-inch. So we can get a little faster. But on both telescopes, what we've done is we position the dome to the south and we don't move the dome anymore. We operate it on the 100-inch. It takes a long time to move the 100-inch telescope. And we also wanted to put the operating equipment next to the 100-inch operating telescope position, which hasn't changed much from Hubble's days. And so by positioning the dome there, we actually turned the power off to the dome so it couldn't be moved, and we could tape cables and move stuff up on that where it's between the part that moves and doesn't move. And from an optical point of view, aperture is everything. We think there's a little bit of distortion put in by using the refractor feed. Essentially, it's you take the there's a cast focus, they call it north port, and it's about a 3-inch diameter image at that point, and they just use the lenses to relay that down the side of the telescope to a 3-inch eyepiece receptacle at the bottom, and that is going to add some distortions and problems. So our plan we're working on, and Mount Wilson's making up a plate for us. We're going to put it on the south port, and then put a big Botter instrument selector up there. And so we'll be able to operate, and instead of using the north port on the refractor, we'll be able to use it more directly. So that should help it a little bit. But the south port with refractors has worked quite well.
So I'm curious, Russ, what are your biggest surprises so far with speckle?
Well, the biggest surprise ever was this Dave Rose thing when Dan came down and we got the results that night of all those stars, and yeah, that was just such an eye opener of what speckle could do.
Is this an accessible technology for somebody with a, say, a 12-inch go-to telescope?
Oh, absolutely. Yeah, the big game changer was when ZWO came out with the first CMOS camera with a Sony chip. And I can remember that. So that was almost a decade ago. When I heard about it, I immediately ordered one of those cameras and put it on my 10-inch Celestron. And that was another wow moment that you could get a camera for a few $100s. I think that was $400 and get these amazing results. So yeah, you can put it on. It helps to put a Barlow in, and now it helps to have that CWO 462 camera. And so if you can have a flip mirror, and a manual flip mirror is fine to flip between an eyepiece or a wide field camera and a Barlow speckled CMOS camera. And the software was very difficult. It was hard to use to begin with, but Dave Rose Speckle Toolbox has made that all easy, and he made the analysis easy. We struggled for years calculating the orbital elements. We would get an apparent orbit and get that worked out, but that's not enough for the professional publications. You want to reorient that orbit and solve for the elements like you were seeing it face on. And so that's a real recent addition. Just this past year, Dave added that capability to the Speckle Toolbox.
Yeah, Dan came over to my place about 5 years ago with one of his cameras and his laptop, and we hooked up to my 28-inch in my backyard, and we picked a star out of this big database and got some speckles, and Dan analyzed it, and it was like, pop, there's the 2 stars. It was like magic. It was really pretty exciting.
I think this isn't surprising, but it's the big lesson is that amateur astronomers, as exemplified by the Altice Initiative, really come up with things that the professionals don't necessarily come up. So we make a good alternative. We've come up with robotic telescopes. We've come up with what led to the this whole plane wave instrument suite of telescopes now, and the professionals now kind of taken over plane wave instruments. They're busy building 900 Delta Rho cameras for the Argus array. And they've had the 1 meter telescopes now around the planet. But at any rate, the Altice Initiative has just done a lot, and I'm delighted to see it keeping going.
Okay, so thank you, Russ.
Most welcome.
Yeah, it's always a pleasure, and I'm glad that we were able to do a run through before the real presentation to make sure everything worked out okay.
Yeah.
Yeah, so that was good. So we are going to move on now. So next on the agenda is, let me double check. Yeah, Cindy Krach, second presentation. This is really cool one. Oh, there's Jerry. Hi, Jerry. So this is about Cindy's adventures in grinding an 8-inch mirror. So this is a presentation that she pre-recorded. So I'm going to pull that up and we can watch. Go. No, I don't want to start that yet. Zoom, share screen.
Aloha, my name is Cindy Krach, and I'm a retired veterinarian, an amateur astronomer, and a member of the Haleakala Amateur Astronomers on Maui. I'm also the Astronomical League Sketching Observing Program Coordinator. And I like understanding how things work, and building a telescope has been on my bucket list. I wanted to create a simple, lightweight reflector using woodworking tools and anything else that I had already at home. And I started to think, wouldn't it be cool to grind the mirror too? So this talk is about my adventures and misadventures creating an 8-inch telescope mirror. The reason I wanted to talk about it is that it would force me to really understand what I did and try to put it all together. And if you ever consider grinding your own mirror, I think the most important thing is to have a good mentor. And I was fortunate to have not one, but 2 fantastic mentors. Stan Truitt, master optician here on Maui, as well as my friend Jerry Oltian in Oregon. And Stan is a friend to a pretty famous mirror maker, Mike Lockwood, who was also a great help, especially at the end. So yeah, I was hitting the jackpot here. And before I start talking about my experience, I wanted to talk about some of the mirror making myths out there. Many of them I believed. It doesn't take hundreds of hours to create a mirror. On average, a 6 to 8 inch f6 mirror will take about 40 to 60 hours. You don't need expensive tools. Amateur mirror testers are pretty simple to make, and you use some scrap wood and a few other items. And the grit used for grinding is cheap, and it can be bought in kits. The surface does not need to be perfect. A 1/4 wave error is acceptable, and half wave at low power will still give nice views. And many people find mirror making addictive, each mirror getting better than the last. The next one I found out firsthand is not true. It will not save you money, and at least in my case, it didn't. But the learning experience is worth every penny. And seeing the night sky from a mirror you labored over, I mean, those are pretty cool bragging rights. What you do need is plenty of patience, and a mentor is even more important. And there are a lot of great resources out there. But again, try to work with someone that has a few mirrors under their belt. And you can learn way more from the experiences of other people than from books that become paperweights because you don't understand them. And that was my paperweight right there. And first I needed a glass blank, and I decided Pyrex glass would be a good choice since it would be thermally stable as a mirror and available from amateur telescope suppliers. I ended up buying an 8-inch blank and 8-inch glass tool on the Cloudy Nights classified section. And I was told by the seller that the blank was probably a porthole from a ship, which, that was kind of a fun thought. I had this romantic idea that this piece of glass had seen the wide ocean and now it would be pointed to the stars. And Stan popped that bubble when he told me that Corning made a lot of 12.5-inch portholes, but not a lot of 8-inch ones. My next step was to perform a stress test on the blank in a dark room. And the blank is held between a white LCD computer screen and a polarizing filter while looking for irregularities. And the stress test shows up in the dark glass as dark irregular areas as seen in that Pyrex pie plate on the top right. And the reason you don't want stress is that it can deteriorate the reflected image. But stress can also cause the surface to grind unevenly, which can be disastrous. I mean, think pieces chipping off. The left image is my blank taken through a lunar polarizing filter, and I was pretty happy to see that it looked clear with no obvious defects. The first thing I learned about mirror making is all light focusing at one point is the desired outcome of mirror making, and a parabola is the only shape that will accurately focus light from infinity and is the key to making a telescope mirror. A parabola is not a sphere, showing how much attention I paid in geometry. For years, I repeated the simple information about my reflecting telescope at star parties. Yeah, the light comes in here, it hits that curved mirror there, and the light is redirected to the secondary mirror and is focused at the eyepiece. Simple, right? What I didn't realize was that creating a parabolic mirror surface means shaving thousands of inches off the glass surface from a spherical shape in order to obtain that perfect optical axis. And I like this illustration for understanding what a spherical mirror is. It's important since we're going to start with a spherical surface before we figure the mirror. A spherical mirror is just a small subsection of a larger imaginary sphere. And it's pretty close to a parabola, but focuses light differently. And if they're so close, then why is a parabolic mirror needed, you may ask? A spherical mirror will produce an image when light is directed towards the surface, but that image will not be sharp. And this is why. For a spherical mirror, light rays that reflect off the mirror from far away will not all focus at the same point. And that's because the light from the edges of the mirror focus a little bit closer than the rays reflecting off the center. And this causes a blurry image of what's known as spherical aberration. A parabola, on the other hand, can focus all light from infinity on its focal plane to a point. And understanding this was like a head-smacking moment, because I had always thought of the mirror in my 8-inch Orion as a spherical mirror. So figuring to create a parabola now made complete sense. And now let's look at what happens to light from center of curvature. And what's useful for testing is that light coming from the exact center of a sphere reflects back to the same spot on the optical axis of the mirror. However, for a perfect parabola, light instead returns into different focal planes along its optical axis. And we'll explore this again when we talk about one type of testing. Now it was decision time. There were a number of simple calculations I needed in order to create the mirror. I had an 8-inch blank, actually a little less, and I needed to decide on a focal length for my mirror. I also needed to decide on a focal ratio for the mirror. Most first mirrors start simple, like a 6 to 8-inch f6, but I didn't want things simple. Since I already had an 8-inch f6 Orion telescope, I wanted something larger. But Stan wanted me to stick with an 8-inch for the first mirror. And I then thought, okay, let's do like a shorter focal length or faster mirror, which was also discouraged. And at the time, I remember feeling a little annoyed, but by the end of this adventure, I understood why I didn't want a large or fast mirror to start. So my plan was to aim to create an f5 8-inch mirror, even though it'd be a little bit more of a challenge than an f6. And these are the 4 basic steps in order to create a mirror from a glass blank. The first step was rough grinding or hogging out. And John Dobson describes this part of the process as caveman work. Eat well, sleep well, work like hell. And rough grinding was definitely some work. Yeah, it was. Before starting to grind the blank, I needed to create a 45-degree bevel or chamfer edge on both the blank and the tool. And I was using the edge of a sharpening stone initially, but then later a Dremel tool to keep the edge in place because it was quicker. And this needed to be done frequently, since after a few sessions, the bevel edge would start to disappear. And I was grinding, as I was grinding more glass. I used a small wooden table, and I created these rubber bumpers to help hold the blank or tool in place, and found that shelf liner material worked really great for gripping. I also needed to figure out how much glass to remove from the center of the blank to get the curvature I needed. So working towards an f5 with an 8-inch mirror, the equation gave me a depth of about 0.1 inch, which was almost the thickness of 2 dimes. And this was a cool, quick reference from Jerry, who amazingly knows the depth of a lot of coins and business cards. My goal was to dig out a smooth central depression using the tool and coarse grit, but there are other ways to hog out. I started by wetting the tool and sprinkling some of the grit, and I used specific strokes. Each stage of mirror making requires different strokes, some strokes for more than one purpose. You rotate the mirror and tool in opposite directions as you walk around the table. If you don't, you end up with a mirror that repeatedly gets strokes in one area, causing an irregular rather than a spherical surface. Think potato chip mirror. Hogging out gives you a lot of time to think. Questions like, what's for lunch? And why couldn't I use the bottom of a Pyrex pie plate for a mirror, since I noticed it had a curve and could it be figured? And at this stage, every surface that I looked at looked like a mirror waiting to happen. As far as the pie plate, Jerry said someone in his astronomy group did just that, figured the bottom into a mirror. And, thinking back on the stress we saw on the pie plate, we marveled. And I had a turkey sandwich for lunch. To say coarse grinding is a noisy process is not an exaggeration. Okay, maybe this is. But the grinding noise is evidence that something is happening as you grind grit, which is harder than the glass you're trying to remove. And this is just a short video of Stan instructing me during that first wet session. So it's pretty noisy. The random motions of grinding and polishing two pieces of glass together will naturally result in a spherical mirror. And while writing this, I thought, wait, why does that happen? And this is because when you begin hogging out with the mirror on top, you apply even pressure. And the edge of the tool on the bottom creates a central depression in the blank. And since the edge of the tool wears down as well, it becomes convex, and the blank naturally becomes a concave surface. And after a few hours, I could appreciate that the blank was milky and that there was a slight dip in the center. And after a few more sessions, nearly all the concentric circles on the tool were gone. And then I made it up to just under 0.1 inch depth, and I could almost fit 2 dimes under the edge of the ruler. And I was so excited. I wanted to just keep working, but my daughter was annoyed and wanted me to come into the house to make cookies. And Jerry said I had reached a milestone in mirror making. Your family has complained you're spending too much time on the mirror and not enough with them. I also started to get this feeling of kind of like little needles in my hands after each session, and later developed a pretty painful swelling at my thumbnail base, and it needed to be lanced by my doctor. I suspected it was a glass sliver, so from here on I wore gloves and it didn't happen again. Okay, on to step 2. I was instructed by Stan to create a long gash in the green tool center, which really bothered me, and I put off doing it because it just looked so perfect with all those, those rings evenly ground down. And the reason for the gash is to help the tool, keep the tool and blank from sticking to each other during fine grinding. And I created that ugly central gash with a Dremel tool, and I just had to repeat in my mind another John Dobson quote: "Diseases of the tool are not contagious to the mirror." And I don't think this is what he meant, but I'm using it anyway. It was also time to move on to the next grit size. I needed to get rid of everything with the old grit so I wouldn't contaminate the blank, since we're going from a rougher to a finer surface. Before going from one grit size to the next, I was using a bare filament bulb in a dark room, and I was glancing it off the surface to look for any irregularities or pits in the glass. And at this point, I had ground 2 dimes depth, and I needed to see how close I was to the focal length and ratio I wanted. I wetted the glass first to make it more reflective, and in the video, it's actually in the lower right corner and it's out of the picture. When the mirror was struck with a strong beam of light through the sunlight, it was exciting to see where the light was focused on the cardboard. And this distance from the cardboard to the blank was my focal length, and I was right on my mark. And at one point, I actually had the idea to save grit and reuse it, kind of like when your mom would have you wash that paper plate because it's still good. I decided this was too much work, and I did have plenty of grit. And also, Jerry sent me this image of what happens to grit as you use it. It loses its sharp edges, which makes sense because the action is kind of like a rock tumbler. You're grinding the grit edges smooth. I could now actually feel the concavity of the blank as the tool and blank slid over each other. And now the blank surface was so smooth that I always needed to hold on to whatever was on top or it would slide off, reminding me of another great John Dobson quote: "If you drop your mirror, be sure to do it early." Oh yeah, I have no intention of dropping it now. And here I am using the remaining grit size for fine grinding. And you can also hear how the sounds of the blank and tool together have changed. As you can see, Doesn't really make any sign. Once the filament test showed no pits, it was time to move on to polishing. Step number 3. Now that my mirror was ready for polishing, I needed to change the surface of the tool. So the next step was to pour a pitch lap onto the surface. And a pitch lap is used with a polishing agent to get the mirror surface extremely smooth and to parabolize. And the polishing material actually gets embedded into the pitch and smooths out the irregularities from the fine grinding process. And I met with Stan and we melted that Google's pitch in an old double boiler, and it took a really long time to melt, but we wanted a molasses consistency for the pour and didn't want it to boil. During the pour, some of the pitch didn't quite make it onto the tool, and there was one corner that was not completely covered, but no worries, the pitch should spread out during the polishing phase to fill in that gap. And cerium oxide was applied to the warmed mirror, and while the pitch was still warm, we put the mirror on top and applied pressure. And they're mated so that the pitch mimics the mirror's surface. And after the mirror was removed, a razor blade was used to cut channels into the hardened pitch of the tool. And this is for the polishing agent to flow through and for the mirror's surface to mimic. And when I began my first polishing session, it was a really strange sensation. The lap on the mirror felt really rubbery and resistant, even with a lot of cerium oxide. And I was advised not to rest my fingers on the sides of the mirror as I was polishing, since warm edges can cause the glass to expand and contribute to a turned down edge. And at that point, I didn't know much about a turn down edge, but I knew it was something to avoid. And it was difficult to not grip the mirror at first because of the resistance I felt. And I later talked with Mike Lockwood about that, and he said that it's really hard not to, and that he's never found it to be a problem. So while polishing, there were times I could get into this really mindless Zen kind of rhythm, and I enjoyed how smooth it felt, but there were times I was also really bored and my back ached. So raising the table helped, and books on audio were a savior during this phase. And during polishing, it was thought that the pitch would move out to the edge of the tool where it was missing, but it never did. So I went ahead and did another pitch pour from home. And this may have been one of my worst days in the mirror making process. I was melting pitch on my stove using 2 lasagna pans, and one acting as a double boiler, because I thought, wow, if I could melt it faster with a wider surface area, I could then throw out the pan when I was finished. What I didn't take into account was that the wider surface would also account for faster cooling. So the pitch never really got hot enough. And an hour and a half later, I went back to a double boiler pan. Even with the doors and windows open and a fan, the house was full of strong odors as volatiles were released from the pitch. And yes, those fumes are toxic, and that was really dumb. You need good ventilation. When I poured the pitch, I filled that gap first, and then I poured the rest onto the old surface, but it just stuck to the middle instead of spreading out. And I quickly tried to press the pitch into place with my fingers, but it was just a mess. So I decided to give up and try another day, where I gently warmed the pitch tool in the oven, and then I moved the surface around with my fingers and remated it with my warmed mirror, and that worked. I began using a laser light with a baffle on the end to check for the surface smoothness of the glass. You're scanning the surface with a light and looking for it to eventually disappear with continued polishing. But a faint light will usually remain, and it's acceptable as long as it's uniform across the surface. So looking at the mirror was a little confusing at first, because there are back reflections as well, but these are fuzzy compared to the surface. And on to the fun stuff. There are 2 methods commonly used by amateurs for testing, the Foucault and the Rankine. And Foucault is considered the gold standard and big daddy by many amateur astronomers. The tester is relatively simple to build, using scrap wood, a light source, and a dial indicator for measurements. The Rankine is also easy to build, using a light source and a mounted grating, which produce lines on the mirror surface placed at different distances from the mirror. Jerry sent me a Rankine tester he built. and Stan asked his friend, Mike Lockwood, if he would send a mirror tester I could use for Foucault testing. And you may recognize the name. Mike Lockwood is one of the most respected mirror makers alive. And Jerry likened the loan of the tester to having Einstein loan you a slide rule. This is Mike with a 1,200-pound, 50-inch primary f2.2 mirror, he figured. And when Mike was visiting Stan here, I had the opportunity to have dinner with them both. And Mike was a great resource when it came time to use the Foucault figuring software, Figure XP. And he was also kind enough to review this video and help me with corrections. Besides his mastery of mirror making, he also loves roller coasters, something we had in common. I picked up Mike's tester from Stan, and I already had Jerry's Ronchi tester. And I fully intended to learn both methods and decide myself which worked best in my hands. I was in contact with Mike, and he said, I think you will learn more this way, and you will see the superiority of Foucault. Then you can annoy Jerry. Mike reminded me that he is a professional mirror maker, and he has to produce data and test results for his work. Jerry prefers Ronchi testing. He's made a dozen or so very good and excellent mirrors, and his group includes Mel Bartels, who is a legend in mirror making. Mel is also a big fan of Ronchi testing and has a great webpage about why he prefers it to Foucault. So Stan and Mike with Foucault in one corner and Jerry with Ronchi in the other. Yes, this was going to be interesting. Before testing, I needed to create a mirror holder. With Ronchi testing, I could actually just lay the mirror against a pillow, aim the tester at it, and get a reflection. But Foucault needed a stable, reproducible setup. The Ronchi test. It takes place looking at a pattern of lines reflected from the mirror being tested. And it's considered a qualitative test since it gives visual information about the surface, the smoothness, the shape of the mirror, and is very sensitive to something called a turn down edge. It does not give hard numbers like the Foucault. However, there is a more sensitive test using a program by Mel Bartels using a matching Ronchi pattern where mirror reflections are compared to a perfect parabola by overlapping images of the two. And I began testing using the Ronchi right away because it was so easy to use, set up, and interpret. I mean, within 5 minutes of getting it out of the box and aiming the tester at my mirror, I could see the reflections on the surface. And one of the best things about Ronchi testing was I could easily get feedback about my mirror after each polishing session. And having this setup also made it really easy to find the center of curvature, which I could then use to remeasure my focal length with greater accuracy. And from center of curvature, all light rays within a sphere will be reflected back to the same point. And this produces perfectly straight lines on the ronchogram. Any deviation from straight indicates a non-spherical surface, which is what we're looking, to eventually get towards, a parabola. So using a program created by Mel, Jerry created a set of computer-generated patterns that were specific to my mirror. And the plan was to get the flat surface of the mirror to a sphere first, and then keep testing and watch as those straight lines bend gently at the start of a parabola. And these were my first set of ronchogram images. And unfortunately, what was evident to everyone was that I had overshot a sphere and jumped right into a hyperbola or overdone parabola. And this was evident by the curvature of the lines, both inside and outside center of curvature. What was also evident by the kinked lines on the bottom images is that I had a turn down edge. And a turn down edge makes the outer portion of the mirror useless. And this is a problem since the outermost portion gathers the most light. And a turn down edge is a common problem for people grinding a first mirror, and it would go away as I polished away the overdone parabola, but it would probably be the last thing to go since I basically had to lower everything else down to match the edge. And a turn down edge is just as it sounds. The edge of the mirror is sheared off or turned down. The pitched lap rides up too far on the rim of the mirror and it hits the edge, removing glass. And in my case, the reason was possibly too long or wide of strokes, but later I realized it may have been the hardness of my pitch. And I had not been testing until well into the polishing phase. And of course, it would have been better had I been testing all along. The Foucault test. It makes a quantitative comparison between measurements in the order of nanometers. A light source is directed onto the mirror, and the reflected return light passes a knife edge. And this cuts the beam somewhere in its path. And we're comparing measurements of where the light is blocked or nulled at a given zone on the mirror with a theoretical parabola that we're aiming for. And remember this slide? It helped me a lot in understanding how the Foucault test works. For a parabolic mirror, the return bundles of light from center of curvature fall on the optical axis within an area known as the line of longitudinal aberration. Try to say that fast 5 times. In this example, light rays fall on this imaginary line at different locations, as noted by those arrows in the upper part of the image. And these arrows will correspond to the 5 zones that we're going to test for on the mirror. We can cut off or null each bundle of light from specific zones with the knife edge and measure where that takes place using the dial indicator on the Foucault platform. And if we take a closer look at that previous diagram, we can hone in on that line with the long name. The longer the focal ratio of the mirror, the wider this line becomes, giving it greater tolerance to error. And shorter focal lengths have a narrower line, and light falling outside this line results in a blurry image. And this helped to explain why an F5 would be more difficult to create than an F6. Now imagine the line of an F3 being that much tighter. This is another reason why mirror making classes start with an F6 or greater. The mirror is placed on a stand and a mask is placed over the mirror. Measurements of the mirror zones are taken using a coder mask made to the specifications of the mirror. The cutout is used to mask off parts of the mirror so you can measure specific zones and then compare them to a perfect parabola. Now that I understood how the tester worked, it was time to give it a whirl. But my experiences with the tester was at first a hateful relationship. When I first set up, I could not get the tester to work or reproduce the expected reflections. And then I realized I had the tester backwards. But even after getting the tester pointed in the right direction, I found at first the test was very difficult to set up and interpret and not readily reproducible. The light pointed at the mirror must be perfectly aligned along the mirror's optical axis. And at this time, COVID was in full swing and everyone was social distancing, so I could not go see Stan and was learning things the hard way. And I also didn't want to look dumb, which was dumb. And I figured I needed to work it out myself, which I eventually did. And I think had I been meeting with Stan, it would have saved me a lot of aggravation during this part of testing. So I started setting up in a dark closet where everything stayed put during testing, which made for quicker setup, but made everyone unhappy because we couldn't put the vacuum cleaner away. You need to have a place that things don't move to have a reproducible result. And I used a laser with a makeshift attachment to center it to the tester. And after getting everything lined up, my iPhone clipped to the tester helped immensely since the reflection on the mirror was magnified and it didn't change when I moved my eye, and I could make recordings. And testing did get easier over time, and I felt like I was really getting the hang of it, and it actually got kind of fun. This is just a short video showing the light being nulled at zone 1, or the most inner zone. And actually, zone 1 is not quite nulled here. It's a little bit darker on the left, but you get the idea. What you want is to see it become equally gray on both sides of the opening in the mask because light's being blocked by that knife edge. And measurements are recorded for where this occurs for each of the zones. And as a geeky little fun aside, I use the calculated length of the line for my mirror. And I was aiming to get all the light to fall within a range of 0.095 inches on the optical axis. And the direct measurement I came up with using the Foucault dial indicator was 0.2 inch. This calculation told me I was overcorrected by a factor of 2, or basically 100%. And it was kind of cool to see how overcorrected I was in numbers. And as I continued to work to remove the turned down edge and return to spherical, it was going much slower than expected. And during the process, I also created some irregular zones, which were easy to see on the Ronchi. And I began to notice my lap was really hard and brittle. And while cutting the grooves one day, it just crumbled. So I ordered the softer number 64 pitch, and I went on to another pour. I was getting better at that. But I continued to polish, and I was getting frustrated by the slowness of my progress. And at times I would put the whole thing away for months at a time. And then I jumped back into it, determined to get it right. And only much later did I realize my pitch was still way too stiff. Then everything changed in one day after changing one thing, the temperature. And Jerry asked how hard my pitch was, and it was hard. I couldn't even dent it with my fingernail. So he recommended trying a warm room. And I took my entire setup into the bathroom, and I heated up the room with a space heater to almost 80 degrees. And the surface of the mirror changed so quickly, I had to stop every 5 minutes to test. And I was able to get the mirror to spherical in 45 minutes and get rid of the last of the turned down edge. And after 30 minutes, I had moved on from the straight Ronchi lines of the sphere to the gently curved lines of a parabola. And Jerry told me not to breathe, that it was time to star test. He also said this was plain luck and a very rare occurrence. And I really didn't think about how to get to a parabola. There was no figuring here. I just kind of fell into it. And I had put in 23 hours of polishing, and the last 1.5 hours took me from turned down edge to sphere to parabola. Go figure. Yes, pun intended. In retrospect, Mike had also told me my pitch was too hard long before Jerry did. I found an old email where he likened the hard pitch to trying to wash your car with a block of ice instead of a sponge. I also sort of forgot I live in the cold mountains and not at the beach when I decided on my pitch hardness initially. A little about mirror quality. The screenshot on the left is from Dick Parker's video series, excellent for understanding methods used to validate mirrors. And it can get pretty confusing, so I like the term circle of least confusion. I mean, how do I get in there? When testing the quality of the mirror, you're looking to see how smooth the surface is, and it must be very, very smooth. When it's not, there's a scattering of light waves coming off the mirror surface as they head towards a focal point. And this error can be measured in waves. Small dislocations of the wavefront with respect to the ideal location is known as wavefront error. And one of the standards that Foucault uses is the Danjon-Coder analysis. In simple terms, it just says that most of the light should be in something called the airy disk, a region where most of the light rays converge into the smallest bundle along that longitudinal line of aberration, and that the wavefront error should be less than a quarter wave if the mirror surface is uniform. In figure XP, Mills-LaCroix analysis just takes that one step further with an inner and outer acceptable deviation from perfect. A 1/4 wavefront error standard is considered an acceptable mirror, and anything 1/10 of a wave or greater would be a very good mirror. Figure XP program showed numerically how far off my mirror was and in which zones, plotted on a tornado-looking graph. And I have been getting results showing that zones 2 and 5 were off. The outer zone 5 was probably due to that turned edge. And after the heated bathroom event, I obtained new data sets of Foucault measurements. And this analysis was by far the coolest visual for me, since all the values needed to fall within those curved green lines for a good mirror, and now they did. And the analysis from Foucault showed 1/15 wavefront error from my collected data, assuming all areas of the mirror are equal and regular with no lumps and bumps. After I created this presentation, Mel ran my last Ronchi images through his new Ronchi null program and pronounced it indeed a superb result. At this point, I feel like I've fallen down another rabbit hole, so I'm hoping that Mel will talk a little bit more about his testing. And Mel also mentioned that both luck and skill are required, and I think luck was definitely on my side. But now another test known as the STAR test is needed, no matter which test I use to get this far. And there are a number of things that are looked at in the STAR test, but it's pretty simple. You observe what a star looks like inside, outside, and at focus. And it's most useful once your mirror is close to being parabolized and is easy to perform and very sensitive. You need excellent conditions, perfectly aligned optics, and a high magnification to look at the airy disk of a star. Shaken, not stirred. I did get the mirror set up in my Orion telescope with some modifications for the mirror's shorter focal length, but it was never precise enough to do star testing. So I just went on to build a telescope, which I have to admit I enjoyed way more than creating the mirror. I have yet to star test, but I did aim the uncoated mirror towards the moon and get an image, and wow, that was really very exciting. And this was the time I put in for the mirror. The blue is the expected time needed to finish each step. It took me about 2.5 years, only because I kept putting it up for extended periods of time. Stellafane reports most 6 to 8 inch mirrors take about 40 to 80 hours of work, but some people can make them in as little as a long weekend. In my case, I spent way too much time polishing and really hardly or any on parabolizing. And these were my costs. A new f5 8-inch mirror factory made would probably cost about $235. But I would have missed out on this really awesome learning experience. And what's that worth? It's priceless. And I don't fully have a grasp of everything yet, especially parabolizing, but I must say I appreciated what both tests could tell me about the mirror. And that for someone that gets frustrated easily, Ronchi was a far simpler test. I do prefer the Ronchi testing in my hands, even though I appreciated the value of those hard numbers the Foucault provided. The sciencey part of my brain just loved those numbers. But if the STAR test is the ultimate end, does it matter how you get there? What I realize is that Ronchi could get me almost to the finish line, and STAR testing is the finish line. Okay, that's it. I would again like to thank Stan, Jerry, and Mike, and everyone here for listening. And as Stan would say, aloha.
Okay, let's bring you up so you're the star of the show. There we go. Okay. Any questions here? Yes.
Just want to mention the GSO mirror probably would be a 15 plate.
Yeah, so Jawad's, his comment is that GSO mirror that would cost around $235 would be very unlikely it would be 1/15th wave. So you definitely got a better mirror making it than you would by buying. Okay, let's look at the chat. There's a couple here. Okay, from John. It's immediately clear that Cindy's presentation would be a wonderful one to share in the Saturday afternoon program at the annual Stellafane convention in Vermont. Cindy, maybe you can attend Stellafane someday soon, although it would be a long trip for you. They have an ongoing year-round program teaching telescope mirror making. It's pretty cool. Your example doing it would be very welcome there. And by the way, the Stellafane website for amateur telescope making is a rich and deep source to mine. About 1,000 people attend Stellafane. Yeah,
I would love to make it there sometime. And yeah, I used Stellafane website for a lot of the information I needed to make the mirror. Excuse me.
So, yeah, so there wasn't a question.
Thank you, John.
And there, yeah, that'd be very nice. So in the recorded presentation, you mentioned that you would hope Mel would make a few comments about his Ronchi testing program. And Mel, if you're available and willing to make a few comments, here we go. Just unmute yourself.
Hi, can people hear me, see me?
Yes.
Okay. I can't see myself. I'm like the invisible man.
Yeah, you're definitely visible here. We see Barb in the chair. Hi, Barb.
the wonders of wide field optics, you know, on this tiny laptop. Well, I just think that what Cindy did was absolutely wonderful, and I do believe that it takes skill and luck to make these mirrors. And I'd like to ask her if she's still interested in making an F3.
Oh, you're muted, Cindy.
Yeah, that's still possibly on the agenda, but I haven't even star tested this one yet. I'm embarrassed to say. So yeah, I'm going to draw it out so that it takes a little longer to do.
You know, star testing, that first star test, it is, you hold your breath. And then you're like, don't pass out. Don't pass out. You've got to at least look. But you're so scared to death that there's going to be something terrible. And then you look and you see it focuses wonderfully. Yes, yes, it's great. It's wonderful. And then there's that moment of strength or weakness, depending on your viewpoint, when you go, I'm going to make another mirror. That's when you need to say yes. But what I find amazing is that you can send me a Ronkigram from Hawaii, and I'm here in Oregon, and I can kick back the result to you in a couple of minutes and tell you that it's luck and skill. Surprise, surprise.
Oh, yeah,
I
Rob.
just want to say I appreciated learning the hard way. You used that word in your learning the hard way. By golly, I'm living that.
Yeah, Rob's presentation will touch on the hard way.
Oh, you bet.
Yeah, yeah.
I also want to say that your chart on Ronki versus knife edge, I've got a slide, puts me right in between the two, and I want you to stick around and see. It's pretty cool.
Okay, I'll definitely be here for the day. And
right.
I agree with learning the hard way. I really think that's where my brain has to think and think forward and think about how to solve problems. If it's just like kind of given to me, it doesn't stick as well.
Right.
I'm looking forward to your talk.
Yeah.
So
So
I have a comment as well. I'd just like to say that I learned more about the Foucault test today, listening to Cindy's talk, than in hours and hours and hours of reading about it. So thank you for condensing that down to where I finally think I understand how the Foucault test works.
Thanks, Jerry.
Yeah, I was very clearly explained. I was really impressed by your whole presentation on its clarity.
Oh my God, the video of the shadowgram showing that zone 1, that was awesome.
Yeah, I think many of us here have seen that and have had nightmares about them. Yes.
Yeah.
So you have
well,
another.
Mike looked at it. Mike Lockwood looked at it and he said, you know, the one is not quite grayed out like the other one. And that's when I first went, oh yeah, you're right. You know, so he was kind enough to review the whole thing from start to finish and gave me a laundry list of things I needed to correct, which was, I really appreciated that. That was one of them.
Yeah. Okay. Richard has a question.
Back in the 1970s, before imagers used.
Can you hear him?
Not really.
Yeah. Why don't you come up here, Richard? Okay.
Back in the, here we go. Back in the 1970s, before amateurs were using the Ronki test at all, so everybody used the Foucault test. I mentored people at the McLaughlin Planetarium in Toronto and making mirrors. And they had a mirror shop and they had a mirror test lab and everything like that. And all these kids would come in and they were making 6 and 8. And there was some adults making 10-inch mirrors. And all these, I just felt so sorry because I watched all these people make mirrors. And I knew they were going to go back to the end of the subway line to the 17th floor in the apartment they lived in, and they would have a mirror and they would never have a telescope. So I have always said, build your telescope at the same time you work on the mirror. And I mean, you know that you have a telescope, a mirror you have not star tested yet. And the other thing is, I would say the Hubble people found out the hard way. You don't trust the test. You put the mirror as soon as it polishes out enough to reflect light, and it's going to reflect 4% light. Stick it in there, and you're going to focus on some bright star. Doesn't have to be very bright, because 4% on a 6-inch mirror is still a lot of light. And there's always the moon. So you've always got something you can look at. And you're going to have a horrible image because it's going to be a sphere, but you're going to realize it's spherical, it's F7 mirror, but it's not that bad. I can see craters in a spherical mirror with, breaking all the rules. And so you begin to realize that all the books and all the stuff is written by crazy, insane perfectionists. And when you get it down to one wave and you're looking at it in the wonky mirror, or your Foucault stuff is looking kind of funny, you're still getting a really good view. You can start to see Saturn's rings. And so the unilluminized mirror is the thing that people keep forgetting. So get your scope finished.
It is.
Yeah. Nowadays, I think the biggest problem, as all the silvering guys are discovering, is getting the mirror shiny again. And, it's costs a lot of money to put the aluminum on a 20-inch mirror.
Thank you for that information, and that's interesting because the tool that was used, I found an image of it from like the 1960s or 70s in a lab, and Stan had said that green tool with all the rings was actually a really common tool that was used back then, and we don't see them around anymore.
Yeah. So there was, Dan.
Yeah, this isn't a question. This is a comment on the John Dobson.
Can you hear him?
Yeah, barely.
This is a comment on the John Dobson quote that you put in there. It says, "Drop your mirror early." And I'm afraid I was in the polishing stage and doing some testing when I dropped mine. That was the last one I attempted about 15 years ago.
It broke your heart.
Yeah.
Twitter.
Yeah. All of us who have made a mirror have either dropped, chipped, or dropped things on them at some point in their making. And so we have scars.
Has anyone else experienced the embedded glass in their hands issue? Because I was pretty sure that was what that was from.
No one here. Anyway.
Okay.
Pierre Lemay here. Yes, I did. I'm working on two 16-inch F3s at the moment, and I'd never had that problem before until earlier this year. And I was rough grinding with 40 grit, and I kept my hands kept hurting, and I saw some blood sometimes. So I kind of figured that I was getting glass or silicon carbide in my skin, and I eventually did what you did. I bought a big box of these gloves at Costco, and that's what I use now. So yes, I've that's happened to me as well.
Okay.
I got plantar fasciitis from walking around the barrel, grinding my 8-inch mirror. I was wearing bad shoes on concrete floor.
Yeah, it's a dangerous activity, I guess. Yeah. Okay. So any other comments and questions?
Very good presentation.
Yeah, it was a very good presentation. Yeah,
Thank you.
And then the production values are certainly, I think, the highest among any of the presentations we've had. Your embedded videos and your little face down in the bottom right-hand corner. I'd like to know how you did all that at some point, but yeah, really good, very clear, and it's a great perspective for a first-time mirror maker. You have earned your wings, and
Thank you.
yeah, I'm really anxious to hear when you do star test what you think.
Mhm.
Okay,
Okay.
so thank you very much. And let's see, yeah. Okay, let's see. Pin, there we go. Okay, I am going to, let's see. Going to get rid of that. Put this in. Okay. Okay, so Richard, do you want to have some comments before your your deck of slides, or you just want me to bring up your presentation?
Bring us a presentation and
Okay.
you know, I can talk over the first slide.
Okay. Oh. Come on. It's a double clicker. So our next presenter is Richard Berry. You may remember yesterday when I introduced Mel and said he's one of the people in our hobby who need no introductions. That is also true with Richard Berry. And so I am not going to introduce him beyond saying that the advice he just gave Cindy is very good advice. And yeah, we're going to listen to a really cool presentation because Richard really knows what's going on with smart telescopes.
Okay, thanks. Let's see, just make sure I know there's where the mouse is. Okay. And let's see, what is it? Shift moves it forward? No, enter moves it forward.
No, just the arrow buttons.
Oh, okay.
Yeah, there you go.
Okay.
That would be
It's slightly different on every computer.
Yeah, okay.
It doesn't want to move forward.
Doesn't want to do it. Okay, click on the screen. That's some advice somebody gave.
Okay.
There we go.
Okay, so
And now they should, yeah. Now
okay,
there you go.
fine. Okay, what I wanted to do is talk about smart telescopes, which is the antithesis of visual observing, which is what we've been really focusing on to some degree at this meeting. Since the 60s, when I got into astronomy, we have seen wave after wave after wave of innovation and changes in how we do astronomy. I mean, it used to be that if you didn't have an equatorial telescope, you had a really third-rate telescope. And then people started building things like pipe mounts and other kludgy mounts. And then the Dobsonian revolution came along, and then Schmidt-Cassegrains came along. And now we're at a point where the Alt-Az revolution finally came home to roost, and the computers and the telescopes got together and they migrated over to the commercial realm. And we suddenly have smart telescopes where the telescope has a camera, no eyepiece, and the image is plate solved. The telescope knows where it's pointed, And then the user, who is typically looking at a computer screen or a cell phone to see the image that's there, goes, okay, the telescope has just said I've initialized. What do I want to look at? Well, let's go look at M8. Click on M8. Telescope slews over to M8, takes a 1-second exposure. You go, yeah, it's there. And okay, now take a 5-minute exposure. Click, and the telescope starts taking 10-second exposures and stacking them on top of one another to build a nice, deep 5-minute exposure. And you're sitting there looking at your cell phone or your tablet, watching the image build up. So, okay, I'm going to talk about, I'm going to talk about 3 of the smart telescopes that people are very enthusiastic about. And I'm going to talk about them in the context of, okay, these things are made for, let me be blunt, people who know nothing about astronomy but have money and always wanted to do this stuff, but it was always too hard. And all of a sudden, here's the telescope, you put it on the ground, you turn it on, and wow, you can see stuff in color in 2 or 3 minutes, much better than you could ever see through, I hate to say it, your 25, 28-inch f3 telescope, fully dark, adapted in the middle of nowhere from the city. Well, what can I say? I mean, this is this is a change in the way astronomy is going to be done. Well, I'm president of AAVSO, and we have always, for 113 years or something like that, AAVSO has been using amateur astronomers to look at variable stars, estimate their brightnesses, report them, and now there's something like 50 million data points in the AAVSO database. But the world of professional astronomy has moved on, and there is currently, as was mentioned briefly, PlaneWave is now building 900 telescopes, which are going to be used in the Argus array. These 900 telescopes will be housed in a sort of a dome kind of thing with a window in the center. These 900 telescopes will point through the window. They will be mounted on a big platform that swings back and forth, and they will track accurately for 30 seconds and take a picture. And then they'll go for about, I think it's about 20 minutes. Each one of those 900 telescopes is taking a picture. Click, click, click. All that data from each one of these are 8-inch telescopes, very nice little 8-inch telescopes. I didn't think it's 8-inch f3 with and they're going down to like 16th or 17th magnitude in that short period of time. Then the whole array ratchets back and it keeps on following. Runs all night long. So all the stars in a 120-degree chunk of sky, we're doing photometry on them in 2 colors. So what's the AAVSO going to do? Right? All of a sudden, the Argus array is just eating your lunch. It's all night long, every star in the sky, in the Northern Hemisphere, is going to have accurate, precision CMOS photometry. So what are we going to do? Well, there's a lot of amateurs out here who are buying these smart telescopes, and they're going to sooner or later get bored looking. I mean, how many times can you look at all the, right? You invite your friends over, and after a while, it gets to be, well, we've seen M8 already. So one of the things we hope we can do is to get them interested in looking at variable stars which change. And one of the things the Argus array and these other big survey telescopes are going to do is find the stuff that is interesting, right? Some star that nobody ever thought of before suddenly gets 5 magnitudes brighter. If they weren't surveying the things all the time, we wouldn't know that was happening. So it's going to throw up a little notice. Boom. Now we get the amateur astronomers to go after it and observe it in detail, right? Because where the Argus array is going to be cloudy sometimes. In other words, there's going to be a whole lot of interesting new work for amateurs to do, different than just looking at stuff. But the professionals are now, by trying to do everything, are actually churning up lots of cool stuff on the side. Okay, so let's talk about the 3 telescopes that I will talk about. The Zwo C-Star, which, because it costs $499, there's a lot of guys who go like, that's cheap. I'm going to get one because I can then do what I've always wanted. This is what it looks like here. It's tiny, 2-inch aperture. You say, well, trivial aperture, right? On the other hand, it takes great pictures. And it's $499, right? I can play with this thing. I get to combine my computer hobby with my telescope, or with what I think. It's a no-brainer for a lot of people. The unistellar equinox, and I chose the equinox. Unistellar actually has telescopes that range from about $1,800 to about $4,800. Some variation in the specs. I chose the equinox simply because it was in the middle of the range. It's 114 millimeter aperture, right? Just like a lot of people's first little telescope that they got in grade school. It has basically a inexpensive sensor, and it covers a field just big enough to fit the full moon in one axis. And then finally, the Celestian Origin, which has just been announced in the last several months. I've been a beta tester for Celestron since last December, and I brought the thing in so you can kind of, knock on it and see that it's actually a real device. So here it is out when I got it sitting there in the snow. So it covers basically 1 1/4 by 8/10 of a degree field of view. It has a resolution on the order of it's almost seeing limit. On a night when the seeing is poor, the images are fuzzy. On a night when the seeing is good, the images are sharp. So it's really using the atmosphere appropriately for a 6-inch telescope. And these are kinds of images people are taking. This is from the C-Star. That's the Pac-Man Nebula. This is actually the first image I took with the EV scope. And if we go back a couple, let's see, this is going, nope, back. By the way, talk about public outreach. This is a perfect telescope. Some of the versions have eyepieces on them because they take the image from the sensor and they roll it back into a little viewer. So you're looking at an electronic image, which is steadily getting better as the stacking makes the quality of the image get better. Yes.
Your field of view on that chart looks way wrong.
It may be. Oh, yeah, it's arc minutes. Sorry.
Okay.
Sorry. No, when I calculated the étendue, I had to convert to degrees and I forgot to change the numbers. Yeah, sorry about that. But for public outreach, for showing other people, and like 8 or 10 people can log on and get the output, because the telescope becomes a wireless point server. Yes, you can log on to it and you can watch it. Or if the guy who's running the thing says, "Oh, I'll give you control," any one of the people using it can log on too. With the Celestron, it turns out any number of people can log on, and anybody can control. This leads to some very interesting fights at some point. No, I want it this way. I want it that way. Okay, so this is the kind of stuff you get. These are, well, this is 40 seconds, and this is actually taken in that lit up parking lot picture that I showed you. The processing is quite sophisticated. They are able to remove your light pollution background. Of course, you're picking up noise, right? The photon statistics don't go away just because, but the results, are remarkably good. And this are like 20-minute exposures. So we're talking, and as I mentioned in the charts, all 3 of these telescopes let you get your MITs on the FITS images that came off the telescope originally. And they stack it. That data is then sent over, a stacked image is then sent over to your cell phone, where they use AI processing to make the image look prettier. They smooth it, they do a bunch of other stuff. Well, okay, so can we get science out of these things, right? I wouldn't call them toys, because no good telescope that lets you get your hands on the raw data is a toy. On the other hand, a lot of people will use them that way. On the other hand, why not see what we can do? And so we've been working on this kind of thing. So are they special? Well, they make impressive color images. You control them remotely. If you can control them by Wi-Fi, there's no reason that I can't control it from anywhere in the world. We just don't have the software yet to let us do that. Excepting smart people will be able to figure that out. But, when I've logged on to the Origin telescope, it logs onto my home network, and then I can use it from anywhere I have access to my home network. So, I mean, we're just one step away. Anywhere I can log into you get it. So I can UPS the telescope out to some friend in the middle of darkest Australia, and I can then drive my telescope from. It's autonomous because it's plate solves, so it knows where it's pointed at. It's self-contained. I can take this thing out. I have the little tablet there, and we could be observing the sky tonight with it. There's no setup. There's nothing fancy. Perfect for public outreach. And you get the data if you want. On the other hand, you can argue, and there is a class of people who says they're just tiny little cells. Who cares about a 2-inch telescope? You're serious. You can't be. It's a Bayer color sensor, right? I mean, talk about crapping up your data. Put a big filter and break the image up into little pieces. How can you do science with that? This field of view is not very big. I mean, compare it to the NP101. The NP101's got like a 3x4 degree field of view. It's beautiful. Of course, you can build your own rig up, and it can't do anything your rig can't, excepting you bought it, put it in the backyard, and started observing with it. And the guy who's built his own system, he's still working on it 4 years later. Going like, well, the UPS cable must have failed. And it's inflexible, right? What you get is what you see is what you got. Yada, yada, yada. There's lots of reasons you can say it's horrible. On the other hand, there's going to be a lot of people buying these things. There are currently 25,000 EV scopes been sold. Okay. Okay. So if 1% of those people have any interest in doing science, well, you've got like 250 potentially dedicated, serious observers if you can figure out how to actually effectively use that. Well, traditional photometry, this is measuring the brightness of stars, is done by very, very uptight people. Okay, there's a way to do it right, and everything else is not doing it right. Okay, a monochrome sensor, photometric filters, and the photometric filters have to be the right kind of photometric filters. They have to have the right kind of passband shapes. Okay. And so the way the traditional photometry works is you have you put a digital circle, copy out the number of pixels and the total value. You look at the circle surrounds it, and that's that gives you your background reference. You total up all that, and this equation, which is kind of hidden behind here, gives you back the raw instrumental magnitude. Okay. Okay. The raw instrumental magnitude is influenced by the atmosphere that you're looking through. It's influenced by the fact that your filters are not quite perfect and stuff like that. So they have elaborate ways of getting back to the true standard magnitude. So this is the kind of stuff people do. And this is something actually Dan will probably remember this star, one of these stars, you were using the lollipop scope to observe this. A few years later, I was doing this kind of stuff. A red that is a photometric red, a photometric green, which is called V, and a photometric blue, which is called B. Okay, so we're getting light curves, and you can see that the blue and the red bunch up because this color, the star is changing color as it expands and contracts. This is a pulsating variable star. So it goes up rapidly and then goes down, up rapidly as the photons emerging ionize a layer of helium inside. The star heats up and it goes through this pulsation cycle. Here's T-core Borne, which everybody's waiting for it to blow up. This is photometry from the last year. If you look at the scale here, that's a half a magnitude. So this thing's flickering a lot, but it's also got a regular periodic thing. And the question is, when is the hydrogen going to overflow and land on the white dwarf and blah, 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 and it's going to blow up? Recurrent nova. Why do we want to get this stuff accurate? Well, astronomers happen to know a lot about stars. And so we plot the brightness versus the color, and color is defined as the brightness in two different filters. Okay, and this tells you where it is. Now, you can go on a plot like this and you come up here and say, when I observe this star, this is where it fits into our big picture of astrophysics. So if we look over here and we see a star whose color puts it about here, we go, that's a weird star. What's it doing there? Let maybe a star, it would be something called a blue straggler, where it was once a binary pair that combined. And so it didn't go through the regular process of evolution by itself. It combined with another star. And so it's in a different evolutionary status than it would be otherwise. In other words, you want to do your photometry accurately because it tells you about the astrophysics. And if you just say, well, it's bright and it's kind of somewhere out here, that's not telling you anything really. So smart telescopes, they all, because they're all intended to make pretty color pictures, they all use a Bayer array filter on the front of the sensor. Okay, this is what your smartphone uses. This is what your DSLR uses. Is in front of the pixels in a regular pattern, you've got red, green, and blue. And these are the tricolors that are used to recreate good color pictures, and the manufacturers like Sony optimize the filters they use in these things, because the fundamental task of a camera, a digital camera, is to reproduce people's skin colors accurately. Nobody likes to be green. Okay, so I mean, this is the key thing. It's also got to make nice skies, nice grass, everything like that. But skin color is the thing they really, really worry about. Okay, so what are we going to do if we just treat this Bayer image the same way we treat a monochrome image? If we sum up the light that landed in this patchwork of colors, we don't quite know what we got. Well, there are lots of things where you want to do photometry where you don't actually have to care exactly where it fits in the astrophysical world. Okay, with a pulsating star, if what you want to do is to find out when it reached the time of maximum light, that doesn't depend on the temperature of the star. It just gets its brightest point. You can fake it, okay? So you can do your photometry on single images, or you can stack, say, 5 minutes worth, and then do your photometry on a stack of 5 images. Case 2 is you can say, okay, well, we got the red, green, blue. Let's take our Bayer array and split it into, this is tricolor red, tricolor green, tricolor blue, so that we don't confuse it with what astronomers call B. And they don't call it, well, actually, Gaia satellite calls them G, but we want to make sure we keep these things separate. And again, you can now split them into the different channels and save them. So we've been messing around trying to figure this out for years. Now here, this is the spectral response curves of the standard photometric filters that have been around since the 1950s. Harold Johnson first did this with photomultiplying tubes, and graduate students spent hours slewing the telescope to one star, putting in one filter and then another filter and then another filter, then measuring the sky, and then going back and measuring another filter and another filter and another filter. It'd take you about 20 minutes to get one data point in 3 colors. And this is the DSLR filters. You notice they don't match. Okay, what we want is to produce the magnitudes we would get if we had these filters, but we're stuck with these filters. So what do we do about this? And I'll come back to this later when we try to fix it. But if you now impose on this the brightness of stars, a type A star is going to be strong in the blue and it's going to decline into the red. And a star which is an M star, like Betelgeuse, it's going to be weak in the blue and it's going to be strong in the red. Well, okay, and the same thing is going to happen with the tricolor filters. You say, well, okay, if you look at the brightness here and the brightness here, and you compare those two, there's going to be a difference. It's going to be brighter. In the case of a star like Vega, it's going to be brighter in B than it is in G. Well, the same thing happens here too. It's going to be brighter in the B than it is in the V. What if we could say, oh, well, we'll look at the slope of this line here, of this difference here, and we'll convert that into this here. Okay, so the conventional technique which is the way that we have been, AVSO and other groups have been doing it, to take DSLR photographs or images and convert them into the standard colors. Typically, they'll shoot some images of standard fields, which might have 30 or 40 stars, maybe, and they will derive what the conversion from one set of colors to the other set of color is.
So they're using predetermined known stars to calibrate.
Exactly.
Okay.
And we usually use clusters. M67 is one, M11 is another. There's also a whole series of fields around the sky, mostly on the celestial equator, called selected areas. And these will have 20 or 30 carefully calibrated stars. I mean, you know, astronomers have spent their lives calibrating those stars because, again, we're always trying to get back to those things so that we can get the astrophysics out of it. Okay, so this is stuff we're looking at. Case one. Let's ignore the Bayer pattern. Let's just see what we can do if we forget it exists. So we're going to just like sum up all this. So here's a simple photometry thing that I did with a couple of students a few years ago. My backyard. The star is called XX Cygni. That's it. And these are comp star and a check star. And the purpose of it is that you use you know the magnitude of the comp star. You don't know the magnitude of the variable star. That's your target. And you calculate also what is the magnitude of the check star. And if it doesn't agree, the check star is not a variable either. This is your check. Okay. If you think about it, that's actually a fairly thin check, right? You got noise and all these things, shot noise and stuff like that. Okay, so so you're looking at a certain radius around it. And what you do is you extract the magnitude data, and this is this table of numbers, variable star, a comp star, and a check star for each one of the images. Now, in this study we were doing of this star, what we're doing was that the star had been reported to come up to sometimes reach maximum brightness early, sometimes reach maximum brightness late. Okay. And so what we were trying to do was determine when does it reach the maximum brightness. These are a couple of high school kids. So here's a chart for the star, and this is all night long. Every 10 seconds, we're taking a picture of it. Okay, and then we do the photometry by saying, forget about the barrier filter, and you can see you get pretty nice results. Okay, this is dusk. Here's dawn. You can see it gets noisy, but you can see it's pretty. And then if you hone in on that little peak there, remember this is once every 10 seconds, you fit a 6-order polynomial to it, and you end up pulling out a time of maximum light to about 20 seconds in a period of about 3 hours. Well, if you think about this, here's this great big star, you know, hotter than the sun, pulsing. It's got all these internal things. It's got star spots or whatever on it. And it comes to the same maximum brightness within 20 seconds every time. That's interesting. Why does it do that? The world is noisy. Why do you think it's happened? So there's astrophysical stuff. Now, this is only, of course, one sample of about a month long. But this was a good project for a high school student and a first-year college student to be engaged in. It's the kind of thing that looks good on their resumes. Okay, so let's take the same technique and we'll look at a calibration cluster like M767. And here's the raw instrument of magnitude. This is what we get by just summing up all those values. And this is the V magnitude from the standard stuff. Well, okay. So if you look at it here, we got up around 10th magnitude and the curve, right? Those should match right up. That's what you want. You want a 1-for-1 correspondence. My raw instrumental magnitude, once I've adjusted it, so if they have the same 0 point, is going to match up with the official magnitudes. Well, okay, what's happening up here? Well, a star brighter at about 11th magnitude is too bright. Oh, this is with the EV scope, by the way. So there's a 114 millimeters. It's too bright. We're getting the pixels are getting saturated, and so it's no longer linear. Okay, so okay, don't look at anything. What's going on here? You got a bunch of guys who are trying to. These turn out to be very red stars, and this is the penalty for the fact that a red star now is putting too much light into the red channel, and the star is coming out anomalously bright in my measurements. It's not as much of a problem with real blue stars, but when you actually go through and look at what those are, you say, okay, we can do good photometry as long as we don't look at very blue and very red stars. Okay, we'll stick within the less blue than Vega, not too much redder than the sun. Well, maybe a K star. Okay. And then this is XXD again. This is now using the EV scope. This is just a proof of concept. Can the EV scope do science? It's a much smaller aperture than that earlier stuff I showed. But we're taking a picture every 10 seconds and then plate solving it. The green dots are the check star. So it actually shows that we're getting the right magnitude out. And here we are coming up on a maximum light. I guess I didn't put in the maximum light, but you can do a nice solution with a small telescope. Well, as one of the ways that Unistellar is promoting its telescopes is they've working with the SETI Institute, the Search for Extraterrestrial Intelligence, to have science projects you can do with your EV scopes. So if you get the app, which you can download for free and look at it, there's 5 different kinds of science programs you can participate in. One of them is exoplanets, one of them is comets, one of them is monitoring the positions of asteroids, which might crash on the Earth. The very smart part, marketing thing is you say, hey, you got this for fun, but you can do some science with it. Okay, so let's look at case 2. Yes. Oh, this is it's my 11-inch row Ackerman back before my property burned up. Okay, this is the scope that the students used. This was in the we did this project in the summer of 2020. And then the wildfires happened in September. So but we got the project done just in time. This was done in, I think, July. And so at any rate, okay, so here we are back with our star and its aperture and its annulus, and we split it into red, green, blue, and we're basically interpolating. We go to this. We to get the red, the green, and the blue stacked for those things, we interpolate from the adjacent pixels. Okay. So this gives us a nice, right? I mean, if you just said, well, just look at the red. Okay, so the star image is sitting here. You're not sampling it properly, right? You've got, if the star is landing in this particular area, you're going to have much too much red. This does not solve that problem entirely, but it gives you at least a first approximation. So then you just conventionally extract the tricolor red, tricolor green, tricolor blue out of those interpolated images. Now you're back to the same problem you've had before. And this is now bringing us up to date as to where we are now in investigating this with our smart telescope work group. Right, so we're going to have the blue stars have a brightness curve that is very high in the B and then drops down, and the red stars are going to be very low in the blue and they're going to rise.
Before you change,
Yeah,
what's that little red thing right at 4,500?
that's the red leak. Oh, the other thing this doesn't show, and it should. Okay, here at about 6,800 angstroms, your DSLR camera that Sony sells to you or Nikon sells to you has a filter that cuts off all the light longer than about 6,500. Okay, and when you buy a modified one, they've actually modified that cutoff filter to let the H-alpha line through. Okay, so you can take pictures of the pretty nebulous. So your green Bayer filter comes up again. Your red filter probably sort of rolls up here, and blue filters are particularly perverse, and they often have more light coming through in the infrared than they do in the blue. Okay, so you have a nice chop off filter here, and it cuts that out. So if you're using a smart telescope, you want to make sure you have a infrared rejection filter in the optical train. Well, most of these telescopes can also, like the C-Star, you can point it around the landscape and take pictures. Well, if you take pictures with this type of filter system with those infrared leaks, you discover you have orange trees, right? Because now you're taking pictures with as much light from the chlorophyll as you have from the green reflection from the leaves. Okay, so you end up taking infrared pictures. So all of your digital cameras have that. Well, if C-Star has, because it can do this, you're throwing away photons, right? And it's astronomy. You'd really like to keep every photon you can. But if you keep the infrared photons, it becomes problematic. One of the interesting side effects that happens, by the way, is you take pictures of galaxies and you have these big infrared leaks. Galaxies have very subtle colors. And if you just throw a big infrared contributions, the same in the red, the green, and the blue, the color disappears in the galaxies. But if you cut off that, you end up with slightly yellowish cores and slightly bluish spiral arms, looking the way we want them to look. Okay, so we've taken images. Paper was written back in 2012, investigating what could be done with consumer grade DSLRs. Said, oh, if we have enough stars, we can actually not have 10 or 12 stars. We can have a lot of stars. We can have maybe a few hundred stars, right? Because the DSLR is taking a fairly big swath of sky. And so all you have to do is to line these up, each of the unknown stars, the red, green, blues, against the standard known magnitudes. And AVSO did a big project called APAS, where they photometered the entire sky down to 16th magnitude. with standard red, green, blue, and now they're also using a couple other bands that professional astronomers use called Sloan from the Sloan Digital Sky Survey. And you can solve these big, horrible matrices, and you can come up with the conversion values to convert these. So this is just to show you, okay, at this scale, you can probably just see, those who are close by, you can see the Bayer pattern of the red, green, blue. If you stack up, if you calibrate it, most of the color disappears. And then this is actually a color picture. It doesn't look like a color picture because most straight color pictures of the sky don't have very much color in them. And the stars are saturated, so you wouldn't see them.
That one red star to the left of
That's probably a hot pixel.
that's a pixel.
It could be a hot pixel. Okay, remember, somewhere out here, there's going to be remember that if the pixel out here has a value of 30,000 or it's saturated because it's a bad boy, it shouldn't be on the array. He's going to come through the interpolation process and pop up over here as a red spot.
Yeah, because there's a rod in that star, so that red star is.
Yeah, when you start playing with, well, I mean, you've worked with CCDs, you know they have hot pixels. And one of the nice things about CMOS is actually really pretty good nowadays. You can, a lot of CMOS chips have, you know, in 20 megapixels, you got maybe 10,000 hot pixels. It's now just, okay, so in a test that we did recently, this is a picture taken with the Celestron Origin. You recognize the Deerlick group, probably. And we did an extraction from that. Now this now has details for every single star in the entire image. Okay, we just looked at them all. Okay, so this is a 30-second exposure. And here's what we get. If we look at all the stars and we compare them, the instrumental magnitude versus the APAS magnitude, right? These should match up, and they don't. That's because of saturation we're coming into here. So if we say, okay, let's look at the stars that have no saturation, we have a slope of 0.975. It's a 1-to-1 match, very close. And then if we come over here and we compute what the transformation would be, knowing the blue, and remember we also have the blue stuff, we can say, oh, it looks like that equation could be applied to this to correct for those, and we could get a hopefully reasonably accurate blue magnitude, a reasonably accurate red magnitude, and a damn good blue visual magnitude, green. So that's where we currently stand. This software that generated this is a month old. The software, those of you who know Dave Rowe know that his program called PlateSolve will also extract magnitudes. This is what I used, but we now developed another set of software to PlateSolve the raw data. This is the kind of thing we think we may be looking at for doing science. And this is actually very similar to the model that Unistellar has developed for their science-oriented programs. The observer creates a list or gets a list of objects to look at. And these would be things that have turned out to be photometrically interesting, but not something that surveys well, you know, for the cloudy nights or whatnot. You upload this list into your smart telescope. Right now, one of the things that smart telescopes don't do is allow you to upload external lists. They have like 70,000 objects but they're not my objects. I want by objects.
Hmm.
You know, a couple hundred would be fine with me. I don't need to have every NGC object in the sky. Smart telescope takes the images at the specified times because you can set up a shooting schedule, put the telescope out as soon as it's dark, and say, okay, here's my shooting schedule. And right now their software does not make it easy, but it can be done. And then you just let the telescope run all night long, and it shuts down the first time it gets too cloudy. So if you have intermittent clouds, it's going to shut down and leave you in the lurch, but won't turn back on again and say, I'm going to try again every hour. These are the things that beta testers say. If it shuts down, it's got to try again in an hour. You know, please do this because I don't want to lose, you know, because one cloud went over. Yeah. I mean, there's always that one cloud, right?
Always.
It comes in, it stops things. Okay.
It just occurs to me that an all sky camera coupled to this thing could put a little smarts to that, right?
Yes. I mean, there's lots of things you can imagine.
Mm-hmm.
Okay, now you're talking about commercial companies that, you know, they're still selling telescopes that make pretty pictures.
Mm-hmm.
But okay, so the smart telescope takes the images. It subtracts the flux of every star in the images. It uploads now just not a 13 megabyte image, but a 13 kilobyte list of stars. Zoop, up it goes. The server that we would potentially have solves the big matrix of standard stars versus the raw magnitude. So it's got to do an identification off of the current best list of known magnitudes. It figures out what those conversion factors are and comes back with the standard magnitudes. Those are then saved in some master database, which might include the magnitudes of every star in the image that was captured that night, or it might compile them. I mean, now you have a lot of data on a lot of stars. Then that goes into the master database, and now you know you have an accurate magnitude for one star, or potentially for all 1,000 stars in the image. So that's where the future might be in, say, a year or so. And we're at a pretty early stage on that. So it's very interesting when you begin to, oh, the other thing is, because the smart telescopes are manufactured and they're all the same, once you know one smart telescope, you know all smart telescopes of that manufacturer fairly closely. So you can really characterize the performance of these things. The other thing is that if you're getting regular input of data from my smart telescope, you know very accurately the transformation coefficients that my telescope has because you've seen 10 objects a night for the last 200 nights. So you know my system inside out. Please don't clean your telescope, just let it get dirty. We can model out the dirt, but if you change something, there's a jog in the data, right? You want reliable long-term performance. The other thing is that those transformation coefficients, that if they turn out to be stable, will become very stable over time because you will have run 1 million stars through those solutions. And you're going to really, really know that. Again, don't clean the optics, leave them dirty, right? And of course, the atmosphere gets, the atmosphere solution for the atmospheric extinction and stuff like that all comes out of that too, because you have this big matrix, but you got 700 input values going into it. Well, 400 if you throw away the ones that were saturated. And you probably can also begin to, because you know fairly reliably the performance in saturated stars, you can model that too potentially. Once again, throwing away the traditional methods and saying, wait a minute, when you've got a lot of data and you can solve that, you know, you've got a lot of data. You can really begin to play with that. So questions? Yes.
Well, this isn't a question, but it gave me an idea to make a smart telescope that had filters and a monochrome.
Yep. Celestron, okay, right now they have a Bayer filter in there. They will probably sell a monochrome camera that can go in there because it'll basically get a magnitude or so fainter. And for people who don't want to take free pictures of red nebulas and stuff all the time, but who want to do things like follow satellites. And this little guy can probably follow satellites, although I haven't tried it yet.
But I was kind of thinking of like make it a smart telescope so it automatically indexes the filters in, and you can still look in your cell phone and see a nice color image if you do RGB, but if you do UPVR or whatever,
yeah,
then it's expensive. Yeah, it'd be a lot more expensive, and you'd probably want to make it 12 inch or something out of it.
Yeah, yeah. I mean, here's the thing about smart telescopes. They're very scalable. There's nothing about the smart telescope in a 6-inch aperture, or for that matter, the C-Star at a 2-inch. If ZWO does not come out with a larger than 2-inch smart telescope, you know, they're missing a big opportunity. They have the mounts. They have the you know, telescopes they can outsource. They have the software. The software is getting beat on by hundreds of customers all the time, thousands of customers all the time. So they're really debugging it. Same thing goes for Celestron. I mean, they make the optical system in the now 6-inch size, but also 8, 11, 14-inch size. Yeah, I mean, this stuff is very scalable.
14-inch origin. Wow.
It could be. I mean, it would cost a lot.
Yeah.
On the other hand, there's a market in the educational world. And in the educational world, if you have a good project and you write a grant, there's a level at which the cost of hiring people to do jobs is more expensive than the hardware that they're going to use. And so you can write a grant asking for a $20,000 telescope because you still have to hire the assistant who's going to keep the observatory clean and running, and that's going to be 40 to 60,000 a year minimum. Or you're going to pay us, you know, a grad student to do it for less. But yeah, I mean, the telescope at these kind of scales becomes less expensive than the cost of operating it. And I mean, I'm sure that's what's driving the large educational sales of plane wave telescopes, right? I mean, they can write a grant, they can get the thing, and what is the 20-inch plane wave is pretty affordable if you can make a good case to the granting agency.
Oh, Russ just detailed that a little bit with the camera he was using for the speckle. Yeah. Hardware comes down.
The hardware cost begins to disappear at some point. Yeah.
Peanuts for that camera.
Yeah. Well, I mean, the Origin scope, which is not the most expensive available on the market now, is $39.95 or $39.99. And you can't put together probably an imaging rig for that much. Or let's put it this way,
Little.
that for that little, yes, it's too good a deal. Especially when you consider your target market is typically older than 40 or 45 years old. They're getting older. Adults older than 60, 65 are likely not to have a suburban backyard. But they are interested to be able to put the telescope out in a common area, in a housing, shared kind of thing.
Condo, retirement village.
Exactly.
Yeah.
And it's remarkably able to work in very light polluted environments. I mean, I live midway between Salem and Dallas. I can just barely see the Milky Way on a good night. And if you remember the picture I showed of the Andromeda Galaxy and the Central America chunk of the, people go out to dark sky sites to take pictures that good. I just said, oh, it looks like a pretty good night. I've got to be testing tonight anyway, so I'll do half an hour on this guy.
There's 4 channels. Yes, I have a question.
Yes.
You mentioned earlier that there's about 25,000 smart telescopes. That
EV scopes,
for EV
yeah.
scopes. And you said that just 1% of those people
Well,
to do science. Do you have a feel for how many people are doing science?
the best way to find out is actually to just go onto Unistellar's websites and drill down past the sales pitches and act like you're a person who owns one of the scopes and just go into those areas and find out what the projects can be. I mean, they're commercial outfits, so they're not going to really tell you the real numbers. But I mean, 1% is probably a conservative estimate. All you have to do is to look at how many people are observing exoplanet transits using the unistellar scopes. And that will give you some feel. And
So people are doing this.
yeah, lots of people actually. And the other thing is Unistellar got a grant, forgotten which foundation gave them money, but the guy who teaches astronomy at Chumacata Community College, they gave him one for free. The only stipulation is that he has to use it in classes, and he has to produce something like 3 sets of data that they send in, that he sends to them each year. And he's going to do that anyway for teaching his classes. And he can take that right out into that brightly lit parking lot and use it in the brightly lit parking lot with his glasses. So it's
a new age.
It's really different.
Wow. Okay, there's 4 comments.
Oh, there's comments online. Where's the chat? Let's unshare this. Where's the chat? Okay, chat. I'm not sure.
I think it says, why a smart scope become a big data scientist? That's from Mel.
Okay.
That sounds like something Mel would say.
Yeah.
And then from Cindy, are there amateur citizen science projects with the C-Star or just the Unistellar?
Right now, just the Unistellar. The C-Star, when you sign up for the C-Star, you also sign up for this community of C-star users. I haven't investigated it because um, uh, not all of those users speak English. And not all of those users, I mean, it's just another way to spend a lot of time, a lot of time messing around with other people who are looking at obvious things. The C-star has been used for doing science. There was at least in one of the one of the announcements for a nova that somebody had observed it. The nova was great because it was, relatively bright, and they had derived a right ascension declination coordinates from it. All of these things can be used for that kind of stuff. It could revolutionize teaching, certainly.
The smart scope distributed equals virtual application opportunities.
Yeah.
It's a mouthful.
Yep. And the right now, I think IOTA has a program where they're using fairly small. I don't think they're using commercial scope, but I think they're using something like 2-inch scopes and recording their stuff on videotape. And one of the big things that IOTA had always had problems with is timing. That's now internet timing, and that problem is solved. Everybody's, logged on to the nearest small number of milliseconds.
Mills, you have Mill fired up here. Smart scope in space, on the moon.
You can put it in. I mean, a good number of the big professional telescopes are essentially smart scopes. You run them from a computer screen and you get your data. The big thing is that they're always changing the instrumentation on the back.
You have to harden the electronics. Yeah, I mean, certainly. Really harden
right.
Yes, yes, for space.
Or not, you just launch them into space and then they're gone. Problem solved.
Yeah, just if one fails, send up a new one. Yeah.
Hey, Richard, this is Joe in Squim. Can you hear me?
Yeah.
Yeah. Hey, how are you today? Did you do any thing with the Einstein experiment with the last eclipse or not? Did you get clouded out?
I was personally clouded out. The group that went to Mexico they had three perfect clear nights to get set up. The day of the eclipse, high cloud moved in. They got about quarter as many stars in the sky as they hoped to get, but they did get data. One of the 5 telescopes they had there was kicked over accidentally. And one of them was hit by a wind gust, and they couldn't get it back on the sun in time. But they got data out of 3 telescopes, and they are now analyzing that data.
Okay.
And they developed a really nice piece of software for doing the data analysis. They had a father-son team. The kid is the son is I think he's a senior at Cambridge University. Real smart programming kid, and they developed a Python application for plate solving, finding the stars, and doing the data analysis.
Did you experiment with anything with the occulting disk to block the bright inner corona?
You have enough dynamic range now in the C-star. I mean, in the
CMOS
images to get away with it now. So that was not necessary. They're still trying trying to get good data up real close to the sun.
Mhm.
Part of me says, you know, we know it works to microarcsecond levels in radio waves. I don't know why we're trying to do this in optical through an atmosphere. But it's
Because Eddington did it.
because Eddington did it, yeah. And I mean, we're doing better in Eddington. I shut an off. I was going to go to Texas. The people who went to Texas where I would have gone got clouded out. My wife and I got COVID just before, and so we did not go to Texas. So I got sniffled out or coughed out. But actually, the Sea Star went and they took some pictures of the eclipse with it. Not to do that, just to get pretty pictures of the sun.
Okay, good. Thought I would ask. Yep.
Yeah.
Okay, anyone else? Lunch. Oh,
Yeah, lunch.
Star API was reverse engineered and it's available for any kind of automation and data gathering project.
That's correct, actually.
And there's a link
Yep.
for more info. Thank you, Marcus.
Yes. Yeah, that is ongoing process. And a lot of their focus has been on doing mosaics. So what you do is you shoot a series of images in an expanding oval, and then stack them all. So you let the telescope happily run for 4 hours, taking a larger and larger field. And because you're plate solving, you know, you have an image that you're creating, and you just keep dropping pixels for the new positions onto it.
Just register perfectly because
It'll register perfectly because you know where the star, where that pixel came from. Exactly.
Okay. Wow. Okay. All right. Thank you very much. Okay. So this is our lunch break and I'm going to stop the recording. And we will see you back here at 2 o'clock. Today is a long lunch break. I think we're all going to take a little nap, actually. So we'll see you back here in a little bit.
Grab that guy. Yes.
Okay.
Enjoy your comfort. It's a privilege meeting you. Goodbye. You're Richard and Krach. Was Richard from the Krach and Barry book, right?
Yes.
Right.
Yes.
Wow, I can't believe it. I use that book to go my yes. Right. Was a problem for the
Right. I don't know what happens to them. I hope they send me. But yeah, yeah. Yeah, the transition. The band had changed. Okay, and so he fixed all the stuff that needed fixing. I mean, this is actually one of their other standard methods.
Yeah. Yeah, I mean. Interesting. That was. Of heating.
Yeah. Yeah. Yeah, but yeah, so you can see the these row acronyms are really sharp. You can operating them 1.2. Yeah, the area is very small. I mean, you can putting cameras at the focus of that then scope. Right, the area district that scope is about 9 months across. Now we have 2.5 months. Very long grossly overseen.
3. Yeah. Okay, well, the deal this with I don't know, that whoever Barbie, this is Barbie was in that. So somebody other than that absolutely cooking today. Fine. Okay. Okay. There's a chance we want all the hungry. We get all.
Yeah.
Goodbye. Did you volunteer?
Yeah, I did.
Okay, I'll help you, but not the, you know. I'm technical.
Yeah. So, finish what we were saying, so this one now has 2 micron pixels.
That 2.6, yeah. So it would be about, yeah, it was in the table. It's
all this, the pixel and the areas are roughly matched.
Yeah.
Better than the other ones.
Yeah, I mean, there's some aberrations, the usual thing. But the row acronyms are really good. Scarily good, the 11-inch of it. Very slightly smaller stars. Biggest problem with the early row acronym, was the focus mechanism. They fixed that now. This seems this is all things. Yeah, I mean, it's a fun.
It's fair enough.
Yeah. I mean, if I turn it on, it will be confused because it thinks it's too bright. No. There were for about 8. Oh, and there also has a new meter privilege. Well, it's so let's try to get years to figure out they put it usually necessary. You know, usually imagine a person will lose the product.
Yeah.
Just, it's everyone. That's it does really- Yeah. Yeah. It's fine. But Ed's gonna schedule. So this is an easy way to build a schedule. Oh, there you go. Yeah. Yeah. Okay. Yeah. Oh, very yeah. Near the capability of how do you like use?
Easily. I think experts who can do that. Yes. At this point, you're doing something to do the next step. Yeah. Yep, it doesn't know what to do next year. We'll get that to fix all. Oh, yeah. What do you mean by nearby? Like, oh, yeah. One person. Yeah. No, I mean, there's no. There. I knew I forgot something. Thank you.
So I'm so sad that we are going to miss the time of your job. Okay.
You'll recognize it.
Can you take this to the next one?
There's a function here for you to download. Okay. Well, apparently it's now. Well, yeah. Yeah. And if I want to. Yeah. That's what the news color. It's called this is the control. I mean, that's what the yeah. Does this have any column? Is it so rugged that you can't follow? I have not finished the article. Well, of course not. But I don't see any place where you can even access that, so it must be built. The answer is I don't know. No, you have to take off computers, get to the primary error. There isn't any secondary error. It's got, yeah. But if you take off the camera, it's probably screws for adjusting that's going to be so solid. After you finish
yeah, well, thank you for using it online.
Okay,
But
thank
I
you.
just didn't want you to, like, you know, all of a sudden, like, they're not. They're going to go.
You deserted me. Yeah. You can look it up.
That's.
No, I had Stephanie last week that they even like what is your seeing pictures of N13 every time you go out and look at N13. This is where right, right. You have clearly the agency smart so keep it real instead of it just being, because I mean you talk about like, hey man, we can't just do this. Before maybe somebody doing this, I don't know. Before it's also M13, it knows what the M13 and then it goes down with the best picture of M13. There you go. You know, what have you got? Yeah. Yeah, but really is so interesting, even without the science. Look at the time over 2 hours of the night, it's much very that's of course right. Oh, okay. Because one software is used. Oh, you don't know. What else is you don't know? Is that a Chinese name? Yeah, no, it's a Chinese. The initials of the name. Oh, okay. Okay, okay. You know, yeah, okay. Yeah, so you're using their software to do your process. Well, their software processing is doing. Okay. And then you get those unique files, dark and flat. Then so they use my list of 250 versions is now all the clothing lines transactions. I found that very similar. What's this? Oh, yeah. But you would think it more strong. And it cracks pretty well. And you see, it's very pretty sad. The new I mean, this is when the alphabets. Where's it all? That's surprised. Doing that with this small. Yeah. Well, as well, I mean, think about that. Big screen TV here, that they show people, on your feet. Yeah. This one, and Oh. Well, is this a, this is a color sense. Oh, yeah. Oh. Yeah, this is the last thickness is the focus.
Don't you start?
Oh, wow. Wow.
No, he just, all of it. I just watched. There's, a little more. Oh, thank you. Yeah. Walking you couldn't make me hungry. It's just a problem. Yeah, so. I really want to try to. It's like a bolt on kit. Bolt on to any other scope. It's some sort of. If you have any old scope. Yeah. You have like a go-to scope with a camera that leverage their software development. So it's self-aligning. Oh yeah, yeah. What I'm saying, if you can make it, they can still work from your phone. Oh, that's great. Automatically. Yeah, but process the images up locally, images. Oh, that's. Yeah, the amount of time where you're not doing your own stuff. But you could, real photographer that is real photography. Yeah. We've been happy to say this is starting to get news about. Oh, we 101. Doing 60 we use those for the effects, but we use experience. And that's not smart.
No. they're using, if you use a whole message to line up to do the current part.
Oh, you're on that guy.
Yes.
St. John Bridge is talking about a very similar telescope.
Yeah.
It's a wonderful thing, but it's not neat. It's not. Smart scopes.
Oh, yeah.
Right? You just got them. I just freaking built this thing. I'm gonna use it. But it's really the kind of experience that I want to have. It's still very much on the right. Yeah.
That's why we have one.
And also, you know, very encouraged to do some more stretching.
Yeah.
I'm worried that well, I've done some of this. I haven't been when you're going up to the top, especially the sun and the moon.
Look at that.
But then after a while,
Codes on real estate, I think that happened Monday, and then,
working.
don't catch some of the parts in
You're
here.
like the leader.
A little closer at our unistellar app, so that.
When are you gonna close, tomorrow or a week from tomorrow? Tomorrow. So you won't be there.
Yeah. A little more variety.
Then we're gonna go
Yeah.
fix some of the pieces and figure out what I want.
You haven't seen solar?
Yeah, we have an EV scope too. I got it because, well, I was waiting for one that had the eyepiece again. So with the EV scope too. I said, okay, I already wanted that. It's partly because.
Variable fix.
I think you just need to go grab and go, like, or grab and go and even pretend it's.
This one,
Just
generator.
sometimes it's
Get the
just,
water. Yeah. You know.
you know, like when you get to the
Those
campground,
run-
you're too tired to send
very
it up. But
But the.
when we were camping last weekend,
blades
at
don't
least we
have
were
any
talking into setting
curve
up
to it.
this
They have
stuff.
So,
Because it was like, you know, it's like,
very.
come on, you know, surely this would be better.
So you pick it up and you carry it out, so flop down.
Yeah, but his first choice, like the scope that he wanted to take to OSP was the 16 scope that he built, you know, so I mean, it's like two ends of the spectrum to have both. And you wanna have a little table space here?
Yeah, it's such a great feelings and it never goes away. Never goes away.
So far, the only telescope I've actually had to fly, there was two. I got my C8 when I worked there. And then the hydrogen alpha telescope. Absolutely everything else is made.
No. Buy anything you want. I found one YouTube video about observatories. Yeah, on YouTube. And, yeah, I just searched for, amateur observatories. And then it's your video, it was like an hour and a half or something long. And it went through all the different observatories we've got. And now the different culture. It was you. It was definitely you. Unless there's a different Richard Berry who looks just like you. If I can find it again, sure, yeah, I will. I've forgotten that I need it. But there's but the best part about it, for James, and these are the things I've learned that you have to do and things that you should. Oh, okay, now here's the pearl of this.
Yeah, why the heck are you reading that? Are you gonna build yourself an observatory?
That's a perfect spot. Yeah.
What was the problem?
The big scope. Big.
If you like a little roof, you can flatten it.
But the thing that I remember the most surprising is that you should leave the eaves for the roll-off roof is open, so air can circulate.
Oh, yeah.
Because you don't want condensation building up. Bugs are gonna come in, but they can also go out. And to have, for the roofing material, use that semi-transparent, or what's the folio tape, part of that material. So when you walk in, it's not perfectly dark. You don't have to put a light.
Bugs do not like.
Oh, right. It's all coming back.
How do you let come in? What light come in?
Yeah. To get right inside. The only problem I ever had with chili.
This is really good video. We had one observatory this city. Over the top of it. Yeah. They roll the top of it.
That's called the takeoff roof.
Yeah, roll it up.
I named that. That's what I did with Cal Poly.
Oh, you did? Oh, okay.
From Richard. I needed to prove something, really, I mean, it's a really long story. It was a lawsuit. And they were blaming my software, so I shipped a Cal Poly scope and proved it wasn't our software. Remember that, Richard?
Yeah.
And I made it take off the that you buy for picnics.
The chicken is a little bit complicated.
Oh, sure.
Yeah.
Can you test?
I was in diameter limestone sundial with removable gnome the garage door. So it's coming out of the garage door. What's my observatory?
But the SQA, or probably call it.
That little
Like that, so.
4 by 8 foot roll off building. That used to have, later became the building for the 2017 solar eclipse.
All the telescope.
Yeah. So it's now at my new place. And it's got an ADX mount. So I'm not sure what scope I'm going to be using.
Are you refreshing your mind on your thought? You're not a problem, huh?
It was out in the observatory itself in the little roll-up shed. The alpacas all showed in the theater.
Hey, by the way, in fact, Samantha was asking about your alpacas, and I said I didn't know.
You really want one. Friend of ours,
Yeah, there, yeah, see?
Their company.
don't get a chance to chat people.
You're leaving?
Not
Been there for about a year.
Oh, God. No, I'm not gonna tell that. I thought.
So I just wanted to.
See you next year or any other time.
Actually, okay.
Yeah.
The
Other thing that brings you to
Okay.
Yeah.
Far away. Natural.
Yeah.
And you look to each side.
The fire is through.
There's
We changed the mountain. To the mountain, and I said, oh, down in the valley, there's only sheep. Really small, very evident.
And that, remember.
Right, right. What town do you actually live in? Is it Dallas? It is. Yeah.
Well, I mean, we can visit, so.
Yeah.
Yeah.
Yeah, I'll be leaving. Okay. From the same direction. Okay.
You can pull up a chair if you want. You want the end or the side?
Horizon.
Have side of the side of the table. So we could end up going for a walk.
Actually, yeah, just a little walk down. That's what that. President, there was much to see.
Oh, no.
Direction you go out of it, both ways, red house, 80 yards or something about the area. But you can't get in there, so.
Well, it wasn't about
So,
swimming, I guess.
Yeah.
I mean,
So.
if you had wanted something more scenic.
I should get started shopping for. There's a
Remember
bunch
that
of things. Set up for one.
Went to the walk at one time? Yeah.
I think you can have.
If you wanted to. We could just one.
It's getting dark, so.
Yeah,
Yeah. So it's.
but there's a.
Yeah, that's all I found, no.
There's no-
Including
There's a waterfront
$50.
There's like a
electronic
Yeah.
waterfront that you can get to.
used from
the,
Adorama.
It borders the river, you know, and then that would have been nice, like a little more scenic.
Yeah. Star City.
So you're gonna take that off of there and put it on something else.
So that's it. I'm gonna
But
use
we
the
used to go
Raspberry
on
Pi to
Scenic
see
roads.
the thing on
They
the.
would pick different places.
Right, yeah.
Permits to just kind of think of
It's just nonsense to me to.
And that's what.
Like.
So you can
Well,
see along
so
the water.
we're using this thing called Sky Sol. You know, you see. Yeah, and it's just, it's great when it works. I just love it, but it doesn't
The
work
time we were there, they were.
enough to make me happy.
Look at this.
So, like, you know, I'm sitting there eating night, and I just upgraded software too. It's like it's solving every half a second. I'm like, this is awesome. It's just about real time. And I'm getting over to Andromeda, and I'm still about an eyepiece field away, and then it just stops.
Yeah, I remember of Seattle.
It's like, it's giving me errors, like, nope, can't solve, can't solve, can't solve. I'm like, what's the difference? And so I find Andromeda, look at it, and then I swing back a few degrees and it starts solving it again.
Oh,
It's
yeah.
like, what about that piece of sky don't you like?
They bought a property, right? Yeah, near Golden.
Well, it's always any topic.
Right. Got it.
The new. That essay.
Yeah.
Yeah. Yeah, someone
What's the latest on that?
I grabbed an image from. I know, and around the center, not center, and they did sent that over to Dale.
They were much to buy it.
How do I solve this? And he's like,
They already
"Oh,
bought it and they were
okay, that's
getting
good.
machinery
So,
there to level up.
How do I know what settings
to travel?
use? Are there a different set of settings for light pollution and dark sky? Are there a different set of settings for when?
This
I mean, is
year.
it part of the sky?
Yeah.
Is it part of the sky?
But, you know, because
How
I
do I
worked.
know? There's the user manual ones. Yeah.
But it was not.
And he's like, well, those are all good questions.
Yeah.
Never had my work.
It was.
So he only uses it from one
No,
place.
it ended up not.
One place, yep.
Not
And
being.
but he never has to do it. He just stops thousands and thousands of dollars. Yeah. And that's you there. Yeah, that's everyone who's bought one from me has had probably this looking to buy jointly. Which is why, I don't know if you saw Lauren's presentation yesterday. So all these,
It would have been.
she talks on all of these
Wasn't it, isn't it?
little upgrades. in
Because
terms
it was
of
like
finish,
50, maximum 50 and just.
and one of the last ones she talked about.
Seattle.
You know, Sky Safari.
And it, you know, a lot of those grandfathers, names.
So that when she
they
moved
put
the
them
scope
all
around,
at risk.
the Sky Safari would
Right.
show exactly.
So
what
our
that
club,
was.
RCA,
After she did it, she started.
Parcel in Central Oregon.
And it was like, Rob and I were going,
Used to ban-
well, that's what we have.
Yeah.
That's all we need, that's all we need. You know, we don't need to have
We haven't made
plate
it
solving.
yet.
But it was expected for two.
If it works every time.
The property belonged to, like,
Yeah.
real city, you know, members, you know?
It was a couple that first discovered the location where OSP is.
Right.
They that way over my head. So, yeah. It was in southern. Yeah, that's right. Yep. And the strong, I turned on this location and protocols. So that's when the stars. Exactly, right, right.
But they wanted that property to stay with astronomy. So it's like. Name proper, that was their.
Yeah.
To a non-profit, so they wrote city astronomers, and that really did.
And there was a couple in the. Don't want to carry a laptop.
There's a red.
Yes, it has, I think, the biggest airport in Central Oregon. And he has become the club, telling the manager, caretaker, out for the house, because he's so close. And he can work remotely, so he can, you know, have his time.
Oh, yeah, poor me.
No, no way.
His dream job.
Yep.
Well, they're probably using more of the tape. Well, sure. No, they're using the rest of the tape.
They're doing some of the things to figure out if it is, they're probably. Have a few areas smooth enough and clear enough to camp on. Started thinking it's,
Okay.
But one of the issues with that culvert, and they were talking about on the Seattle, the property that goes to Seattle.
yeah, something about a wet, not a seasonal wetland or something that they were having to deal with.
That's bad. I hope they don't have a lot of dog.
Well, it's dry, a lot of the year.
Okay.
We didn't expect to be but you have inside tracks if you to go to that.
I actually, no, I'll mention that we're affiliated with my, I made a few friends at, Washington Square Party. They had their private, a lot of land. Reasonable.
Yep.
So I basically told me I could go there.
It's just a little bit.
Another thing is,
The people that don't be on, if they let me know that, I can just go there.
That's nice to meet up.
Yeah.
Be the first thing out the door.
They're really great people, yeah. One is Jack Day. I think he co-chaired the one who's start party. I don't know, he's pretty nice. So he lets me use the property. I think I'm going back in late September.
I mean,
3.5.
about the same as the Star Park fund.
Yeah. Yeah, it's like half an hour from Thursday, so like house.
Because it doesn't say that, well, sometimes it says.
They're actually starting to build that amenity. They have an actual bathroom. Yeah, well, they're what do they do for volleyball? For the company that sold the property from the meadow. They have there like this area where you can fill with water or there's right.
But the drawback to that is it has to be ingrained. So the bathrooms aren't functional, it's freezing weather. But if you're in a motorhome or trailer,
Yeah.
self-contained, it's still an easy thing.
Now this property, they're trying to leave it more this that way you can also say
In places with scopes like mountain.
Yeah. There, yeah. I don't think she
Got my talk queued up, all right? Yeah, well, good. What is this? So this, I'm actually building for that big old reset there.
Oh, that's what you were talking about yesterday.
Yep.
This is it.
Yep.
Okay.
So it's a Arduino with a three axis accelerometer. And it measures gravity and it's going to compute hour angle and declination.
Yeah.
It has to be an equatorial mount.
Yes.
It's properly aligned. That doesn't work at the North Pole. It doesn't work at the equator.
Well, we won't go there. Uh,
Yeah. Yeah, they're able to have wells and septic. Basically.
So it sounds like three house, kind of like. They just be driving that far.
So, see, the other thing ends up being, well, that's because there's something compatibility.
Howard, we're starting at 2.
2.
I have 2.
Many. M42.
I brought a Mac.
This is the 47.
That's Bay. No, I already bought the iPhone.
So January.
Right, and then now it's this side it's a Mac. I think I have time to go on a week though. Best Buy.
I know, but which is.
You can take some beacons.
I think so, yeah.
That's just right down the street.
I think I can go pick it up and be back by 2.
Right. But it'll be easy and quick. It'll be.
Okay, let me do that.
Okay.
See you guys in a bit.
In the long run, so. And they're they're very responsive.
That's good.
I have never found this as big as that. As opposed to something different.
Right.
That they get out of gas. People with it. And then choose anything. So.
What screen is?
Right here.
Hey, it's scrolling.
So that reads gravity vector. It's reading gravity. So X, Y, Z. So the Z, Z should be -1. And the others two should be close to 0. Are there programmers located in Torrance? That's gonna help me point the big anti-retractor. Sorry. Put that on a equatorial mount that's properly aligned. Calculate our angle of declination of the gravity vector. Wow. And then have the little clicky dot on the sky safari or whatever. So for the telescope, it's going to be in New York City. We can't see the stars anyway. This is going to be better than GPS. Well, you know where you are, right? So it's not that. You need to know the time to go from our angle to that to the right section. But that's not hard. Anyway, I'm just trying to get something to find her. When you go into the factor, yes. 7,000 pounds of telescope.
7 houses.
So you didn't call it any picture? No, I rented a truck.
It's like you could have an elephant or you could have a telescope.
Very impressive telescope. It's a beautiful piece of industrial art. The optics are great. We're sheer lengths from 1895. I'm in Ecuador right now. That's what I did. Yeah, they knew what they were doing. They knew how to test. That was a key. Never here had H-state with the calculus. So they put forward design. They knew how to do it. They wanted to do everything on here. But they knew how, they knew what to do. Many pages. Oh. Friends again. And I said, you know what? In my retirement, put some time into understanding of this. Just insidious go-to scope work. See if we can get you up and running. Because neither of them are very good at playing stuff. Right? And one of them is he was given the scope as a after his father-in-law died, I think just transferred to him and said that I'd really like to interview. So just a level of a time ever getting Starlink to work on the next star.
Do you think you can?
And the best thing that I could offer was first getting it on Wi-Fi so that we could do sky support. And the second was, well, you can do 2-star landing and reliable than anyone, but then it won't find anything. It'll be outside the field of view with 2-star landing. Pretty much, that's our experience.
I searched my inbox and I have emails from 2012.
Yeah, use the hand paddle control to do 2-star landing. Yeah, but then
Well, they had that, they had that. How old is this stuff?
They're probably, you know, they're 15.
Oh, okay.
They're not new.
No,
Yeah.
okay. If you get an AVX today, you could really, you do huge star alignment, and then it says you want to the
Yeah.
yeah. And it does some kind of thing, and it figures out the phone errors, you know, all this stuff. And the pointing is accurate to. Yeah.
But you might explain this text.
So I did, and that capability is actually there in these. If you use the Sky Safari app to do the star alignment, it will do that. It'll allow you to add stars, and I've on very rarely gotten that to work, but very rarely. And it's like, what is it about this stupid thing that doesn't work every time? What am I missing? And I get online, I try to find out. And the instructions are so vague, and I don't know. There's some.
Have you, okay, you're using the standard name.
Well, unless I'm using the Sky Safari app to do the alignment, which you don't do.
No, but I mean, is the firmware in the one dollar up to date?
Yes, because I need sure.
Okay.
Mhm.
Well, I mean, don't use 15-year-old. So
No, I updated the firmware first thing, yeah.
I can't think of any, I mean.
Well, I'm not asking you to, I know there's no reason it shouldn't work.
Hardest writing is technical writing. And the worst part of that is it's a good user.
Yes.
Clear and useful.
Yep, yep.
That's
And
the hardest.
I have no idea what I'm doing wrong. And I've gotten to the point where I just feel like, no, this Celestron stuff doesn't work. I'm really happy this works so well.
Yes.
I'm kind of surprised after this summer.
Your manual is 15 pages long, it's not complete, but it's anything to do it.
Well, if it's 15 pages long, that's about an order of magnitude more effort they put into that one than they did on the next one.
Well, this is a cool stuff that's being sold to people who have their own results, right?
Yeah. As was the next one originally marketed.
But also companies, all their feedback comes from people who make That's probably why I do better finding things in data testing. The people who experience know how it's supposed to work, and what it can do, and you don't push it. And I'm going like, yeah, it's a real pain in the neck to enter hours into this thing, because when it comes up, it's got, it's got views and it's second parts, and you need refills or not. And what kind of thing is to do if you just like 11 space, 13 space, 22. So do that at once. And do it up. Other ones use okay. Christian, do you know that the space bar moves the cursor back and forth on most input things? Yes. When you're trying to place a space, the cursor precisely, you're going like one keep back fingers. Space bar moves the cursor. You can you go like, okay, 11. I'm gonna keep that 2. And then backspace over the 11. Put in but you can do that because you can control. And okay, understanding keyboard lyrics.
You're right. Yeah.
And this is not. Right. This is the little detail. that-
I already did the restroom actually, so, yeah, good things for their hands.
We're just supposed to replenish it and there's some. So you're saying you did not pick the last one? Yeah. If you do the last one, then you're in trouble. Well, because the sign said.
No, I mean, how come Unistone came up on my phone?
What do you mean came up on your phone?
I just opened the screen and it was on Unistone.
I don't know, I was logged in looking at that sign, it's down. Oh, because I was looking at it, but you can click from those 5 things, like you can say, hey, tonight, are there any comments that I can see? You can click on comments and it'll tell you which ones, and then there's a link, and you can hit the link. And yes. Right.
How many more minutes do I have?
9.5.
Are you serious?
Yeah, 2 o'clock is when I'm supposed to start.
Oh, there's one more break, isn't there? A 10-minute break. No.
That's right.
See how Howard, how hard would it be to like this? I don't know that we would be able to connect with the same recording. Oh. There may be a way. I have no idea what it is. I'll try to put it on thumb drive, but I sent you an email and I'm hoping that you can load it up before I talk. Yeah, we can do it right now. We have time. No.
This is the fastest way to generate almost cost-free electricity for life. What if the ground you walk on could easily power your entire home endlessly?
Yeah.
Rediscovered.
Yeah, oh yeah. YouTube ads are the worst. They're just the worst. I have no idea what this is going to work. Oh, geez. So yesterday, we set, I think it was a new record for attendance at one of these. Oh, personally, in person and online. We've had about 15 people here. There was about 15 people on Zoom. And I was told there's at least 20 people watching the YouTube live stream. So, top 100. Wow. Yeah, that's like double what we used to get out in person.
It's interesting. It feels real sparse.
Yeah, because we're all split up in
Right.
different domains here. Yeah.
The AVSO has been running into a problem with the annual meeting, which has been traditionally held in a hotel and stuff like that. And by the time you count on, okay, the problem with being president of something is you have to deal with the budget. Okay, and when it's significant staff time, unbelievably expensive.
Oh, yeah.
So, I mean, we're looking at $100,000 to put on the meeting, which typically 50 people come to. Well, wait a minute, there's a disconnect here.
Yeah. That's a lot of money per person.
Yes, that's exactly. I pointed everybody at this meeting and said, hey, you really ought to look at meetings like this, informal, local, small, and have like an organized committee of, Howard and Mel to put it on and have it in a place where you don't have to pay for the rent. And, library will rent your room for $100, $150 all day long, something. And they'll have the AV equipment because it's a public library.
Yeah, good Wi-Fi.
And good Wi-Fi, or at least reasonable. And, put on meetings like this, and it's an uphill battle trying to convince people that informal meetings are very attractive to a lot of people.
Well, I would bet. I'm for sure. It's much more of a relaxing experience to give a presentation
Yeah,
in this setting than it would be in front of 100 people in an auditorium.
yeah, and it doesn't have to be on
So,
paper. It's just, I'm gonna talk about the work I've been doing.
oh, perfect. Yeah. So Dan, what's this? You had this highlighted in your email. Is this something you want? No. Okay. Yeah, I'll get rid of that.
This is just one attack on his computer.
You wanted Tracy's
Yeah,
YouTube?
yeah.
Okay. Yeah, because this first spec got highlighted. And that's a picture of Tracy. Oh, I don't know how that happened. Okay, all right. So we're good. All right. So, okay, who just left this on? Did Dan just leave this for me? He must have.
Yeah, Dan put that down. Yeah.
Workshop. And there's two files, and one's a video and one's a presentation. Okay. Nothing. There we go. 2024. All right. Yep. Okay. I can zoom. We're almost at 2 o'clock. Oh. So, Alan, do you want to say a few things before you bring up your presentation?
Yeah, just a few.
Okay. And you're familiar with using Zoom?
Yeah.
Okay.
Hey, we're 5 minutes late.
5 minutes late.
So 1:55. One, yeah, that's what love gems. Okay.
Yeah.
2.
So there's a 5-minute period where nothing happens.
It's like next to the black hole.
It's next to, yeah. So that's where that's the time I allow for running around here yelling at everyone. We're going to start. So we're going to start. Being 2 o'clock. Okay, here we go. On the dot. There we go. We do try to be punctual here because I know people are out there. They have schedules, want to watch live. Have to depend on the schedule. So, okay, right now it is Alan Silsky's turn. Oh, didn't I say that?
Oh, I think so. It doesn't matter.
Okay. Well, it's entirely possible. Yeah. All right. Anyway, so Alan is going to be talking, and just one thing I want to say is that about a week ago, we had a
a cancellation, major cancellation. Our speaker who was going to do the Peter Abraham's astronomical history talk had to cancel. There was just no way around it. And then we had this big hole. And then about 2-3 hours later, another presenter had to cancel, also for unavoidable reasons. And so suddenly there was 2 big holes in our agenda. Alan stepped up, and he's going to basically, this has become a 2-part of astronomical history. So we get to remember our good friend Peter Abrahams twice. So I'm very pleased with that. I'm going to turn this over to Alan, and there you go.
Thank you. Open up the presentation.
Okay, I'll do that. Excuse me. Let me get the screen shared. There we go. Millen. Share. Start that up. Full screen.
At the beginning slide.
Screen. Okay, there we go. It's working.
Okay. Excellent. Good afternoon or morning, depending on where you are. I'm going to talk about this telescope from 1895. It is a magnificent piece of industrial art made by Warner and Swasey. They were pioneers in mechanical engineering. And about the time this was made, about the time they started making telescopes, there was a transition from craft work to engineered designs in production. This represents an early aspect of engineered designs where we take it for granted today, but the idea that you make a drawing and you make the part to the drawing, not to the part that it fits, was very new. And our entire civilization today depends on this, but it's not really, doesn't really sink in. So this telescope is from 1895. A fellow named Macmillan, very interesting fellow you can look up, donated the money to buy the telescope and build the observatory at Ohio State University in Columbus, Ohio. This is an early picture with a vintage car. And the telescope was used a lot for spectroscopy, among other things. And they had a very elaborate spectrograph, but spectroscope. But this was still kind of early, and they would do visual spectroscopy. By 1976, the telescope was sadly in what I call the old junk phase, with the building actually rotting around it. When I was scanning these slides, I didn't quite know what I was looking at, but you could see holes in the roof. The wood slats for the roof are just rotting and falling in. It was rescued at that time, restored, and it took 10 years to find a new home, figure out a new home. Mr. Ballreich, who owns a potato chip company, donated money to build this observatory in Tiffin, Ohio, where it was used for quite a few years, and then, but for the last 10 years or so, sat unused as the club members died one after the other. So the reason this is all going on, I'm going to talk to you about, is there's a group in New York, mostly artists, but they one of their directors is a astrophysicist named Jan Levin, and she wanted a classic refractor experience for people visiting the site. So she had grown up
early college years using the 12-inch refractor, Alvin Clark refractor on the top of the Columbia building in New York City. And she wanted to replicate that experience. So this is a artist rendering. I think it's a pretty decent job, actually. A telescope in a dome and public lecture, after which one would look through the telescope. So you say, why on earth would you put an observatory in New York City where it's so bright? Well, it's where the people are. The most used telescope in the whole world is a 12-inch Zeiss refractor at Griffith Observatory in Los Angeles. 4 million people have looked through the telescope. So this will be kind of the equivalent experience, very bright, populated area, but with magnification, you dim the sky, and with aperture, you brighten the objects. And for many bright objects in the sky, it's really no problem at all to observe from New York. So this is a 12.5-inch. Can I move that?
Yeah, good luck. I've been drawing for 2 days.
We're going to have to live with it.
Okay, okay, that little screen will go away.
Just take the mouse down.
Okay, so Warner and Swayze made this telescope in 1895. It has a brochure objective.
Hit the little up arrow at the very bottom of screen sharing in the green bar. There, right there, that little carrot. Click that.
That's pretty good. Okay. So it was installed in Ohio State, 1895. And it was deteriorating. I would love to get rid of this
Can you
thing.
put it at the bottom? Yeah, you can move it to the bottom, but it'll just block things at the bottom. Yeah, but all his writing's at the top. Same with mine. All right. As far as it goes.
Yeah, it's not really a whole lot better. Oh, well, that's not too bad. So the when I left Ohio State in 1975, was rescued. It was cleaned and refurbished and put on display for 9 years, and then it left Fostoria in 1984. Was installed in this new observatory. It was operated by the Sandusky Valley amateur astronomers, used by undergrad students at Heidelberg. And then they dropped their astronomy program. And the telescope really hadn't been used. So the telescope had been refurbished, but time takes its toll, and the corrosion was starting to take over again. The paint was failing, and many of the bolts screws were brass, as you can see here, but many of them were steel. The bigger bolts you see here are socket head cap screws that didn't exist in 1895. So those are going to get replaced with bronze hardware. So we had to get this out of here. This is my son David that came with me to fetch this thing out of the dome. And I had restored one of these for myself, a 10-inch, some maybe 10 years ago. So I kind of knew these things and how they went together. It's surprisingly complicated for a manual telescope. You can see the control rods, the right ascension and declination, fine motion controls. They're concentric knobs. There's a tube and a rod inside, driven by these knobs. And the mechanism to get the motions from here at the operator all the way down and around the corner to drive the right ascension fine motion is quite complicated. So it's an example of a mechanical user interface. Today we move icons around on a screen, and back then you had to use gears and shafts and universal joints to move the user interface. But this is one of the big features of Warner Swayze telescopes, was a good user interface. This is the 12.5-inch lens. It's kind of interesting. It was a interesting design where it had a front element that came off easily. And it was intended that you would have two different front flint elements. And depending on whether you're doing visual or photographic work, you could switch the elements. This telescope never had the photographic element.
That's backwards from the usual.
Yes. So Hastings, that did the design of this, chose flint forward and was able to do the math longhand. So this is actually a very precise mechanism for locating the front element. You see the push-pull screws to do the collimation, and then this clamp arrangement to hold the front element on. So it's basically all there. It moves. The clock drive is stuck. And it had a guide scope on new brackets. And we want to make it a little closer to the original. So this is a period finder that a friend of mine had. He had collected, Hiptic telescope guy. You can see it has the little rings that allow the centering screws to adjust this without actually dinging the barrel. So the setting circles, it has coarse setting circles, you can see with the numbers, but it also has very fine engraved silver setting circles with verniers and magnifiers and illumination. So they actually have light bulbs and slip rings running through this thing. You can see two of the electrical slip rings in the center there. But it had all been painted over. So we started taking it apart, taking the fine motion controls off. The thing's all put together like a machine tool with tapered pins. So you need to punch a hammer and you've got to hit the right side so the pins come out instead of jamming in. You can see some of the gearing for the fine motion controls. The screws, the socket head cap screws had rusted to the point where the wrench didn't fit. Socket, or the Allen wrench didn't fit. So we had to basically hammer it into each screw. And also the screws that are holding the tube to the bronze rings, there's innumerable little brass screws, and some of those are in the way. So you have to take the brass screw out, hammer the Allen wrench in, take the bolt out, then put the brass screw in so you don't lose it. Made a crate for the lens to keep it out of harm's way. That's the focuser. The focuser weighs more than most telescopes today. Certainly,
brass.
it's all cast bronze. Yeah, that weighs more than the 6-inch Origin telescope. The worm gear needs a little attention. Water collects in that housing. For some reason, at that 130 years ago, they hadn't figured out they need to drill a drain hole. I think they were expecting more continuous attention be paid to the telescope. They weren't expecting it to just sit for 10 years unused. So you get condensing humidity on the big cast iron parts and it drips into there.
All that stuff has come in from outside, or is that the?
It's just condensing, you know, if you have a, like a cold spell, the telescope is cold, then you get a warm front that comes through. And the water condenses on the telescope and runs down, and it can run into that worm housing.
Itself rusting.
Hmm?
That's not the worm itself rusting, that's stuff that come down.
No, that's the worm.
Oh, okay. It is as bad as it looks.
It is.
Oh.
But you can see even this worm housing, we had talks the other day about trying to support the worm very close. The bearing should be close to the worm, and you can see to the lengths that they went to. That housing is all scooped out, and even down to the bronze bearing is scooped out a little bit for the worm wheel to clear. So we put a 12-foot ladder under the deck axle there, the counterweight shaft, just to hold it up while we took the counterweights off. The whole thing weighs about 7,000 pounds. And there are some sad stories about people that did not secure telescopes before removing parts. And we did not want to be a new chapter in that book. So we tied everything down very carefully. And again, taking out these screws. And then we got the first big piece off. And now it's top heavy because the other tube is still attached. But we had it pretty well tied. And then we lashed a 2x4 with ratchet straps to the side of the tube so we could turn it over without killing ourselves. Take the finder brackets off. These were pretty good, but they weren't the originals. These were made with a piece of brass tube and an aluminum base. And they weren't bad, but they weren't exactly what I wanted, so I have to make new ones. So now we got the rear tube section off, and we had to reach, this is my son David, had to reach in and disconnect the power so we didn't, when we picked it up, it wasn't the end of the world. And you could see the boom of the lift through the shutter opening there. And we're putting slings on the parts. This is the SkyTrack telehandler we used to lift the parts out. And it was no bigger than absolutely necessary. We were right at the limit. So that top section weighs about 2,200 pounds. And he did have enough reach to go up and over the slit. That's the midsection of the telescope here. That's about 1,900 pounds. And then finally, that's the base casting, which is surprisingly the lightest of the three. It's like 1,800 pounds. I rented a truck to drive from Ohio back to Waltham, Massachusetts, where I'm working on it. We were able to load the truck very easily with the telehandler. And this is at the other end of the journey in Waltham. I had a neighbor that came over with his forklift so we could get the parts inside. This is an interesting story. This is the original clock drive. It's a wind-up, weight-driven affair with a flyball governor. And this disappeared in 1975. And a very crude electric motor had been installed. And then a few years ago, mysteriously, this showed up at the physics department anonymously. Somebody was cleaning out their parents' basement.
Yeah. So that's
And
a hand crank?
it's a hand cranked. There's a drum with a cable on it, and the weight. There's a set of weights that goes down into the pier. And I've got to redo this, take it all apart, clean it.
How long does it run?
A couple hours. So there is the top of the telescope in its new workshop, which is crowded. I rent some space from a fellow that has a shop, and he tends to be a little bit of a hoarder. So tucking these telescope parts in amongst the stuff that's already there is it's a little tricky. So this is an interesting thing. When we took it apart, there's this piece which is wedge shaped, and there's a mating wedge under the next section of the pier casting. And there's bolts, you can run that thing back and forth, but only maybe half an inch. So this is like the micro adjuster for the polar angle.
Is that the azimuth?
This is the elevation. And you can see there's a little bronze brazing there. It's been broken off before. So this is starting to get into the parts that need to be refurbished. So this is that worm housing. And you can see the bolts, everything's a little rusty. That's the worm gear. It's actually coming out, which is a great sign. And this is what it looks like after getting a little attention and polishing. So that's the old.
It's so clean.
Sandblasting and polishing. The lower image is the entire worm shaft with the old rusty worm on it. It's 1.5 inch Acme 4th thread per inch. And I found stainless steel threaded rod, the same pitch. So I put the shaft in my lathe, got it perfectly centered, and removed the threads. Just turned it down. And then I cut a piece of that threaded rod and bored it to match and put it on with Loctite. And that'll be there for next 130 years. And this is the kind of thing you do over and over and over. When they Pioneer Works confirmed the deal to buy the telescope, they asked for bids to restore it. And they knew that I had restored one. And I was very ambivalent. I didn't really want to do it because I knew how many hours it would take. And so I gave them a slightly higher bid than I might have otherwise. But I was the only bidder. So I didn't bid high enough. So another example of these is the larger bolts above 1/4 inch use the same threads we do now, but the smaller ones are different. So it looks like a 1024 screw, but it's not. It's a 3/16 24. So they didn't have number thread sizes. They had like the fractional sizes kept going down. So it's like 7/16 31 or something stupid.
The good old days. Darn.
You just went to Joe the bolt maker and you said, give me some bolts. So we disassembled all the rings out of the end. This is the focuser end of the telescope tube. And it had not been disassembled since it was put together. So people tend to, it's much easier and quicker to paint the whole thing after you assemble it. Go right over all the bolts and everything. And it's quicker and easier, but it doesn't look good. So this is cast iron. It's not so bad, but this is the center section of the tube, which is a big cast iron part. It's about 350 pounds. You can see the declination axle. There's this very complicated gear system for translating those hand controls around the axis and running the declination fine motion. And it's surprisingly complicated. So these are annular concentric gear sets that have been split to be able to install them. And I would have complained if somebody asked me to make that, but they just did it. So you can see this concentric gear, and you can see the guys that painted it last time didn't even mask the bronze parts. They just could see overspray on everything. This is a forged steel axle. It's about 300 pounds worth. They just weren't messing around. That again, those are the bronze bearings for the declination drive. You can see that big concentric gear again, and a little bit of the worm gear there. That's the shaft out, that declination shaft out. My landlord has an old 16-inch South Bend lathe, which is just big enough to rotate, to spin these parts, to clean them up and polish them. So 3 of the 4 rings on the tubes are bronze. And today we like shiny brass and bronze instead of painting over it. So every single piece is polished and lacquered. The telescope has vents at the end of the tube, the objective end, so you can cool it down. But this particular style, the clearances are such that if they jam, and as soon as you paint it, it doesn't open again. So my son Aaron's been helping me. We had to like dig all the paint out of the screw heads and take it apart. That's what that looks like after it's apart and sandblasted, glass bead blasted.
Was that just pulled and open and shut by hand?
Yep. But these steel shutters, you can't leave them because it'll rust. And if you paint them, they don't fit. So I wound up making brass ones. This is my telescope where they figured out, was like 5 years later, they figured out that was a bad thing. They made a rotary shutter. And of course, you wind up breaking a few screws. These are quarter 22s, just to keep you on your toes. I did find quarter 22 tap and die and bought that. These are the screws that hold the rings onto the sheet metal tubes. And basically you have to polish each one. You can ultrasonically clean them all, but each one you have to sand down and then, like fine Scotch-Brite and then finally polish and then lacquer them. So I made these little racks to hold 100 at a time. I made a turntable to be able to lacquer these things evenly all the way around. This is the focuser getting cleaned up. And much of it you can do by spinning it, but you have these lumps where the clamping knob and the pinion for the focuser engage. So you have to kind of do that stuff by hand. And that's getting lacquered, but you have to tape mask over all the threads and other parts. We made custom stands to do the painting. This is what the sheet metal tube looks like after cleaning. And this is the bronze parts, new shutters. You can see you wind up with, you got to be very careful not to mix up the screws because they're all kind of unique and you got to keep track of where they go. So this is the focuser. I took the focuser apart and you basically clean everything. So this is kind of an interesting thing people don't do anymore. So this is the last part of the focuser plugs into this, and these are interrupted threads, like a gun breech. So you put the piece in and you turn it, and it's got this little slot you can see there. There's a locking pin. But doing that is a tricky thing because you're like inside the tube milling a slot. They're kind of showing off. And you can see in this picture, you can see that little pin, the guide pin, and then again, the male interrupted threads. Again, from a user perspective, it's fabulous because it's like a bayonet, quick mount thing. So you can take the eyepiece off, you can put the spectroscope on, you can take it off, I have a plate camera, it goes on. It's very, very clever. and tricky to make. So this is the focuser kind of shined up. I made a threaded piece that adapts a modern Bader click lock eyepiece holder. You don't want the eyepieces falling out. I decided to show off a little bit myself, so I made new knobs for the focuser out of rosewood. And you start getting all the cleaned and polished, some sound left over. So that's what the knobs look like after that. Here's the finder. Needs new wires for the eyepiece, and basically every single piece you got to take apart, clean, polish, lacquer, put it back together. One of the cool gadgets that I got for this project is a laser cleaner. It's about half the size of a dishwasher, runs on 220. It puts out 1,500 watts of laser light. And the hand piece has a galvanometer scanner, so you could do circles or lines. And all the paint and rust comes off as a ball of fire. There's nothing left. And the reason it works is that the damage threshold for paint and rust is low compared to bare shiny metal. So it takes everything off and it stops at the good metal. And you can tell when you're done because you got no fire.
Oh, I need one of those.
Oh, it's so that Arthur C. Clarke definition of magic, where any sufficiently advanced technology is indistinguishable from magic. This is it.
It's like a laser gun.
It is. And you don't want to be on the other side of it. You could chase people around the yard, set their pants on fire. So, doing a priming, painting, here's the telescope tube back together. It's 15 and 16 feet long. You can see I've got prototype 3D printed finder brackets.
Looks like the original eyepiece, doesn't it?
That was an eyepiece that came with it. It's not an original. They didn't have 2-inch eyepieces. But there are rods on each side for counterweights that were steel. And if you paint them, as soon as you tighten the counterweight, you chip the paint and then they rust. So I made bronze rods. It was like $250 for 2 pieces of bar stock. That's how you know inflation. You go buy a piece of bronze.
Those focuser knobs.
Yes, those are the wooden focuser knobs I made. So I'm trying to set up the finder rings. That rear tube is tapered.
Oh.
So it was a tricky business to put the finder eyepiece where you want it. And then I have to locate the other ring. And the bottom of that other ring, this one is a cylinder, but the other one's part of a cone. And the height's different because you want to look straight along the optical axis. So that turned out to be way too much time compared to what you would think. So I've got this gadget here, which I'm building for them, which is a 3-axis accelerometer. And I'm going to mount it in that little hole under the finder. So in my new parts, I have to put like a kinematic mounting in there. So you could take the thing out, put it back in, and have it repeat. The people online, I'll talk about that maybe a little later if I have time. But I want it's not go-to, it's a push-to, but they wanted the functionality of digital setting circles, and I told them I wasn't going to drill any holes in this thing. Fish wires through it because it's not pleasant. I've seen many done badly. So that's the two. We have a local group of antique telescope people in the Boston area get together maybe once a year, and I had them over to see this stuff as in process. So the tube's basically all done. The ends are bronze. There's like hundreds of brass screws. It's really very beautiful thing. Mm-hmm. So there it is with the prototype finder rings, the finder in place, but you can see the nice rosewood knobs, and it's a lot of bling. these are some of the gears for the fine motion. This is the RA fine motion. So you can see that lead screw. And that pushes on a big cast iron lever. And this little thing sticking out with the universal joint, that drives the locking wedge for the fine motion. And the right ascension is that other tube that goes past it. There's the lens, Roger Genet, some of you may know, sky and telescope editor. That's what that fine motion assembly looked like before. It's basically fine. It's just got 130 years worth of dirt. And that's what it looks like after you clean it. So that's the base casting. I bought a forklift just for the job. And as my son Aaron, he went over it with the laser, then paint stripper, and then a wire wheel, and a sanding disc. And now he's doing a metal prep, this thing phosphate metal prep. And then we bought a paint booth. It's like a bouncy house, inflatable paint booth on Amazon. It was like $300, so we could paint it without getting bugs in the paint. And that's us taking the equatorial head apart. That's the declination bearing axis. And we found writing from 1975. Last guy that worked on it.
Dennis Salisbury or something?
So these are the bearings, right ascension bearings. And these are those crazy concentric split gear system. And I'm lost to explain it. So anyway, this is the thrust bearing goes on here. You can see the Babbitt bearings for the main axle there, shims to set the preload. Those are the 130-year-old ball thrust bearing. And these are the anti-friction rollers. They're very sneaky. So they didn't really have ball bearings. So this is a feature that's on many old telescopes, especially larger ones. So they actually have like a lathe cross slide. You can see the dovetail slide there, and that pushes on that assembly. And what you do is you take the load off the main bearings. Right, so you take most of the weight off the main bearings, they don't wear. And then, but these rollers have another interesting trick. You say, well, it's a plain bearing. How does that, it reduces friction. So how does it reduce friction? It reduces friction just by the fact that the shaft that those run on demagnifies the force. That demagnifies the distance traveled. You still have the same coefficient of friction, but it travels less. So it's easier to push the telescope around.
Just geared down. It just,
Yep.
wow.
But it's a sneaky thing where the coefficient of friction is the same, the normal force is the same. It's just you're reducing the distance that it travels, so it seems easier. So we loaded up last week pieces to go to a paint shop, body shop in central Massachusetts. This is my old 1990 pickup truck. And then this is kind of where we are. So it's a complicated thing, many parts, you got to keep track of them. There's no such thing as too many pictures. And every fastener is a little adventure because they're all different. And some of them are unique. Most of them are unique. I have to build a few parts. I got to figure out the leveling bolts. It's going, New York site is 0.6 degrees different latitude. So I have to be able to adjust for that. The clock drive I got to go through, that's going to be, I think, just tedious. It's in pretty good shape. And a publicly accessible observatory is the best thing for these telescopes. You know, little kids see a telescope like this, they know which end to look into, right? You give them a Newtonian, it's like, what? Right? So it's a wonderful thing. It's going to a good home. And the cost of the observatory, they had to do a lot of work on the building. Foundation, they had to put an elevator, you know, ADA compliant, this, that, the other thing. the cost of the whole project is now up to 30 million. So the telescope is trivial.
How do you feel about it now? You were hesitant going in.
Oh, it's just work. I knew how much work it was going to be.
This
And
has to do with Janet 11. She's kind of
Yes.
famous, and so I'm sure she could pull some strings.
Yep. So anyway, it's getting done, and I wanted to bid the job so that I wasn't making any decisions about if I take a shortcut, it's going to take less time. So I got to polish all the bolts. I just got to polish all the bolts. If I have to make 2 different finder rings, I just got to make 2 different finder rings. Got to make a little widget for. So the thing on the table here is a little 3-axis accelerometer that displays the X, Y, and Z gravity amounts.
You can move the camera if you want. So that
This is not pointing at me though, so we can.
this looks right off.
I can stop the share.
Not sure.
And actually, if you just pass that to me.
Oh, here.
I did it.
Oh, that's really flying around. Okay.
Okay.
Okay, let's pin this so it's full screen. Oh my gosh, this is so hard to do sideways. Oh, here we go. Pin. Okay.
Oops, it evaporated.
What the heck?
When you
Yeah,
take the mouse.
everything, there we go.
Okay, so this gadget that I'm building has a little Arduino board in it that has accelerometers and Bluetooth. And the idea, and a little display, and it displays the XYZ gravity vector. And I built this little pointer setup so that I could keep the coordinate system straight. Otherwise, you get very confused walking around doing this with your hands. So the idea with this is I can put this in the finder bracket and it moves with the telescope. And I've determined that if you make these readings and you have an equatorial mount, you can figure out which way the telescope is pointing. And now I don't have to drill holes in the telescope. So I'm working on this with a couple of friends and we're working out the math. And another friend is getting this to talk to Sky Safari. So we'll get a little blinky dot on Sky Safari, wherever this is pointing. And if you think in a dome with a shutter in New York, number one, it's hard with a dome and a shutter because you can't see much of the sky. But in New York, there's no stars.
Tell these folks here the bad news about as telescopes.
So in any event, I'm working on this gadget that'll allow people to use it. And it doesn't have to be perfect. I just want to put something in the finder. So if I'm a half a degree off or a degree off, it's not the end of the world. And if it's 1.5 degrees off, I'll put a bigger eyepiece in the finder.
Alan,
Yep.
Maybe you didn't hear me. So these 2 guys are trying to get their telescopes hooked up so they can see it on Sky Safari too. And I can tell they're saying, "Oh, I want one," but they have Altaz telescopes. So
If you
tell them
have
the bad news.
Yeah, so if you have an Altaz telescope, the readings don't change. It's
Right.
useless. If you have an equatorial mount, you're at the North Pole, it doesn't work at all. If you're on the equator, it doesn't work. But if you have an equatorial mount that's kind of anywhere, I don't know, probably 15 to 85 degrees where there's some signal as the telescope moves, then this will work. So, and the math requires that you build into the solution the fact that it's an equatorial mount and the polar axis is pointed north and up. The elevation of the polar axis is the latitude, and the azimuth of the polar axis is true north. And you have to include those 2 facts for this to work.
Hmm.
And it's been a little brain teaser. Got people to help me, and they keep saying, "Oh, you just do this." Dan says, "Oh, you use dot products." Like, okay, how? Exactly.
Well, there's another guy online here.
Yep.
Zoom, and Alan.
So I created a giant spreadsheet, and I've created test cases. So if whenever anybody comes up with a candidate equation, then you can just plug it into the spreadsheet and see if it works. And then we'll code it for this thing. And that's the idea. So anyway, it'll be a wonderful thing when it's done. And many other old antique telescopes, I think, will benefit from this. So this gadget is sort of consistent with a lot more of what you guys do here, little 3D printed widgets. But the old telescope is kind of where we came from.
That's really cool. So you can't travel. You can't really travel with that thing and expect it to work, especially in latitude.
Well, you have to tell it
your
latitude.
Yeah. Okay.
Mm-hmm. So it looks to me like you're honing in on being kind of done.
About 3/4. So all the big castings are cleaned and prepped and they're out at a body shop getting painted. 80% of the brass stuff is done. There's still a few hundred bolts I got to go through and clean, and I've been doing like a gun blackening process on the bolts, whatever steel bolts I can't replace. And I've got probably 30 steel bolts I will be replacing with bronze hardware. Those all have to be machined to size, polished, lacquered. But it's like a piece of jewelry. It really does look fabulous. It's awe-inspiring, and that's what we're after.
No, nice.
So one of the other little adventures, am I out of time or?
Yeah, but go ahead.
Okay, so one of the other adventures in this whole thing is trying to teach the architects what it means to design an observatory. So the first sketches they did, they had the telescope up on like an 8-foot pedestal. And I was like, now the eyepiece is 20 feet off the ground. And they're like, what? I said, the telescope moves and you got to have your eyepiece at that end. They're like, oh. So they put the telescope back in the right place. I said, it doesn't go exactly in the center of the dome. It has to be offset. They're like, why? Because the motions that are the intersection of the RA and deck, that needs to be the center of the dome. Oh. And I said, you need an observing chair. What's that? So, and I said, the telescope has to be mounted separately from the floor so that when you walk on the floor, you don't move the telescope. They're like, how much? I said, it has to be solid as a rock. They're like, ha, ha, ha. So I finally talked them into coming up to Boston, and I took them to Harvard College Observatory with a great refractor, 15-inch refractor. It's not that much bigger than this thing. And the room that's under the observatory has the granite pier going up through. It's about 12 feet in diameter, big granite blocks. And I'm leaning on it going, you know what this is? And they're like, oh, you weren't kidding when you said solid as a rock. It's like, no, this goes down to bedrock, doesn't touch the building. The telescope sits up and it's like, oh. So we looked at the telescope and I said, you got to there's a lot of relationships. I said, this is going to Manhattan. We're going to be able to see Manhattan. You got to make sure that when the telescope is horizontal, you can see out the dome, right? You can't have the equator of the dome too high because you won't see it. And I said, during the day or when it's cloudy or something, people are going to really want to look at Manhattan because it's going to be an amazing view. I said, so you got to get the height of the dome just right. And then you got to have an observing chair. And that particular dome at Harvard has a beautiful example of this wonderful observing chair. There's like stairs on each side, and then in the middle there's a chair that runs on a track, and it has like counterweights, and there's a big wheel you turn, and it goes on tracks around the observatory. It's really a wonderful thing. So I got them all to sit on that, took pictures. So they know more about it, much more about it now than they did then. And we'll see if, I said, the lighting, you gotta get the lighting just right. I said, you don't want to see any light source. It's gotta be, you know, you gotta have the light source low. It's gotta be red. You gotta have a dimmer. We shall see. And I said, you really got to get the vibration right. Because what's going to happen is when we have an opening, Neil deGrasse Tyson's going to be looking through the telescope. And if it wiggles around, it's going to turn around and say, what idiot did this? And you don't want to be there. So the project has a lot of interesting aspects, and it's keeping me busy, that's for sure.
What about the optics? What's done with those?
The optics are in great shape. They were cleaned about 10 years ago. They're in fantastic shape. I do have to take it all apart, clean everything, refinish the brass. It's not bad, but it's not up to the rest of the telescope.
Are there enhanced coatings on it?
Any what?
Are there coatings on the glass?
No. 1895, they hadn't figured that out. And people have tried to coat old optics with some disastrous results. I think we know enough today that they could probably be successfully coated. But there's an argument that says the uncoated glass has less scatter. So for planetary work, it should be really superb. Anybody else? Anything online?
No, there's one more chat. Oh, spectacular. There you go. Good job. Very good. Yeah,
That's
I
a good
agree.
comment. It is. It's a fabulous thing. It really is. And we'll all get to enjoy it.
Okay. Let's get Rob going here. Wow. Oop. Let's make sure this doesn't get wrapped up.
You wanna, Alan, you wanna take this back? I might end up using the table. Unplug the. Yep. Other end. Okay.
Okay. And okay, we're gonna get Rob Brown going here. Yeah, so sorry about there's no break, but it was worth it. Okay, do you want the PDF or the PowerPoint?
Oh, no, I'm sorry, not the PDF. No.
Oh,
what a dope.
It's all right.
I meant PowerPoint.
I'm president of the Dope Club, so it's all right. We'll just get rid of it. This will count as our break. Okay. Now, will you want to bring it up to share it, or she want me to bring it up already?
Bring it up. Yeah, that's fine.
Okay. No, come on. There we go.
No.
Okay. All yours. Take it away.
All right. Okay, I'm Rob Brown. Nice to see you all again. This is my third talk on this project and my final, although the scope will never be done, right? The previous two talks I gave were really about the making of the mirror. And where I left off last year was just inching closer to that parabola. And I've now gotten there, and I'm very happy to have a working telescope.
which you see pictures of here. And it's covered in this month's Sky and Telescope. So thank you very much, Jerry Oltion. I think the theme of this weekend, if I have to pick up on one, is that good enough is good enough. I put that in there, and then it actually turned out to be true. I've seen this in almost every talk that's been given. Sketching, building whatever scope has been built, and there's a certain amount of having to deal with reality that we all face, and you just draw the line somewhere. So I've certainly drawn a big fat line for myself and said, okay, time to build the scope. Another thing I have to admit is I wouldn't have broken any glass had I built the scope first and then put the glass in it. It was that star test rig that effed me up. So, all right. So let's get into it here with some stuff on the figuring. What did it do? That should not be black. There we go. Okay. So as I said, I left off with the mirror in process. It was 7 to 8 waves from parabolic, but going in the right direction. And it was all in the center. And I had zone after zone after zone that I figured, radially inward to get to the parabola. And I ended up doing a very unusual technique. I'm going to describe that a little bit. The last talk was all about figuring techniques. I'm just going to limit this one to a very little bit about figuring. It is an unusual technique, but if you want to learn more about it, you can get me offline. And then, of course, I'm going to talk about the completed scope and what worked. And I do have the mandatory slide on what did not work relative to the build. Okay. So starting right off, I had thought I got to the final figure in January. And then I built the scope. And then in June, I got or maybe more, May or so, I got my first star test. And I was like, yeah, this isn't right. And not really knowing what was going on, the Ronchi matching test, which you see in this area here, the lower right, was kind of running out of juice for me. And there were things that I just didn't know about the Ronchi test. And Mel kept telling me, well, you got a high center. I'm like, I don't see it. But when I did a star test, I sure saw it. So I refigured it. And I'm going to talk a little bit about the refiguring right now, and then I'll jump into more about the star test next. But right away to start off, look at the Foucault test right here. We got zones that just lay right in the tornado, and then it just pops up in the center. And so I knew I had to get that center down. I did a thing to it, and I got that center down. And what I did was I had been making these very concentrated spider laps that were active only on the area I wanted them to do their work. And those were were working for me. This is what I learned how to do at Celestron way back in 1988 on the hyperbolic secondaries of the 8-inch Schmidt-Cassegrains. Would it apply to a thin meniscus paraboloid? Well, it sure did, and it worked. And everything I was told about how to stroke the mirror over the pitch just wasn't working for me. So what I ended up doing was setting my turntable to a higher RPM and then holding the glass to keep it from spinning and just kind of wiggling it very short strokes, about an inch or so, and then let the glass rotate a bit, do some more, rotate the glass, do some more. And so it's really a spinning action that's happening here on this thing. And so what the key to making that work was using Mel's pitch lap calculator and putting it into the spin mode. You got to scroll down the page to find it, but it's there, and you put in the settings correctly, and you can actually make the polishing action, which is in blue here, match the measured wave error, or this is the Ronchi matching test wave error. So again, I wasn't seeing a high center, but I sure as heck was seeing this zone that I kept going after, and I kept pushing that zone inward and inward and inward until I really couldn't see it anymore. The thing that I was missing in the Ronchi matching test was that I kept doing it on the outside of focus, and I stopped looking at the I kept doing it inside of focus, and I stopped looking at the outside of focus where you get these bullseye patterns out here. And that sure enough showed the central hill. And this is an earlier Ronchigram when I really did have a big hill. So a little more insight is like, oh, okay, you got to look at the Ronchigram on both sides when you're doing the Ronchi matching tests, and that will give you the information you're looking for. Mel mentioned it yesterday. More bands is more information. Okay. The drawback to this technique was that it caused micro ripple or roughness. So you can see these kind of almost record player like grooves in the figure in the Ronchigram. I was very, very worried about that I'd have to go back and smooth it out. But now that it's built and I'm using it, I don't notice. I couldn't tell the difference. Maybe later, but I have another blank for that. I've decided that this mirror is done. So, oh, and here's a little more insight on the on this spinning lap. Very, very strong pedals. You can see that I started using more of a broad pedal. This is more like what I would have used at Celestron to get started on the hyperbolization. In this case, the parabolization. And then as you can see, as you go, it just starts changing shape as you're chasing the zones, right? And by the time I got done, it got from this large area contact to a very small area contact. And in hindsight, I think that I would pay more attention to or just put more work into learning how to do the W stroke and learning how to use a fixed lap on a table. I was very concerned about hurting myself polishing a mirror this big. My back isn't in great shape. I'm 60 years old. I'm starting to feel it. It's cold in my garage sometimes, and it's just like, no, I don't want to hurt myself. So I forced myself to use the machine, and I think the machine then in turn forced me down this path. It shouldn't have necessarily, but that's what I ended up doing. Okay, so I mentioned earlier that I did something a little different with testing. It turns out it's not all that different. But what I did was I used the Ronchi grating as a wire test, which allowed me to take Foucault zone measurements just like you would with a knife edge. And the trick to this was that, and I see this all the time, right? When I'm going through focus, I'm outside of focus, I go to inside of focus. And you always see this bullseye pattern turn into this thing that looks like the letter phi right down the middle, Greek letter phi. You put your dark zone right down the middle, and there'll be a circle at some diameter of the mirror. And that circle, that dark circle, is that zone being nulled out as though it were a sphere. Locally, of course, that mirror is spherical in that over that black area. And when your grading is in the right spot, or in any spot, it will show you where the mirror is being nulled out as though you were cutting it with a knife. And turns out that this is used in the optics industry. I didn't invent it, but I had the insight to try it, and by golly, it worked. So all I had to do was set up and I don't show it here, I'm sorry, but I set up a zonal ruler. So it was a piece of masking tape with a bunch of Sharpie marks on it where I wanted them. And then just turn the screw on my Ronchi tester until the dark zone was lined up on both sides with the mark, and then take a radius of curvature reading, which is really just delta radius of curvature, right? You're just reading it off a micrometer, and plot it out like you would any other Foucault test. You could do this with the, what is it? What's that software for Foucault measurements? I didn't use it.
6 tests?
You could use 6 tests. There's another one that Cindy mentioned, huh? Something like that. WinX. There's I guess there must be a bunch of
Figure XP.
Figure XP. Thank you. Yes, that's the one. I just coded my own thing up in Excel because the math was so easy when I stopped looking at Texero, and yeah, that was very helpful to get the right math in there. And so I was able to plot this up. Okay, now I'm gonna make that really go away.
It might go away, as long as the cursor doesn't touch it, it might go away.
Let's see.
It might not.
I want to be able to read it myself.
Maybe it wants to use the chat. Oh.
Make it go that way. Okay. Right. I got 6 zones. The central zone just is a big blob, and it's hard to read this way. Super easy to get good readings as opposed to making zonal masks and using a knife edge. When I did my 12.5-inch f5 with the zonal mask, those outer edges were so thin that it was hard. You know, you get a lot of diffraction around the windows, and this way there was really no diffraction, and you could really position that dark band right where you wanted it. Okay. Next slide. Here we go. So last weekend, I got to do a side-by-side with Mel out at his place. And the reason I did that was because I still had questions about how my scope was actually performing. It being really my first experience with a very fast scope. Again, this is f2.8, and you know, you'd think after 35 years of optical engineering, you'd know what a star test ought to look like, but that wasn't what my job was. And, it turns out that, you know, the eyepiece matters, what's going on thermally matters, and things just look different at f2.8 than they do at f5. So there's a lot to get my head around and get recalibrated about. So what happened was I go out to Mel's place, set the scope down right next to his, and it gets dark, and we go look, and the mirror just stood up and saluted and said, "Hi, Mel, I'm a parabola." Oh, thank you, Mel. Thank you, Mel. You just shed goodness all over it. So what I had been seeing was a lot of overcorrection and occasionally undercorrection. What did that mean? That meant I got some thermal stuff going on. So I knew I had to make a shroud, and I had started that process, but I didn't have it done yet for Mel. What I found out, observing side by side with Mel, was that my mirror was looking pretty good when we put in a P2 coma corrector instead of a P1 or an MPCC. Wow, it was like comparable to Mel's scope at low power. Again, we're using Nikon 17 millimeter, 102 degree. So this is what, 65X or something? I forget exactly, but low power, the 2 scopes were very comparable. It was, you know, we were able to look at Epsilon Lyra and discern the orientations of the double without splitting them, right? It was such low magnification, but you could see the orientations going on, and that was kind of exciting for me. So I've got an MPCC for sale if anybody wants one. I guess they work great at f5 and whatnot for photography, but not at f2.8. So that will fund my P2 purchase. So please. I learned I really needed a full shroud, and I needed to get that in place. It was working good at Mel's, but still, we could see both mirrors varying over the night, and mine was varying more. So I have now implemented the shroud, which you can see there, and I'll show the people online. Once we get done with the slides, I'll turn the camera around. As I think Mel mentioned, we discovered some IFN around M57, and it's now my next observing project to go sketch that properly. And I'm very glad to have learned some sketching techniques this week. So wonderful. All right. Okay. So that then is, the mirror figure and the star testing and the side by side. Now I'm going to talk about the build. So you'll see here I've checked off some lines that I have for slides. So I'm not going to talk about those right now. I'm going to talk about the ones that don't have check marks. So again, large, thin, slumped meniscus glass blanks. You've heard a lot about them over the years. If you're new to this group, note that we're talking about mirrors that have a thickness to diameter ratio of something like 40 to 60 to 1. Very thin. So this is a 16-inch mirror that's about 0.4 inches thick. I think Mel was a bit more aggressive on his backside grinding, and he's got it down to 0.375 or 3/8 of an inch. So very, very thin, almost scary thin, right? And yeah, they break. So you want to be careful with them. They're float glass. I mean, sorry, they're soda lime glass. So they're not Pyrex. They are not as thermally stable as some of these other glasses. It turns out that doesn't matter so much if you've got good thermal management. It's not the absolute temperature that matters. It's the temperature differential across the mirror that matters, especially front side, back side. And shrouds done right are supposed to help with that. They certainly seem to at 16-inch diameter. Of course, the 30-inchers we know still need fans to help keep that air homogeneous, but okay, it's a thing you got to do. All right, let's see. I'll skip down here too. So free from wood. I didn't use any wood at all in this telescope. It's a first for me. I was inspired to try to make this scope as light as I possibly could, and wood just didn't seem like the right thing to do. So I was looking around at some scopes that have been built, and most notably Howard's 30-inch over there, also free from wood, and you had used this aluminum plastic laminate material that is known by a bunch of different names: Alumicor, Lumalite, Coralume, I don't know. And Alucobond, right? And I got my stuff locally at Multicraft Plastics. They have their own brand. But yeah, it's 3 millimeters thick with 0.4 millimeter aluminum foil, basically bonded to each side and then given a very nice coat of black paint. And it's intended for outdoor science, and it's very durable, and it's very easy to work with. You can cut it with a razor blade if you have to. So it mills on a lathe and on a table saw just like butter. It's great. What I had to learn kind of the hard way was how to epoxy this stuff together. And I ended up making a very rigid base for this scope out of it once I learned how to epoxy right. Epoxy scared me because it's like, oh, you're going to mix something together and then it's going to cure faster than you can get it applied and it's going to make a mess. And I was just scared of epoxy. But once I kind of got my head around what I had to do, I actually 3D printed some holding fixtures so that I could put my pieces together at the correct angles. There's an octagon and all that. And then things went very easily. And I was kind of kicking myself for not doing that in the first place. But there you go, learning the hard way. I got a Crayford focuser that I stole from Jonathan Kistner and then modified to put in this filter flipper. So I got a 2-inch filter that you can just flip in and out. Stole that from Moonlight focusers. I have that on my 12.5 and I was like, oh, I got to have that. And we've actually made that design standard on the high school scopes we have up at Ida B. Wells High School in Portland, because we just don't want kids having to take filters out of cases and screw them into eyepieces and drop them and all that. So I just love it. Okay, tensegrity, that's been belabored, but it's a tensegrity design. The new thing here was that, well, when you make mistakes on calculations like focal length, you can recover pretty easily with a tensegrity design. You can shorten or lengthen your strings. Well, you certainly shorten your strings. You can actually lengthen your tent poles by adding a little extra piece in where they connect. And so I ended up iterating the tube length a couple of times with these tricks. The wire spider, nothing new there, and spray silver coatings, those are now well established. So all of these technologies have come together to make this scope, which is extremely unique and I'm darn proud of. So let's go into the other stuff now. So I've talked about parabolization and testing. So we're going to hit now on the cell design and then damped fluid bearings, which were introduced to me just last year, thanks to Ed. So the mirror cell, this was not exactly my idea. I can't remember where I first saw this, but the idea is that a 6-point flotation cell looked like it was going to work after calculating it out in plop. And I said, well, if that's 6 points, then I can use these torsion bars right here. Those are aluminum bars that go from the mirror cell frame out to another bar that has 2 pads on it. And then there's 3 of those, three of these little T's. And these T's then pivot on the intersection of the 2 bars. There's a little screw head under there. And they, it doesn't take much force to pivot them at all. And that was just good enough to, apply even load to the back of the mirror. The center retention, boy, that was a bugaboo for me. I just couldn't make edge support work. 2 points was a disaster. The sling, I actually had set up my mirror. I built my mirror cell before I started figuring. And so I had put a sling on that thing. And it seemed like every time I set it up, I got a different figure. And this is just trying to keep things spherical. But the figure wasn't like you got zones. No, it was potato chip. I could see that the mirror was not holding a good sphere in that sling. And I had to carefully set it. I had a process developed for sliding the mirror into the cell and then, kind of racking it up and down a couple of times on the sling and causing the sling to go hopefully in the right spot. And sometimes it worked and sometimes it didn't. And I knew that there was no way that was going to work for me on the telescope out in the field. So I said, well, what about center retention? How can I do that ideally without drilling a hole through the middle of the mirror? So, well, it's easy enough to just try without having to analyze it. So I 3D printed myself a little puck out of PETG. put a slot in that, and then although I'm not using it in the photo here, I put a screw hole in the thing and just screwed another aluminum bar to the back of it. Today, actually, the bar goes between the glass and the puck in a slot, so it's closer to the glass, and that there's a reason for that I'll go into later. And then it bends over with a little hole, and that just hooks over the top of the frame right here, and it just hangs down like a pendulum. And I tried that in the tester. Immediately, my astigmatism problems were gone. And no matter what I did, they didn't come back. So I called up Mel. He's like, I got to try that. And he tried it on his, and it worked. But for whatever reason, he was happy with his sling, and he kept with that. So, okay, that's good. So finally, then I've got two-axis collimation. There's a screw up in each upper corner of this thing, and those go up through the top of the mirror box, such as it is. And then I can access those with a wrench, a little socket wrench thing, and collimate from the top with my eye at the eyepiece because the focal length is so short. Everything else is, aluminum square tube and pop rivets, and it was an easy build. And I'm glad I did it, because testing it in the cell on a mirror like this is pretty important, I think. You can do it without the cell, but you got to know what to ignore and what to pay attention to, which wasn't my skill level, that's for sure. Okay, so size, weight, volume, and pressure. Well, I thought about it, and I said, look, I'm making this very lightweight scope that when it's all taken down, occupies a pretty small area. It's basically a 19 by 19 by 15 inch cube. The total scope weighs 28.5 pounds, not counting the eyepiece or finder. And I thought, well, gee, if I got the weight in pounds and the area of the mirror in square inches, that sounds like a familiar thing. Pressure, pounds per square inch. So I called Mel. Hey, Mel, have you ever thought about pounds per square inch? He's like, well, yeah, actually, kind of. And it turns out that he had a list of about 150 of the lightest telescopes, and then he put those together and ranked them by their pressure. And this is just the top of the list here. There's some very low pressure telescopes out there, if the reported weights are correct, that is. And Mel, if you're there, I really don't know if your 30-inch total weight is 97 pounds or if that's just the optical tube assembly. But it kind of doesn't matter. It's a 30-inch. Anyway, 0.13 pounds per square inch for these very lightweight telescopes. And I'm telling you, if you were to get the pressure lower, it's going to start to blow away in the wind. So it is just it's like walking up to an eggshell or something like that. I don't know. It's not as fragile as you might think, but it has the feeling of being fragile at times, So, all right. But there's a remedy for that feeling of fragile. And God, this bar.
What if you read the chats? Will it allow you to?
Maybe that's the thing. Let's read some chats. Oh, and Mel answered a question already. It's 97 pounds of the OTA, not including the base ring. So, well, I'm at the top of the list. Thank you, Mel. What was the name of the aluminum coated material for signs? AlumaCore, AlumaBond, AlucaBond, dual. Yeah. Just look.
For the 3 mm.
Yeah, just look up aluminum signboard, or I don't know, laminate, aluminum laminate. I don't know. All right, fluid motion control damper. This thing saved my butt. I originally built my scope assuming Teflon and some sort of textured laminate. In fact, I thought, ooh, 3D printed bearings. I might as well just use the 3D print. I've done that before. And well, I had it all put together, and it was just as jiggly as heck. And, you know, you push on the scope and it's not infinitely stiff, and it, you know, the star starts to move and then it hops. And it was just a nightmare, even with a whopping 1.7 degree true field of view, right? You'd think that'd be really forgiving. But no, it just wasn't working right. So Ed presented this thing on fluid dampers last year, and this is before I'd even started building the scope. So I knew that that was in my future. And sure enough, as soon as I got the scope built, I was like, I got to do fluid dampers. So off we go. The second bullet there, the reason this works is that friction has two coefficients, you know, which you don't want. You don't want two coefficients. You don't want static friction jumping into dynamic friction. You want one coefficient. Viscosity is the answer. So we use something called a fluid damper. It works on viscosity. As soon as it starts to move, it just moves. It doesn't accelerate. It doesn't have to hop off of a static coefficient. So let's see. It's a 3D printed housing, which I'm going to pass around. Oh, yeah, Richard's got it right there. And I'll hold it up. Actually, if I can hold up the camera first, you do see a nice picture of it. But let's see. I'm going to do a stop share real quick here, and we'll get back into it. Okay. So if you're looking at my picture, here is a sample of the thing that is on my scope. This is an altitude bearing. You got the damper sitting right here, a couple of skateboard bearings, and then right in between is the live axle roller, which is coupled to the shaft of the damper. But then that shaft, I should say, the damper doesn't carry any load except rotational torque, and the two skateboard bearings hold the axle in place and carry the load. And I'll continue passing that around. And also I'm going to pass around the thing that I did to increase friction between the roller and the bearings or the trunnions themselves, and that was to put 120 grit right on the axle or right on the roller with epoxy. Mix some with the epoxy, and then I just rolled it in a little pile of grit and got this very nice grippy thing. It's nice and round too. There's no lumps in it, and that really solved some problems for me getting this thing to work properly.
Okay, screen share, green button.
There we go. There we go.
Does that work to get rid of to read the chats? Yeah.
It did. Thank you, Dan. Now that the weekend's over, we figured it out. All right. Okay. It's supposed to work. All right. So, yeah, I had just mentioned I'd used the 120 grit impregnated epoxy surface for enhanced grip on those smooth surfaces. So only one Teflon pad remains. When all is said and done, you still need a little friction so that you can change eyepieces and stuff like that. So, and I am, now that I've kind of tuned it up to this level, I'm going to add another fluid damper to the altitude axis. In fact, the very one that you're passing around, I'll add that to my scope and see if that either allows me to eliminate a Teflon pad or if it just makes it work better in some way. I don't know, but it's certainly working fine now. So things to experiment with. Okay. There it goes. All right. Was there something else I wanted to say on this slide? I think.
Sorry, Rob.
Yes.
Can you just do you have details on exactly which damper you're using?
I do. And it's I've lost. Oh, it actually says it right there. It is the
Yeah, I can't see it on that image. It's sort of blurry.
Go over the scope and look, but E3152. I'm on the altitude, I've got the FRT D3 152, and on the azimuth, I've got the dash 501, I think, which is an even lighter, a lower viscosity part. Now that I've said that, don't assume that because it worked for me, it's going to work for you. I did the calculations, and this was kind of earlier, like back in June, and I think I made some wrong assumptions. I think Ed has changed a few things in the calculations since then, but I arrived at the wrong damper part. I had a very, very high viscosity part, very high torque, and I just couldn't move the scope right. But I do think that at this point, if I had to do it again, I would buy a range of parts, and then I'd just return the ones that I wasn't going to use. But maybe we'll get better at it and be able to calculate exactly the part to go use. But I'm not feeling highly confident about that right now. I think we'll get there. It's just
I asked. Yeah, I asked because when I was looking at it a week or two ago, it's not only how much friction or viscosity it's got, but there are the different classes of devices, and some are better than others, and so it's even just the class of device that you were using that I think that I wanted to get details on.
I certainly couldn't comment on that. I only ever tried one class of device, and that certainly seemed to be adequate. It's really the low end of the price range stuff. But I guess that's good news. So, all right. Next slide. Okay. Getting down to the end here. So what went wrong this time? Well, let me just first of all say that I didn't break any glass, but I did miscalculate the focal length. You'd think an optical engineer would know how to calculate focal length. Well, there were things that, in the end, I got the radius of curvature right. But when I went to go build the scope, I made calculation errors. The biggest one being that I didn't have my focuser perpendicular to the optical tube. I thought I did, but I didn't really have an optical tube to measure against, in my defense. But it was off by a lot. And when I was done, that secondary was like an inch off in terms of its distance from the primary mirror. So I was like, why didn't it come to focus the very first time? I had to rack it all the way in, and it wasn't it wasn't getting there. Well, I just added an inch of path length that I didn't know about. So what did I do? I shortened the tubes, right? And the strings. Then later on, I found out, oh, yeah, that secondary is not in the right place. And then I redid the wire spider and got everything lined up where it's supposed to be nice and perpendicular. Oh, shoot, now my tube is too short. So I had to take half of the string shorteners out, and then I had to add some extenders to the tubes. And it was just, I'm chasing this thing around like, what could be so hard about it? Well, tensegrity is a little funny. Building a scope is, this is an unusual scope, put it that way. It just caught me in ways I wasn't expecting. Those live axles are too fragile, and I did pass them around, right? The live axles, the ones with the grid on them, are they back in the box? Yeah. Okay, good. So what I did, this was kind of clever. The damper has on it a pair of flats on the shaft, right? And you're supposed to put a set screw in there. But I thought, but I got a 3D printer. I could do anything. So I measured those things carefully. I made the inside hole there match that exactly. And I iterated a couple of times until it just kind of snapped on. So I put the two bearings on, snapped that damper in there, and man, it's solid, right? Oh, this is great. Well, the plastic isn't all that strong, and we are putting a fair bit of torque on this thing as we move it. And over time, and not a lot of time either, this is like, June through now. In fact, just this week, the altitude axle snapped off. And so I quickly reprinted some new ones. That's why these look so fresh, because I made a bunch of them. And what happens is that the wall thickness, in doing what I did, I just have a very thin wall thickness, a very thin cross section. And so what I did to fix that, what I will do to fix that is I've ordered some new bearings that, instead of being an 8mm inside diameter for an 8mm shaft, I got 10mm. It was the biggest shaft I could get. They were just a few bucks, and I'll then make a new axle that's bigger on this side only. I don't have to do the other side. And that ought to give me some plastic to grab onto, and hopefully it'll last. If it doesn't, then, well, there's another way to skin that cat. But for now, that's where I'm at. It's a very compact design, and I was thinking I would use couplers, right, to couple from one to the other with set screws and all that. If I had gone that route, then it would just stick out a couple of inches and something to whack my ankle on. So that's why I did that. The balance isn't perfect. I got a spring to compensate that, but this is a spring to compensate for a balance miscalculation, not a spring to compensate for really an unbalanced telescope. So that's working out really well. I'm happy with the spring. It's a little annoying because I got to remember to disconnect the spring every time I pick up the telescope, or it takes the flex rocker with it, and it's all, oh, geez, what a mess. So I did rebuild the base. The first one was a laminate of 3D print and the aluminum stuff, and it just was way too flexible. It turns out that this aluminum laminate material, if you do it right, boy, it is rock solid. So I had to learn how to do it right, and Mel and Howard were able to guide me really just through the pictures you put on your websites. And I was like, oh, now I get it. A few questions I sent out to the group, and, think of an I-beam. Okay, how is this like an I-beam? Oh, it is really, I actually made an I-beam, about a foot long of I-beam out of scrap material, and just to make sure I kind of knew what was going on. And that helped. So then I put the whole thing together, and it was like, okay, wonderful. The upper ring, I'm going to rebuild that and do the same thing I did to the base. The secondary, I'm still learning about wire spiders, but this being a very lightweight scope with tensegrity, I've had situations where I've traveled as far as from Portland to Eugene, set up the scope, and it's been like, wow, it's perfectly column, or it's close enough. I can just nudge something and bam, it's collimated. Other times it seems like, God, I got to totally rewire the spider to get back to where I was. And so hopefully when I redo that ring, then I'm going to increase the string angle or the wire angle on the wire spider. That should give some more stability, along with a stiffer upper ring. I think that'll stay put like it does on all the other scopes I've heard about. So the mirror itself, I'm very happy to have an operational telescope, but this does not pass the flashlight test, this scope. And I had these spheres. I silvered them at Spherical just to test the silvering, because we were doing some silvering experiments. They were spherical a year and a half ago. And I say they because I had two of them, and they were beautiful. Not a scratch, not a sleek. I put silver on them, and it was like, wow, I could fall into that hole, just wow, they were so beautiful. Well, then I get to figuring. I run out of the good cerium, and I was like, well, I got this Wilman Bell stuff. I'll just use that. And I was so disheartened. It was almost as bad as breaking the mirror. It was just sleeked to forever. And I said, okay, well, so I ordered up some good cerium, and I just said, you know what? I'll probably spend so much time refiguring that I'll polish out all the sleeks. And that never happened. It got better in the center though. So honestly, planets suck looking at them in this scope. I get halos, and the reason for that now I'm convinced is that the figure it's still a little high in the center, and I could go back to the Foucault data, but it is a little high in the center. And before I really report on that, I'm going to do another couple of star tests with some masks like Mel recommended, and I think that will tell me really what the center versus the edge is doing. We heard yesterday about how important the edge is and how important that the difference between the center and the edge is small enough. So on the other hand, good enough is good enough. And even if I do find out that, well, I should have gone further, I probably won't. I would rather start over on a new mirror than dink around with this one anymore. And I have the blank. So maybe there's a binocular in my future. That was certainly part of the plan. Okay, there's a chat. I'm going to read it. If it were easy, it wouldn't be fun. Yeah, I can't argue with that. So, in summary, the telescope gets me to a snap focus, I think. If I know what a snap focus is supposed to be, I think I'm there. Good views up to about 150x, not too bad. No astigmatism, cell's good. I just mentioned I'm going to check the center versus edge foci. Super wide true field of view, 1.5 to 1.7 degrees, depending on the eyepiece and coma corrector. And that has changed my viewing experience and my viewing methods. And that's probably the most important thing about this scope is you see in the photo here, I'm sitting in a chair instead of standing. I'm not used to that. And I'm scanning the sky instead of staring at objects. So I found this just came naturally. I didn't expect it. But with the fluid motion, moving that scope is so easy. With the wide fields and just being able to be comfortably seated, I am no longer wanting to just go find that galaxy and look at it or whatever. It's like I'm following the Milky Way. I'm seeing the IFN that I've heard so much about and have experienced just small tastes of. And I'm going where the scope tells me to go rather than the other way around. Isn't that a thought? So really different experience, and I just love it. It's made me a beginner again. You know, it changed my relationship to the sky. I feel like a beginner again. So the fluid motion, of course, I can't say enough about that. I hope it becomes the standard in ATM now. It's not hard to do at all. It's a heck of a lot more. Well, it just works so much better than Teflon and whatever laminate. You know, you might have to iterate a couple of times on the dampers, but I think we're going to get there where you don't. If enough people start doing this and really, you know, it's easily accessible with 3D printing. You can make some really wacky looking housings like I did, but you don't have to. And Jonathan Dubé was here yesterday with his 10-inch bino, in which he strapped on an extra damper. By the way, I got all these extra dampers from Ed. Thank you, Ed. So I gave him a couple. And he just kind of kludged it in there with a couple of nuts and bolts and a timing gear, and didn't need to do any 3D printing. He had it done in the afternoon, and okay, good. But I say it does not mitigate poorly balanced scopes. So it does work best when your scope is properly balanced. Thus the spring on that thing. If I take the spring off, no, that scope's just going to droop just like it would on Teflon. Maybe more slowly and more smoothly, but it drifts. So get your balance right. Very compact and lightweight, low pressure, goes into the Prius with room for plenty of camping gear, goes into my Nissan Leaf fully assembled. And that is really awesome to show up at Stub Stewart, you know, and just pull my whole 16-inch down, set it down and start observing, you know. My friend with his similarly compact 18-inch is still assembling. I can just carry it, you know, one hand on the OTA and the other hand on the flex rocker and ground ring. It takes about 10 minutes to assemble or disassemble, and eyepiece collimation. That's actually what I'm doing in the photo right here. As you see my hand out there on one of the collimation screwdrivers there, or a nut driver actually. And the mirror wasn't coated, but oh well. But that's what's happening there. So that is the end of my discussion. Any questions, comments, complaints? Yes, we'll start with Dan.
Why did you call it broken glass?
Why did I call it broken? Are you just rubbing it in? Why did I call it broken glass? Oh, okay. Well, I broke 2 mirror substrates to get to this state. That's why I called it broken glass. I put a little umlaut over the O and dropped an S just to make it cute. In retrospect, I think I should have used the Swedish. They have a slash through the O. I don't know what that does, but it would be cool because then I could break the O into 2 pieces and make the slash jagged. Oh well. Javad.
Yeah, you have the center suspension mirror, whatever support. Very cool. But I'm wondering, what if you just attach that puck to the mirror cell itself and do away with the 6 points?
Okay, the question was, what if I do away with the 6 points and mount the mirror right on its center, just like a Celestron 8-inch or 6-inch or whatever? And the answer to that is probably more complicated than I even know, but the substrate has to be designed for that, as far as I know. I didn't try it, so it might work, but my feeling is that it wouldn't, because the usual way of doing that, you have a substrate that's thicker in the center and thinner at the edge for good reason. So this isn't that. And I was like, nah, it's too much to buy, you know. And where I started from, of course, was 6 points with a sling. And adding the center support was easier than thinking, what would I design if I was only going to center support? So that's kind of how I got to it. And maybe it's worth investigating. But I'm done. Sorry, what?
Follow-up question.
Yeah.
What if your 6 points are attached to the center puck so that you can just bolt it to the mirror cell? And, you know, so it's kind of a cone but stripped out.
Yeah. What if the 6 points were part of the center puck?
Yeah.
Well, then it's an entirely different support system. So the center puck only retains the load parallel to the mirror surface. And the 6 points only retain the load perpendicular to the mirror surface. So you don't want to put those two together. If you do, you're into something else. Yep. Okay. If there are any other onlines, no, then do I have time for just one bonus slide? All right. This is kind of getting off topic, but kind of not. I just had to put this in here. It's called Enjoyment versus Relevancy for Shopping at a Hardware Store. And I thought, well, if there's any group that's going to appreciate this. So I put this chart together as inspired by Randall Munroe of XKCD, right? So it's a chart which shows on the vertical axis increasing joy and increasing pain and anguish going in the negative direction. And then here at the 0, point, we have intended use, no joy, no pain. And then going left to right, we have increasing irrelevancy. All right. So you go to the hardware store and you go buy something and you're going to use it exactly as intended, right? Doesn't matter what it is. It's like, it's just a chore. There's no joy, there's no pain, no anguish. It just works. You put it in, it's done. Unless it's plumbing, of course, then it's negative. Yard and garden, yeah. So then you get a little more irrelevant and you get into these tangential uses, and it's like, oh, it's just get more interesting. I get to go to the hardware store and do something a little more creative. And then you get to like totally unrelated uses, and the joy factor goes up a little more exponentially. Oh, and by the way, there's these error bars. So these 2 sigma error bars, that's this dotted line that goes up here and this other dotted line that goes down here. And what you see here is that when you're in the low risk area, tangential uses, you might get more joy than you get pain, right? Because you're not too far off the mark. But as you get out into unrelated uses, then finally into telescopes, man, you're way out in the weeds and you're going to get some joy, but the potential for pain really increases. It's also worth noting that, of course, that most power tools fall into either the high joy or high pain and anguish, or both, depending on your luck and skill, I suppose. So there you go. A quick summary of, oh, there's one more thing on here, way up at the very end where this curve just starts to go asymptotic to vertical. There's a dot, and that says only something I would think of. Okay, and so the joy error bar goes right through that dot. There it is. So if it was like something only I would think of, then I just get that much joy, and that's it. There's no extra. And it is all potential negative after that. So that's my talk. Thank you very much.
Okay, one more
Oh,
chat.
got one in the chat. Okay. All right. Let's go up here. We got a couple of them. If it were easy, it wouldn't be fun. Kind of in the same vein. I recognize the in-between image you mentioned earlier using Ronchi as a wire test. I remember seeing that with the Ronchi. Yes, you definitely did. And Dick Parker mentions it. Yes, absolutely. I didn't invent it. It's well known and probably poorly documented. So hopefully we get to see a little bit more about that in the future, and maybe it becomes I thought it was so easy, just like I'll never make another cooter mask again. There's just no point in it. 5-gallon buckets make great secondary cages. Sure they do, Jerry.
That's what he did.
You know, the 5-gallon bucket is smaller than my mirror, though. So, in fact, I use 5-gallon buckets as places to put my mirror and tool in between, you know, like for drying it off and cleaning it for testing and just putting it aside so I wouldn't break it again.
Why do you want that?
Why do you want that? Asked the clerk. For my telescope. You know, if I have to get into a discussion with the clerk, then my joy just goes down. It's just there's no. I've tried. You know, it was for this telescope I'm going to make, and they're like, you're lucky if they even know what a telescope is. You know, so I just kind of give up. But that's me. Sometimes you get somebody, and it's like, yeah.
So I had an experience. There's a winch on this telescope. I'm going to give a presentation on it that lowered the bottom shutter, and so I'm talking to, and it's bad. The winch is bad, the electric winch, and I called and ordered a new one because they wanted to make sure that I said, what is this for? And you know, it's not like, can I explain? Well, it's for a shutter on an observatory, and they have no idea what I'm talking about. So
yeah, exactly. A shutter on an observatory. First of all, what's a shutter? Yeah. Just for kicks, so you can see the whole thing in its final configuration here. Those of you online, you can experience the fluid motion virtually. One thing I will say about the fluid is that if you just come up and grab the scope and move it like I did, you know, try to swing it around real fast, you'll go, oh, that's not very good. It just feels like Teflon. But it's when you're at the eyepiece and you move it really slow, like you're slewing across, you know, a degree per every 5 seconds or something like that. That's when the fluid kicks in and you're like, oh yeah, I get it now. Yeah. Yeah.
Just imagine a hardware store that had all these things, and you could walk in and it would be very large, but you would find this kind of thing, all the sizes you might want.
Right.
So you could play with.
Yeah.
But there's many other things you haven't even thought of.
Exactly. Right. That's the power of 3D printing, you know. Yeah. I used to think of it as, oh, what a waste of plastic, a rapid prototype, and then you throw it away. But No, man. It's a good use of plastic now.
3D print everything that's possible.
Yeah. Okay.
Are you going to show us the mirror?
Thank you all. Am I going to show us the mirror? Heck no, with all those scratches in it. No, I'd be happy to show you. You'll see how good enough is good enough.
Yeah.
Yep.
Remember too, all the wires here, it's the same as sketches on the mirror.
That's right. Yeah, all those spider obstructions. Compare to a scratch. Yeah. Here we go. Pull it off.
Okay.
Are we at a break?
No, we have no breaks. We're a little behind schedule.
Okay.
And yeah, well, I think that's good because we don't have any more time.
Testing.
Testing.
Good.
Test-
You hear me? This is John.
Oh, hi, John. Okay.
Always in front of people.
Let's see here. Let's get your.
If I can just introduce this for a minute or two before you start it. Because soon as you start it, my voice is pre-recorded but thank you so much. When I saw there was a hole in the schedule, I volunteered to offer this talk. Peter Abrahams was such a good friend and inspiration to many of us, and his knowledge of telescope history and his willingness to share it was just so wonderful. So I gave a talk a couple of years ago about a really cool observatory out on Fisher's Island, which is off the coast of Connecticut, but it's actually part of New York State. And this was at a museum out on Fisher's Island. And so they have this observatory there. And the people who live on Fisher's Island is a very exclusive place, mainly summer homes for very wealthy people. And I knew about the observatory for years, but a lot of people living on the island didn't know about it. They didn't know about Warner and Swayze, and they didn't even necessarily know that much about astronomy. So in this presentation, I tried to share share it with including information about astronomy and why we love telescopes, why we're inspired by the beauty of the sky. It was for a very general audience, and so thank you, folks, for your patience as I spend some time in this presentation talking about our motivation in general for astronomy. But I hope you enjoy it. I was real happy how it came out, and I'm especially grateful that Alan Slisky was also speaking about Warner and Swayze telescopes for us, because he went into the technical details of the telescope and how beautifully it was made. And I don't do that in this presentation, but I hope that you enjoy how I handled some of the other issues for the general audience. So Howard, thank you. Why don't you let it rip, and hopefully my sound will come through for everybody.
Okay, here we go. All right, let's see. This is, why is this not? Exactly the way I thought it would be. Okay. Maybe just doing that. Yeah. Okay. Push that out of the way. Get that going. Okay.
You might need to have share sound enabled on your computer, and you might not.
And I'm going to share with you today the story of astronomy and the E. Wilbur Rice Jr. Observatory on Fisher's Island, New York. Now, I've been interested in observatories and telescopes since I was a boy, and the interest has carried on all these years. And I have an observatory of my own here. This hilltop is in my backyard in rural New Mexico. I thought before I got into the history of Rice, I'd just show you a few pictures of our sky here, because really it's the beauty of the sky that inspires such intense interest in astronomy and telescopes for people like me. And it's been happening a long time, of course, but let me show you. Here's a picture of the Milky Way above one of the observatory domes on my backyard hill. Isn't it something? It's sad that too few people nowadays, especially children, have a chance to see the Milky Way in all its glory. Of course, the camera that took this picture was very sensitive, but many people would be surprised how possible it is to see the Milky Way and the features of the night sky still by eye from a sufficiently dark site. The orange glow down in the lower left is scattered light from the nearby village of Magdalena. Only about 1,000 people live there. The sky glow was especially bad this night because of passing smoke from a forest fire. But you could still see here in New Mexico the breathtaking beauty of the sky. What sensational beauty is there for us to see and record in the sky? Like in this shot by my friend Bob Fugate when he was visiting my hilltop. Look at the color, the natural colors that are there in the gas clouds and the darkness of dust clouds that are blocking the light from background stars. It's really an inspirational sight. Notice that one cloud is quite yellow, and there's a yellow star embedded in the cloud, and there's maybe a sideways V-like structure in the dark nebulosity. Just make a mental note of that. What a picture of the Milky Way. Like the last one, it was recorded by Bob Fugate for my backyard. In the upper right quadrant of this picture, there are quite a few blue stars, but also among them, the brightest one is a yellow star. And then above the yellow star is that same V-shaped, sideways V-shaped, a pattern of dark cloud in space. So this is giving you a sense of scale for that last picture. Those mountains are the Magdalena Mountains, about 5 miles south of my place. And the scattered light below is coming from the village, reflecting off the hills. But nothing of this image is in any way a cartoon or somehow artificially enhanced. This is showing the real sky as it is, just beyond our human ability to see it. But it's surprising how much of this we can see. And of course, it's the beauty and the mystery of the sky that attracts our attention to it. And that, of course, is the way it has been for a long time, at least for people lucky enough to have experienced it and to have had the time to think about it and learn about it. Well, I grew up in Massachusetts, and I was hooked by the beauty and the mystery of the sky at a young age. And actually, I was not terribly unusual in this interest, but I was also fascinated by the tools that made seeing these things firsthand possible. And so I was no more than a young man when I happened to notice this advertisement on the back of a 1930s issue of The Telescope magazine. Now, that's an impressive telescope. The caption reads, 10.5-inch refracting telescope for the private observatory of E.W. Rice Jr., Fisher's Island, New York. I couldn't help but be curious about what this observatory was, really not so far away from my house in Massachusetts. Also, it was made by the famous Warner and Swasey Company. I'd heard about them, but I didn't know who Rice was. To give you some perspective on the Warner and Swasey Company that built the telescope, well, for example, let's take a look at Yerkes Observatory, built by University of Chicago, dedicated 1897. In the early 20th century, one of the world's great observatories. Many of these observatories, built for research and advanced education in the early 20th century, were equipped with Warner and Swasey telescopes. They were really superb. Yerkes Observatory still exists. It's in Williams Bay in southeastern Wisconsin, and it is a wonderful place to visit. Even before you step in the front door, you realize that they built this place to be a lasting and significant observatory. Yerkes Observatory is famous for many things, but certainly its great distinction is the gigantic telescope, the Yerkes refracting telescope, still the world's largest lens-type telescope, dedicated in 1897, and its mechanical parts were built by Warner and Swasey. The Warner Swasey Company mainly made machine tools like turret lathes, milling machines, but both Mr. Warner and Mr. Swasey were amateur astronomers in their own right. They loved telescopes. They built telescopes for themselves, for sale to schools, to private observatories, and most particularly, the leading research observatories in the early 20th century. But going back to that advertisement that had impressed me so, who was Mr. Rice? Eventually, of course, I found out he was a pioneering electrical engineer, and he ended up being the honorary chairman of the board of the General Electric Company. What's clear, though, is that even through all of Mr. Rice's in electrical engineering, he had maintained his interest in astronomy from his boyhood. And it clearly goes back to his attendance in the 1870s at Philadelphia Central High School, which, as you can see in this image of the building, featured an observatory up on the roof. Now, when Rice came to Central High School, he discovered a young teacher there, English-born, Elihu Thompson. Elihu was intensely interested in science, and particularly the mysteries of electricity. The telescope up in the rooftop dome had been imported from Germany in 1840. So it had already been there over 30 years. It had a 6.5-inch diameter lens, and it was one of the very first observatories in the entire United States. It's clear that Central High School in Philadelphia was not the average high school as we think of them today. All kinds of things, exciting things were going on there. For example, this ghostly image here allegedly shows part of the high school building, but it is noted as the first photograph, a daguerreotype, recorded in the United States. This image shows the Central High School building about as it appeared when Rice and his young teacher, Thompson, were there together. And you can see a hint of the observatory dome peeking out just above the roof of the building. I didn't realize, however, that one of Thomson's most particularly noteworthy electrical observations specifically involved the observatory until I worked on this presentation. Let's look again at this image as I tell the story. As any good teacher of physics or natural philosophy knows, a great way to engage students is to demonstrate electricity with big sparks. It's the subject of electrostatics. Thomson was well equipped to do this at Central High School, but he made an observation that was later recorded in his memoir published by the National Academy of Sciences, a very astute and unusual observation. Exactly as his large sparks flew in the electrostatic generator, at the same time, small sparks were noted on metal objects elsewhere around his lab. Small sparks were noted even upstairs in the darkened observatory dome on the doorknob. The experiments were reported in 1876, and you can only imagine the impression this must have made on students like Rice to be seeing experiments like those. Thomson recognized that this was a demonstration of electric action at a distance and of what we call today electromagnetic waves. It was a direct clue to the coming world of radio communication. Not long after the experiments, Central High School granted its young faculty member Thomson a master's degree, because that's one of the other unusual things about Central High School. It was certified as a degree granting institution. Again, very different from what we think of high schools today. Not long after Rice finished his studies at Central High School, he and Thomson decided to team up and devote themselves as research pioneers in the expanding world of electrical engineering. The rest is history, leading to the creation of the General Electric Company. Here are Rice, just left of center, and Thomson still as young men as they ascended, in the company of scientific and engineering luminaries, including none other than Lord Kelvin on the right, someone you learn lots about in the history of physics. And if that last photo weren't enough, here's Rice on the left, now much closer to retirement, beside none other than Thomas Edison there on the right. The amazing environment at Central High School continued, and astronomy was considered a very important part of it. The building was replaced about 1890 by this cathedral of science that had not just one observatory dome, but two. And the telescope now was a 15-inch diameter refracting telescope, an extraordinary instrument. When I discovered this photo as a young man in the late 1970s, already very interested in the history of observatories, I simply could hardly believe it. But why hadn't I heard more about Central High School in terms of recent history? What had happened to this observatory? Well, the tragedy is that the building and the observatories burned not too long after this building was constructed. Let's finally now get to Fisher's Island. Rice built a beautiful retirement summer home out on Fishers. And with the passage of time, I finally had an opportunity to visit the observatory that was also on the grounds of this lovely estate. Adjacent to the home, a beautiful New England garden. And above the garden, the wonderful observatory that Rice built starting in 1931. Let's take a look inside. You enter the building through what astronomers would call a warm room. That's because the observatory dome room itself can't be heated. The rising warm air would ruin the view of the telescope. Just inside on the left, an observatory clock that keeps a special sort of time called sidereal time that's used for pointing the telescope at celestial objects, for pointing by numbers. It also cases holding specialized accessories that attach to the instrument. In another corner of the room, a large table for holding star charts. And in the other corner, space for a reference library. But what about the sink? Well, the idea of the sink is that in the fourth corner of the room, there was a closet with a small dark room for developing the films and plates that could be produced with a telescope. So naturally, it was nice to have a sink to wash off your hands after you're done using the photographic chemicals developing the typically glass photographic plates. Let's step up finally, though, to the main attraction. The 10.5-inch diameter refracting telescope built by the Warner and Swayze company. Oh, to a telescope enthusiast like me, is simply a dream machine. You've stepped up from a doorway from the warm room, up a little flight of stairs and through a spring-loaded gate that makes it hard to slip down the stairs in the dark. But, oh boy, everything about this observatory was just absolutely terrific. This is the action end of the telescope where you look through it or attach a camera for photography. The smaller tube on the left is a wide field of view telescope called a finder, something like a rifle sight on a gun. The magnification powers used with the main telescope might vary from about 50, maybe all the way up to 600 or more if weather conditions allowed such high power. But to point it, you use the wide field telescope called a finder on the left-hand side. The prominent wooden knobs on the right-hand side are for locking the telescope in position, engaging the motorized clockwork that allows it to track the sky and keep something centered in the field of view, and other knobs that you turn for slow motion adjustment. And then, of course, on a brass axle there, two knobs kind of reminiscent of the focus on a microscope, which of course is also used to focus the view through the telescope. For all the excellence everywhere, Warner and Swayze was most famous for the excellence of their telescope mounting mechanisms, the parts that allow you to point the instrument around the sky, but then hold it there stably without vibration, allowing tracking, but also slow motion. Since Warner and Swayze built precision machine tools like lathes, metal, milling machines, strong telescope mountings were second nature to them. The famous nameplate the Warner Swayze Company, Cleveland, Ohio, USA. The large graduated circles on the mounting are used for pointing the telescope via celestial coordinates. And when I first visited, it was only a daytime visit, but I carried with me the right numbers for the coordinates of the planet Venus. Not everybody realizes it, but you can see Venus in the daytime sky if it's a good, clear day. Cherry Rafferty, Rice's granddaughter, was still living when I first visited in the mid-80s. She and her husband Barney were such gracious hosts, but I made quite an impression on her. She loved the telescope, but she entrusted me to open it and exercise it, and since I had the coordinates with me, I pointed the telescope at Venus in the daytime sky, and we all got to look at it. I think by doing that, I scored points with Cherry and earned her confidence. It was a lot of fun. The eye end of the telescope has special features. Let's take a closer look. The eyepiece focusing mechanisms are removable via beautifully machined large bayonet mountings. When those attachments come off, it allows replacing them with things like this. This is a camera for glass photographic plates, turning the telescope into a gigantic telephoto lens. Here's the plate camera mounted on the telescope. The camera itself was built by the William Gertner Company in Chicago that made many scientific accessories for observatories, including even for places like Mount Wilson Observatory in California and the famous astronomer George Ellery Hale. When the camera is attached to the telescope, it has to be focused too. And there's this ring that is attached via 4 brass rods. The rods and the ring here have been extended back behind the instrument to allow the camera to be close to focus. In order to make this motion, you insert a crank on the side of the telescope and you turn it, and then this mechanism moves finely and beautifully and wonderfully. This is the way to build a big refracting telescope. On the same adjustable ring, you could also mount this accessory in place of the camera. In this case, it's a combination spectroscope spectrograph. In other words, a device for taking starlight or sunlight and spreading it out into its component colors, and in principle then, analyzing its temperature and its chemistry by the pattern of colored light produced by this spectrograph. For low dispersion work, the instrument used a prism. For higher dispersion work, in other words, the rainbow-like spectrum would be more magnified. Well, for that type of thing, this had an interchangeable diffraction grating that had been created in the laboratory of Johns Hopkins University. A wonderful specialized attachment for the telescope. Here's the front end of the instrument, looking a little curious because I have removed the main lens, 10.5 inches in diameter, to clean it. Here it is, safely handled and set down on an observing bench. It was made by C.A. Robert Lundeen, a famous lens maker who had begun his career working for the Elvin Clark and Sons lens making company in Massachusetts. 5 times the Elvin Clark and Sons firm had made the largest lens type telescope or refracting telescope in the world. But by the time this 10.5 inch was made, Lundeen was working on his own in Watertown, Massachusetts. Here, with the metal ring lifted up and away from the glass, you can see that there are actually two glass parts that work together to make a telescope like this. And folks like me are fascinated with all the technicalities, but for now, let's just say I treated the lens very carefully as I inspected it and appropriately cleaned it and then reassembled it back on the instrument. Shortly after the Rice telescope was completed, Robert Lundin went to work directly for the Warner and Swasey company himself. So he moved from Massachusetts to Ohio. And here's a publicity shot showing Lundin in a large optical laboratory doing a test of some large telescope optic. But remember Yerkes Observatory? This picture shows the same man, Robert Lundin, here on the left, as hardly more than a teenager, because he and his father were among the principal opticians at the Elvin Clark and Sons Company. And what are they working on here, there, in the chain hoist, that big circular thing? That is the metal lens cell holding the two pieces of glass for the mighty Yerkes telescope for University of Chicago, a picture of which we shared earlier. So interesting, the connections between all these things. So you now know a fair bit about the Rice Observatory and the wonderful telescope there at Fisher's Island. But there's a little bit more I'd like to share with you before we're done. What happened to Elihu Thomson in his retirement? Well, there's his nice house in Swampscott, Massachusetts. It's now the town hall. But look, just to the right of the house, there's a curious light polygonal structure, not quite an observatory dome, but that's an observatory. Elihu enjoyed astronomy too and also had a backyard observatory. It seems that the telescope both men had experienced back at Central High School inspired them each to try to enjoy astronomy in the retirement, because here we see Elihu with his 10-inch instrument there in Swampscott. Elihu Thomson, in fact, was so interested in telescope technology that he personally ground and polished the lenses to his 10-inch telescope, a fairly monumental undertaking, especially given all his other interests in life. But he was very seriously interested in telescope technology. And it turns out even Thomas Edison had an observatory telescope. In his case, a small one by the Fouth Company. I couldn't find a photo of it, and I don't know if it survives. But this letter with a handwritten note by Edison testifies to his interest and to the fact that he was even interested in astronomical spectroscopy, getting the Queen Company to properly fit a spectroscope to his telescope made by Fouth. But of all these pioneering electrical engineers, I'd have to say it was Thomson who took the cake in terms of the intensity of his interest in telescopes. And that was in part because he ground and polished his own large lens. His effort was reported in this article in the Amateur Astronomer Department of Scientific American magazine. His home and observatory are again shown on the lower right. It was only just recently called to my attention that Rice and Ambrose Swasey, the surviving partner of Warner and Swasey, had actually been close friends for a long time. Swasey sent Rice this photograph of himself at his 85th birthday, December 19th, 1931. Swasey wrote to Rice, Your kind letter, written on the occasion of my 85th birthday, is appreciated more than I can tell you. Such sweet friendship as has so long existed between us means more than ever to me as the years roll on. Most sincerely yours, Ambrose Swayze. So Thomson considered himself an amateur telescope maker. Would you believe that starting in 1926, there has run almost every summer a convention of amateur telescope makers that to this day draws about 1,000 people for a long weekend campout. It's called Stellafane, and it occurs at an observatory near Springfield, Vermont, every summer. And it was at Stellafane in the 1970s that I first met Jeff Chester, a fellow I bet a lot of people listening know, because he grew up there on Fisher's Island. And what was he doing at Stellafane in the 70s? He gave a talk about Rice Observatory. And it was also Jeff who kindly called my attention to that photograph of Swayze and the letter from Swayze to Rice that I just shared. For years now, Jeff has been Public Information Officer of the United States Naval Observatory. But the experiences of his youthful summers using the Rice telescope there at Fisher's have never been forgotten. He sent me this image out of his observing logbook, and here's the explanation. He wrote, I was looking through some of my old observing logbooks and came across this sketch of Jupiter made with a telescope back in 1976. I remember that night quite vividly. There were details that I tried to copy, but they were well beyond my skills. I remember thinking, quote, this stuff I'm seeing can't be real. And I believed that until the first images came down from Voyager 1. This real photograph shows a bit more like what Jeff was seeing in 76. The wonderful thing is that he recorded this picture himself from his own observatory in 2015. He calls his place Shoe Spring Observatory. And because of the wonders of modern electronic technology, it's possible for backyard observatories today to record images of planets, well, like this. Jeff's backyard imaging of the planets and other targets has really become quite famous, and I was already intending to show some of it to you even before he fortunately contacted me with that nostalgic sketch out of his old observing logbook. But check out this photograph recorded by him of the planet Mars in October 2020. Isn't it wonderful? Another fellow who's been influenced by Rice Observatory is Dr. Harry C. Ferguson of the Hubble Space Telescope Science Institute. Harry attended graduate school at Johns Hopkins, where the Rice spectrograph grading was made. But what impressed me was that I, as a kid in high school, visited Harry's school, St. Paul's, and I saw in a display case a glass plate photograph that had been recently exposed by him showing galaxies at the Fisher's Island Observatory. How could I help but become so curious about the observatory? And as it turned out, my curiosity about the place really did benefit me, because it turned out that the telescope I have been showing you through this presentation was not actually Rice's first telescope there at Fisher's Island. His first telescope was also made by Robert Lundeen, but it was not a Warner and Swayze mounting. it was a little bit more rickety a mounting. Rice soon upgraded it with the Warner and Swayze we've spoken so much about. The original telescope, which only had an 8 3/4 inch lens, was given away to a school, but it was never housed, reassembled, and remounted. I found out about it, and they gave it to me. As a young man, I guess I had something to prove. I built this observatory all by myself. I cut all the wood. I made the windows, made the door, made the dormers. It was all to house the original Rice telescope. I did this in the early 1980s. The dome was a farm silo roof, 14 feet in diameter, and I modified it into a rotating observatory dome. Let's take a look inside. There it is. I called it Bog Sucker Observatory, and that's the original Rice telescope. I painted it red. I lovingly refurbished the telescope. I lacquered the steel engraved circles. I painted it red, like a kid restoring an old car to become a hot rod. But it was me and this telescope. And the telescope was a little rickety compared to a magnificent Warner and Swayze. Mr. Rice was justified in the telescope upgrade, but goodness, this telescope was plenty good enough for me as a young man, and it served me well for many years, and I had great fun with it. But I eventually moved west to observatory adventures that I could only have far away from my home. And here's my observatory now down there in the lower left with a beautiful recent comet in the morning sky above it. Friends visit who are expert in astrophotography because I have a dark sky sight and they can record panoramas like this of the Milky Way overhead. How wonderful. Just a bit of magnification reveals details like this within the star clouds of the Milky Way. And here's a shot that I recorded myself, but was processed by a friend, showing a little nebula, gas cloud called the Crescent Nebula, exuded by a curious star. How wonderful. The Milky Way is full of a diversity of star clusters like these that can be seen beautifully in binoculars, even from sites that aren't as dark as New Mexico. There are so many star clusters in the sky that it's not at all impossible to get two of them in one field of view, like some of these shots I'm showing you. And here's the object, same object, magnified just a little bit more to accentuate the beautiful colors that are different between stars, representing their effective surface temperature. But if we look beyond the stars of the Milky Way, there are other curiosities. Look, for example, at the object in the right center of this field of view. And this is a wide field of view similar to what one has standing outdoors, naked eye. The object there is the Andromeda Galaxy. And we now know with really great confidence that the Andromeda Galaxy is so far away, it takes the light to get here 2.4 million years. Nevertheless, that galaxy, of course, a huge cluster of stars in its own right, it's so bright that we can see it without even binoculars pretty easily from a reasonably dark sky, even still in a lot of places in New England. By the way, in the lower left corner of the picture is the same double star cluster that we were looking at before, the slide before, with a little more magnification. As our Milky Way is full of star clusters waiting to be seen with binoculars, our sky is also just full and littered with distant galaxies, each galaxy with billions of stars of its own. Zooming in just a little bit to show these galaxies better, there you are, they're in the constellation of Leo. And interestingly, the diameter of the telescope at my observatory to record this picture is only 8 inches. In other words, a fair bit smaller than Rice's there at Fisher's Island. But the technology we have today to record these pictures is nothing short of phenomenal. Here's another picture I recorded. I guess at first glance, it looks like another star cluster. It's really not quite so beautiful, is it, compared to the others? But it's nice enough. But nowadays, with the help of a computer and wonderful programming that's out there for us to use, with the press of one button, everything in an astronomical photograph can be automatically identified. And that's what's been commanded here with that same field of view. All these identifications, some are in red, some are in blue. There are so many of them, you can't even read them all. Let's zoom in. There they are. But my point is, in all these objects, they're not stars. Every object identified here is another galaxy. This is a galaxy cluster I've photographed here. The cluster's so far away, the individual galaxies don't look like that much, but they are galaxies, each one with billions of stars. So it's humbling becoming familiar with these things. One does learn some humility engaging with nature like this. And the interesting thing is that topics like the distribution of the very most distant galaxies, that's the type of thing that Dr. Harry Ferguson studies at Hubble Space Telescope Science Institute. He who spent youthful days right at Rice Observatory. It's such a coincidence, isn't it? That his name is so similar to that of your museum. Okay, well, thank you very much for your attention. And I hope you get some sense of how it is that a good number of people absolutely adore magnificent sculpted object of art instrumentation like the Rice telescope. Thanks again, folks. This is a postscript comment, folks. Something else I learned preparing this presentation, there was someone else who happened to be a graduate of Philadelphia's Central High School, none other than Charles T. Yerkes, the man responsible for the creation of Yerkes Observatory. Yerkes is remembered mainly for being a controversial businessman. And what I now believe would have been an earnest personal boyhood interest in astronomy, dating back to his experiences at Central High School, that has not generally been recognized by people looking back on the history of creation of Yerkes. He went on to do a lot of things besides astronomy. through his career. But in the end, he created that mighty observatory. In fact, where my wife and I both worked for quite a number of years. But Yerkes Observatory had a much more significant role than my own interaction with it, of course. It was a very special place. So it says a lot about what Central High School was.
Okay.
Thank you very much for your attention, folks.
Yeah, thank you, John. That was really interesting. Yeah, so did I hear right that you were just given that telescope?
Yeah, but believe it or not, it was in storage, kind of in the dirt floor basement of what was it? The Berkshire School in Sheffield, Massachusetts. And I somehow tracked it down, having just kept my ears open growing up in Massachusetts about curious telescopes floating around. I mean, it was a lot of fun. And somehow I heard about the telescope and finally made the connection that it had a relationship to Fisher's Island. And so apparently what happened was when Rice decided to upgrade to the Warner and Swayze mounting, he gave the earlier telescope away. I think it might have been to Rensselaer Polytechnic Institute, but frankly, I'd have to check my notes on just what college it was. In any case, the college that received it never used it, and then they eventually transferred it to this private school in Western Massachusetts. But again, they never set it up because it's a lot of work setting these things up. But I found out about it. But the school had, it's kind of funny. They did manage to get a Celestron 14 set up on campus. But the astronomy teacher there, who was very enthusiastic, he was also chairman of the science department at the Berkshire School. And he had donated the observatory to the school because he wanted to have it as a resource to teach with. But the frustrating thing to this teacher was he didn't really know how to use the telescope very well, and he wanted to use the setting circles in the Celestron 14, and it needed a better polar alignment. So when I approached him expressing interest in the instrument that I discovered in storage, he said, "Gee, John, you know, I donated the C14 and the observatory to the school. I can convince the school to give you that telescope because we're never going to do anything with it. But if only, would you do me a favor? Give us a polar alignment job on the C14, and it's a done deal." I said very quickly, "Yeah, I'm happy to do it." And of course, I had to become more competent in the process because I was young, doing a polar alignment job. But I think I did a good enough job that the setting circles began to work for the guy. But it's just funny how these things turn out. The world, I've discovered, is full of orphan telescopes, and I have too many of them collecting dust right now. But
okay, well, that's interesting. Okay, we have a question on chat from Bob, and he wants to know, how is the Rice dome rotated? Is it hand power or motor? And how is the slit open and closed?
The slit was opened manually with a hanging loop of rope on a big wheel that had appropriate texture inside the groove of the wheel. So the slit was manual. The rotation of the whole dome, however, was electrified, beautifully engineered, as you can well imagine. When Rice was the honorary chairman of General Electric, he could arrange to have motors rotating his dome, no problem at all. So that's the way it was. And a lot of the domes of that era were manual in the shutter. but electric on the rotation. That was commonly the way they were.
Okay.
Can I add to that? I'm nearly 100% sure that we saw that motor in an early slide that you showed in your movie, and my guess is an old DC motor like what I've seen on Yerkes. Is that right, John?
The I think actually everything out at Fisher's Island, I think happened to be AC. But to be honest, I can't swear to it because there could have been a DC rectifier somewhere behind somewhere hidden in the Rice Observatory, but I have a feeling by the 30s, electricity was modern enough at Fisher's Island compared to 1897. Things were DC at the time of the dedication of Yerkes, and to this day, as far as I'm quite certain, they continue to use DC current for some of the motors in the Yerkes Dome and in the slewing mechanism, but they no longer have a DC power plant on the ground. Of course, they have a DC rectifier under the elevating floor of the 40-inch refractor.
Yes, that's right.
Okay. Any other questions or comments?
John, that presentation seemed like it was focused at the public audience. Is that correct?
Yes, and I tried to apologize for that for you all in my introduction because, I mean, talking about the beauty of the sky to you all, it's really preaching to the choir, but it was very much a public audience at the museum out on Fisher's Island. And so I spent quite a bit of time trying to explain to them astronomy in general and how it motivates people to enjoy it, and of course the instrumentation related to it. But I thought it was easy for me to share the presentation as I had it in the can without editing it further. And I figured some of you would get a kick out of how I tried to cover a lot of bases in a presentation like that. It's nice how even something as arcane as history of telescopes can be used to engage the general public if you present it, I think, in the right way, celebrating the instruments themselves as works of art, which of course is so easy to do with like Warner and Swayze equipment.
Yeah, you did a great job, and I thoroughly enjoyed it. But I really just wanted to know, is that still a thing that people can go to the museum and see that presentation?
The museum, actually, they recorded it and have it online, but their website, it's buried so deeply in their website now, it's not something that's terribly Googleable, but yet it is out there and anybody can hear the presentation. But I'm very happy that you folks at the LTAS generally record things and put them online, because of course I'm always very happy when a presentation like that is seen by anybody interested. And of course, and I have it pre-recorded, and I've learned that, you know, when I make a PowerPoint nowadays, I always now make them recording my voice. I can edit myself picture by picture and not go on and on talking like I'm doing right now, which inevitably I will do because I like to hear myself speak, I guess. But if anybody's interested in a copy of that presentation, I can send it to you the same way I sent it to Howard last night. You're all welcome to it.
Okay. All right. Thank you again, John.
Entirely my pleasure, folks. Thank you for the privilege.
Thank you for being able to give this presentation to fill what would have been a really big hole in our agenda.
Well, no sweat.
Okay, so we have come now to the ultimate presentation. of this year's workshop. Yes, so Dan Gray, our benefactor and friend, is going to give his presentation. Would you like me to bring up your? Sure. I'll bring up. Okay, let's see. That's it. Yeah. Okay. This one or this one?
The top one. But I want to access the bottom one later on.
Yeah, we'll just leave that open then.
I haven't tested this on Windows, so. Actually, I haven't tested it after I converted it to Windows.
Well, we'll find out here. Not open.
I'm trying to rename it. Go to the left and do it on the red part.
Here we go. There we go. Okay, and get that up out of the way. And there you go.
Okay. So I always ask Howard to put me in at the very end in case I'm not done with my presentation. And so that's why I'm last. And first of all, I want to get some. Recording in progress. So some of you might remember this face from being at these in the past. His name's Martin Scott.
Oh,
and last year I called him or I emailed him like I usually do, just to make sure he was invited, and he never answered me. And I found out that he was killed by a drunk driver just before the workshop that year. And he was just, he was such an awesome person. He was quiet. He didn't ever give a talk. We upgraded this telescope for him out in Walla Walla, Washington. And that's how I got to know him. And I miss him. Oh, yeah. Did you ever find this YouTube?
Yeah.
Oh,
Yeah, I did.
Yeah.
You only
Okay.
shared the explore window.
Really? This is all showing here. Okay, well let's try that again. This is why we need IT people. This is good. Well, we'll go back. Got it. Get rid of that. Okay, so there we go. All right.
Click speed that whatever is on the screen.
I think this is it.
So you need to get that link from YouTube. I mean, it's not that important, but it's pretty cool.
Well, is that going to be after this or in the middle of this?
Afterwards.
Okay. Okay. Why don't we do that
It's
then?
not really related. It's just.
And there we go. We'll get full screen. Oh, come on, just work.
So if you go to more at the top right, it's going to be a high floating.
Hide video panel, floating meeting controls. Oh.
Hey, are you done preparing the live stream yet?
The only way to get rid of that I can find is to turn off the live stream.
Okay.
That came up all on its own. I don't know why. The live stream seems to be working.
Okay. Okay, so I'm starting out with the largest telescope. So sidereal started in 2003 or 4, something like that. And I put one foot in front of the other. I didn't really have an idea that I would be working on professional telescopes. But one thing happened after the other. And probably the most important thing that happened, as Mel Bartels and I went on it to Shingletown not a star party. It was just a group of us. Were you there? I think you were there. Yeah.
Well, it was a star party.
Yeah. Well, it was just a few of us.
Yeah, okay.
And we saw Einstein's cross, I believe, and a lot of other things. But this is when Mel and I started talking about servo controls. And he wanted me to program these chips for him, which I did. I made a circuit board, these PIC servo chips, and we made it work. But in the process of doing that, I realized, hey, I can make a servo control. I know exactly how they do it. I already knew about PIDs because of my marine experience. And so that's what I did. And that was the beginning of sidereal technology. So kind of how things turn out, I don't know, but that's what we do. We've done, I don't know how many telescopes we've upgraded or new installations of our control system on other telescopes. I can't even tell you. I can only roughly guess 20 or 30. So this one is 5.3 meters or 206 inches, I think. A telescope that gathers light. And this is the control system. This is our Force 2 controller. And you'll see two drivers down there and then some communication devices and some power supplies and transformers and that's the control panel. This is a first light image. Now this is electromagnetic radiation. This is not visible light to us. And this is the Chang 6. I don't exactly know the story behind Chang 6. Maybe somebody does here. I don't know. Yes, it's a Chinese. Yeah, maybe. Yeah, something to do with that. I know it is. But these spikes are various frequencies. And this radio telescope is designed for astrometry on satellites that have beams of communication. It doesn't decipher them. It doesn't, it doesn't know anything about what's in it, but it can tell where the satellite is. So this is astrometry for satellites that you can do in the daytime or in the cloudy skies. And this is the telescope. And this is where I was going to show the movie, but I'm not going to do that. I don't want to stop this. I have a movie that shows the motion of that telescope that after we got it working. And this is the same one, the Chang. And I don't know, I'm not a radio telescope guy, but apparently the spread here is one thing, and then there's a little peak here and another peak here. So anyway, it's working. And they've been using it now for several months when they get the chance. So then the following one after this, I don't know how to pronounce that, but it's a relay satellite for that. And this is, I think it's really pretty. This is the spread of the beam that's being sent to Earth. And this is another one. It's a Sirius XM satellite. I think they have more than one, so I don't know which one this is. And there's another picture of it. So this is a telescope. I gave a talk on it last year, but it was before we did it. So this is like post done. And what you see on the left is the original one for the larger one. There was two radio telescopes. One's a 2.4 meter, and the one I'm talking about is a 5.3 meter. And it actually worked with the old system if you didn't really care about where it was, and if you didn't need it to track, and if you... So they have VFDs to control motors. Now you can control VFDs and make motors go sort of where you want to do, but it really should be a servo motor. So that's what we did. We took off induction motors and ripped out there was nothing in that. This is the same panel over here on the right, and there's nothing from the old one. Although I have to admit that they did a nice job. It looks nice and neat as opposed to what we did. It's not quite so neat. But ours works. Okay, why isn't it going? Okay. And that's all I'm going to talk about that telescope. This is the latest one, and this is the one reason that I didn't get my talk done in time. And it's in New York. It's right across the Hudson River from Albany, Troy. And it's Rensselaer Polytechnical Institute. And it's a Buller and Chevins. Now, I did not know that they made such a small telescope that Buller and Chivens made such a small telescope. But Alan told me that he knows of several, so Alan Slisky. So, yeah. And so I did not know that. So the fellow there helping me, his name's David Morton. And I put in my quote, I said, I need somebody to help me do, wire pulling and various things. David was such a big help. I mean, I didn't have to tell him, anything. He knew how to wire, he knew how to read a drawing, he knew how to do everything. And basically, he did a lot of the work. And it was a good thing because I did not do a pre-check on this. So I spent 3 days of my 2 weeks time there just I didn't want to rip everything out. I just wanted to, document exactly how everything was before I ripped everything out. And that took a long time. Here he is again, and I'm not sure if I'm clapping or what. Oh, the guy, that's Dr. Charles, and I can't think of his last name right now, but he's the one that's going to run this telescope. And it's right in the middle of the city. And why do you want, this came up earlier, why do you want such a telescope in the middle of the city? But it's for the students so they can learn how to operate a professional observatory. And there is some things you can do in the city. I heard on Alan Slisky's talk, that you take a lot of pictures. Well, sometimes I forget, so I don't have an after picture. This is a before picture. So if you can see my mouse, this is a stepper motor. And then that's a bigger gear reducer. And so this is smaller. So that's like a negative ratio. Then that's a positive ratio there, which turns the worm. And then there's another pretty precision anti-backlash gear right here. It's got the 2 faces and the spring loaded, which turns another gear here. And they looked to be the identical size. Well, we didn't have any good weather before I left, so we could never test anything. So I told them how to use a telescope, and Charles and David went out there, and it was off by 2 degrees. They did like a mount model with a visual, and it was off by 2 degrees and it was a declination. So then I went with them on one night. I went out there and did, remotely. And I said, well, let's ignore the scope encoder, which is, it's not this one. This is the original. So we ignored that, the new one, and then it worked perfectly, had a nice, good model. So I knew it was something to do with this, but I forgot that there's these 2 gears on there. And while I was here at this workshop, I realized one's a 100-tooth gear and the other one's a 96-tooth gear. Oh. And that's the problem. I can verify that when I get my spreadsheet that I made, but it's back at the office. So it might not be the right number of teeth that I just said, but that's what I think it is right now. Anyway, we on the right ascension and the declination. Hi, Emil. This encoder we replaced. Now, the reason we replace this is it's a at least a 26-bit absolute encoder. So that means you need 26 really fast inputs, and you have to read them and turn it into a position and turn it from gray code. I'm not going to tell you what that is, to binary. And I didn't want to deal with all that stuff because all that hardware was being pulled out, okay? And so I found another, I didn't want to go backwards and not have absolute encoder, so I found another encoder, and it's about the same size, slightly smaller, and it's more accurate, and it has more resolution, which we don't really need, and it's got a protocol, a serial protocol called SSI. And so now we didn't move backwards, we made it better, and here it is. This is the new encoder right here. And this is the new motor. This is okay, I don't have okay. I thought I had the data sheet. It's a Hudson, I can't think of the other brand, but it's called a Hudson motor. It's a brushless motor. And that's why we used our Force 1 controller. This is the old control cabinet. And I have another picture later on, and you'll see that not much is left. I'll show you a few things. this right here is all the digital inputs go into this device right here, which has a USB to the computer. It was a Windows 7 computer, and you know you can't even put that on the internet at these colleges or universities because they're hackable, right? And let's see, so these are the digital inputs, and then this right here you can barely see. If I can, whoops, I don't know if I can zoom in. Oh yeah. So these are all the inputs that go to a PCI card in an old PC, and you can't even get them anymore. So that's two reasons they wanted to upgrade this. And let's see what's next. So this is how it ended up. We don't have the cap on here, so it looks worse than it is. But this is our Force 1 controller, and all the wires from the encoders and the motors come in here. We got a bunch of relays. This is two photographs that I kind of married together sloppily. And therefore, these are for the hand pad or hand controller up at the telescope. These are for various things like emergency stop. And then here's some circuit breakers. And this is the only thing we reuse is these two power supplies. This one here is a bigger one, and it's a 24-volt supply, and it's for the stepper motor for the secondary mirror focuser. And I didn't find this out until we got there. This is a stepper driver, and it takes step and direction input, which came from that PCI card that's no longer going to be there. So now their focuser's not going to work. But SciTech has a step and direction controller that acts just like one of our servo controllers, but it puts out steps and direction pulses, and it does both axes. But you can see this ribbon cable here is hanging there because we're not using that axis. We're just using this one. And if you followed out these wires, they would go over to this thing and give it a step and a direction, and it works. So that's how they focus now. So that's all good. I alluded to this earlier about going into, like I was talking to the Granger people, and I found a replacement for this, but it was different mechanically. So if you see this picture, this is an electric winch that you might put on your pickup, or I guess it's, yeah, let's see. No, it's 120 volts. And then you can barely see the cable going over here and then going over to a manual winch. Whoops. And so then these buttons control that. And that puts the shutter down so the telescope can go low to the horizon. The other shutter is more conventional and just goes up the dome. That's the front panel of the shutter control box. And that's the inside of it. And we cleaned it up. It was a lot worse, and I don't have a picture of the before. But what you can see here is we put in this power supply. We put in this as our dome controller board. And this is another power supply. And there's two pairs of relays. And our dome control board, you don't want to open the upper shutter and close the upper shutter at the same time. So you never have to turn these two relays on. I have another slide that describes that. The same thing for these two here, control what's going, the lower shutter opening and closing. So we have, and that's controlled by, well, I'm going to show you that a little later. So now that panel moved with the dome as it turned. So there's communication in there, but it has to be wireless because you can't have a cord dangling. This is the one that's stationary, and this is what turns the dome. And look, there's 6 buttons, and you'd think you would only need 2, left and right, or clockwise and counterclockwise. Oh, so I got an email from David, the guy that you saw in the picture today, and Taj, that works in our office, printed a plug for this because this is no longer used. And there it is. And this e-stop stops the telescope too. So it's right there. You can stop the telescope. And then these buttons control the upper shutter, open and close. And these do the lower shutter, which they call up and down. And then this is a forward and reverse of the dome itself to move it manually. This was the before picture. I do have a picture of that. So this is where the plug goes. I reused all these switches, and we took almost everything out of here. We used a lot of the terminal blocks. Let's see what it looks like now. Okay, this is what it looks like now. So if you go back up, this is the VFD. We reuse that. Now VFD, Emil knows what a VFD is. He works here at TMS. And
What
this
does VFD stand for?
I was going to say, okay, thanks, Emil. And I know Alan knows what that is too.
It's just a way of varying the power of an AC, motor.
Okay, so Emil says it's just to vary the power to a AC motor. And this one's a three-phase, it's single-phase input and three-phase output. It's a three-phase motor that turns the dome. And we did clean that up some, it looks better. And again, here's our dome control board. And then this is a Raspberry Pi that communicates to the main computer. And this is a kind of a close-up of that. And I wanted to show you these chips right here. Those chips are the same chips that are in one version of our Server 1 controller. They're an H bridge, which means the output of that is either plus and minus, or minus and plus, or just off. And then this is an older version of that, this was done for the Mars Observatory, and they used the same things. These are actuators that open up the mirror covers and close them. So we did that. And then if you look at this, so these also have freewheeling diodes on them, but for clarity, I erased them. So if you look right here, let's say this one is plus and that one's minus. So that means we have plus going through this relay, and it'll go through this diode. And so this relay energizes. So this is the counterclockwise motion. And then if this one here is plus, then it's going to go through this relay and through there and to the other way. And then now we have clockwise motion. And there's the same thing for the shutters going up, open and closed and all that. So it's exactly the same circuit board we use for that. So here's some of the software. And this was a lot of parameters for this. The first one is that behind the preparing live stream, it says tele, and it means it stands for telescope. So you have to give the IP address of the computer that's running our software that controls the telescope motion, right? So it has to know where the telescope is, so we can know where to position the dome. And then that's it. That's the IP address. Where's the mouse? Oh, mouse is kind of invisible. I can't see the mouse anymore. Whoops. I can't see the mouse. Oh, there. Well, I can only see the mouse if it's on there. Okay, so I can't show you guys out there what I'm pointing to. Okay, so how do you put the shutter in front of the telescope? It's not as simple as you would think, because you would think, hey, if I'm at this azimuth, I'll just put the dome azimuth there. But we have to do a little work to get to that point. And I'm not a mathematician. I had a lot of help, but I did it, and it works really great. So first of all, we have to think of a sphere, a big sphere in your mind, and then there's a center to the sphere, okay? And we need to know where you mentioned, was it you? Somebody mentioned that you need to, I think maybe, was it John? We needed to know where the axis of where the right ascension and declination, was it you? Okay, yeah. And we need to know exactly where that point is in relation to the center of the sphere. If you had the dome and you kept that dome going around, okay? So we need to know that. And so if you go back to this, you can see these parameters that I can't show you, but where it says dome slaving dimensions. Oh, before I go into that, there's a hysteresis. You can make it so that it doesn't oscillate. And then we need to know the encoder ticks per rev for a full revolution, which, by the way, I put an absolute encoder. I took off the incremental and put on an absolute encoder with the SSI on that, so they don't ever have to home it anymore. But they still need a home position, so they can click a button and make it go home. And then these two on the right is called deceleration time. We need to know that too, so that we know exactly when to turn off the relay, so it will coast and be right where it's supposed to be. And that works extremely well, just a little ramping trapezoid math. Okay, so now we're going to go on to the dome slaving dimension. So we have dome center to mount pivot. So that's where the joining of the, I'm going to call it primary and secondary. That way it works for an alt-az and everything. So where the primary axis and the secondary axis intersect. So we need to know how far it is in north and south and how far it is in east and west. And so here we are. That find the intersection of the primary axis and the secondary axis. Dome center to mount pivot north plus. And then east is plus for east and west. And then we need to know where the mount center or the mount that center point, the junction between the primary and secondary axis, where it is in relation to the center of the dome in the z-axis or elevation. And then of course the telescope isn't right on that axis. That only works if it's a fork mount, but since it's off to the side, we have to know that distance. And then if we go back here, we measured all those, and the mount pivot was, as far as we could tell, was right in the center, and the center to the mount pivot height was 5 inches. And then we measured the dome radius, and we measured all that stuff as best we could. Okay, and then here I have it in the dome follow scope motion or mode because of that screen. The dome follow scope is green. And now whenever you move the telescope, it doesn't just start following where the telescope is as it's flying. It knows the destination of the telescope because you told it to go to some right ascension and declination. And so it moves the dome there. So it takes it, you don't have to like go and then find a set point as it's moving. It goes right there. And not only that, but you can control the telescope from here. You can put in coordinates and have the telescope go to coordinates or go to alt-az coordinates. And you can do J now or J2000. And this is a shutter control. It's got a bunch of like just indicators for the limit switches over on the right. And you can close the upper shutter or open the outer shutter or halt. Same with the lower shutter, but it won't open the lower shutter if the upper shutter is closed. And it won't close the upper shutter if the lower shutter is not closed. And then you can sequence them there. And then these are some more settings over here where it says shutter config. You can enter the shutter cycle time. And then without feedback, we can make these little, where it says shutter motion, sort of on the right above all those little shutter switches. Those things are little bar graphs, so you can kind of see it move as it's opening or closing. And then we can close on bad weather. We did install a weather station, and it's not working because of their network, but it will close automatically if it's cloudy and stuff like that. And this is me on the weather station. This is this was the last day. Weather station didn't work, and I said, let's check the plug. So I had somebody get a ladder up there for me, and I checked the plug. But Samantha was in the car waiting for me because we were supposed to go to the airport. And she had been waiting for an hour or more, and she decided to get out of the car. She saw me up on the ladder and took a picture. So that's why that exists. Okay, so that's really the end of my talk, but I wanted to show you the movie of that motion. So could you help me and run that movie?
We'll stop this share and get that movie out.
Let's do the telescope movie first, which is in that same direction.
Oh, there's more than one?
Well, that one from it's in the same folder.
Okay.
I knew my talk wasn't going to take so long. Everybody's probably pretty happy.
Where'd it go?
I think it's down there, right?
Here it is.
Do you have to share the screen first?
Yeah. Okay, so this one, altitude motion?
Yes. You probably have to pause it so then you can share.
Yeah.
Okay, pause it. Share.
Come on, Zoom. Oh, come on.
Put the eggs in the slideshow.
Where is Zoom? Here we go. Zoom. Share screen.
Okay.
There we go. That's up there. Display.
Okay, so this is one that we kind of, oh, you can hear my footsteps. Okay, look at that motor. That's the new motor that's the servo motor. And then there's a gear reducer after it. I think it's a 7-to-1. And we increased the speed of the prior one because they used like a 20-to-1. And you can see it's moving down. This is Craig. He's the one that sent me those. He's a radio guy. He's the one that sent me those screenshots. So that's how fast it moves. It's going down right now. Okay, I think it's about over. You can close it if you want.
Yep,
Yeah.
here we go.
Okay. And now, I don't know, that email that I sent you.
Okay, let's go there.
That's it. I don't think it's a long one, but you should probably pause it and then share the screen, right?
15.
It's all in the infomercial. Sorry, everybody.
All right, so we're going to pause that. Now we're going to get back to screen share. And which one is it?
Shares. 3-axis rotation right there.
Yeah. Okay. I'll go full screen.
So this is Tracy. What's his last name?
Day one's gonna go down.
What's Tracy's last name?
45 degrees.
Wilson.
Tracy Wilson. And this is a nice movie because it stays in one place, but you can see it both axes turning. So all 3 axes are moving and the telescope is pointing at the same place.
The problem.
Isn't that cool?
I'm gonna put a tray there, so I can put my computer on the tray and I don't have to worry about wires at all. Tray is right around this telescope. You think of this as pointing at 45 degrees latitude at the pole.
It's really cool.
That needs 64 ounces of weight in the bottom. So there's a lot of stress going on in here. Otherwise it'd be moving a little smoother. I ordered a disc. It's on its way to be here in a few days. Our axis also needs to be upgraded so it's a little faster. It's 50% slower than the other 2 axes. It's ended with its rotation and it's going to go back home. And that's it.
Cool.
Okay. Oh, well, you see the engineering of the pyramids. Oh, come on.
Welcome
The history
to History for Granite.
I highly
Join me to
recommend this,
explore
by the
ancient
way.
Egypt. Please
This-
subscribe.
This guy is really good. If you're into the pyramids of Giza, he's your guy. No. So, okay, I can get rid of that now. We'll go back to Zoom. Zoom. Okay, so is there any final comments you want to make?
Our next, yeah, is there anything in the chat? Oh, there's 6 in the chat.
Oh my goodness. Okay, let's get this pinned. Pin chat. Okay. We are not seeing anything in Zoom land. Started working. Okay, she's got it. Okay, cool rotation. Beautiful garden.
Yeah.
Okay.
It is a really beautiful garden. He and his wife do that. Yeah, he told me.
Yeah, okay, so that's it. All right.
Okay.
Okay, so any final words?
Any questions?
I have a question for the two guys who talked about these Warner and Swayze scopes, these maps. They came in different sizes, and they have features like those locking. Did they have a common set of plans and templates and stuff they worked from, or did they do these things like one-off each time?
They were different model numbers.
Mhm.
So the 12-inch one is a Model 5 mount, but the length of the tube the lenses tended to be unique. So they would adjust the length of the tube, but the number of the mount accommodated a certain range of objective sizes. And then, but there were only about 50 of them all together. And they do seem to be a little different, each one. So they were evolving the design.
So they would modify it when they found things they'd sort of screwed up in the design, they'd fix it.
Yep.
And hopefully change the drawings and go back, and the next one will be better.
Exactly. So they had this like the document control they had. So they knew how to keep track of drawings and make things. And most of them were the same, but the one I'm restoring now, that very complicated concentric gear is actually split into 2 pieces, and it's like immensely complicated. The other one I worked on, and it has to be split to get on the shaft. You can't put it on afterwards. The other one I worked on, they were able to rearrange it so that it went on went over the shaft, so they didn't have to split it first. So the machinist must have complained.
Yeah, I was gonna say, somebody came back and said to the guy at the dress.
Yep, you out of your mind.
You're not doing that again ever.
I can, if you hear me, I can add a little bit to what Alan said, and of course, everything he said was consistent with what I've seen. It's interesting, though, that the real early models, like their first telescope was 1880, and then they started selling them, manufacturing them for schools like Durfee High School in Fall River was circa 1886. And then they had a small equatorial, sort of a 6-inch class, and they sent one of those out to Lick Observatory for the dedication of Lick, and that was only in 1888. And so it's interesting to compare the earliest ones from the 1880s to how they kind of normalized the design pretty well by the time they built the one that Alan has been working on, and also the beautiful one that he owns. And so the designs became a little bit more stable by the early 20th century. But like Al says, it's interesting. You see little changes from one to another. For example, I had never noticed on any of the ones that I've worked on that they had split gears, like Alan described for us today, up in that mechanism. And probably some of the other ones do, but I just had not noticed that. But others I've worked on, you have to take the whole thing apart before you can take those gears apart. So, but they're very interesting. One other thing I can mention, out at Fisher's Island, they actually had a big drawing package out there. They also had a drawing package at Wesleyan University where they've got a 20-inch Warner and Swayze. And but what you found in the drawing package out at Fisher's Island, there were a lot of drawings sent to Fisher's Island from like the 18.5-inch model that was at Northwestern University. They just sent them the same drawings to give sort of like a conceptual impression of what was going on, even when they sold the one to Rice in the 1930s. So in some ways, there wasn't that. Things were not perfectly standardized even by the 1930s, and the designs were evolving. But I just always say the Warner and Swayze telescopes, man, they were like Rolls Royce quality. Wouldn't you agree, Al?
Absolutely. So
Yeah.
what I have, there's 3 sets of gears, bevel gears that connect the polar axis to the base. One of them is for the clock drive, and the other one is for there's like a ship's wheel on the pier. You turn the ship's wheel, and there's a shaft and bevel gears go up through, and that slews the telescope. And then there's another shaft that comes down with another set of bevel gears, and that runs the pointer in the RA clock indicator. And on the drawing, it says the exact angle of these bevel gears is unique to each latitude. And the angle shown on the drawing, we forget what at latitude they're for.
Oh. Okay. Good luck.
But they're masters of cutting gears.
Incredible stuff.
Yeah. Any other questions or comments out there from you Zoomies? No? Anyone here?
I would like to say that 2 years ago, we upgraded a Bolin Shivens for MIT Lincoln Labs near Socorro. And they had 2 telescopes. And it was a rack of electronics for each one, a big rack full of electronics. And it broke. And there's nobody that could fix it. And so we got a contract to upgrade that one, which we did 2 years ago. And then we got the contract to upgrade the other one, but it still worked. And so we built all the electronics. We got it in our shop in Estacada. And then I sent them an email. I said, we're all ready to come out there. And they said, this is like 1.5 years ago, at least. And they said, oh, no, we can't do it now. We have to get our software controlling your hardware before we can take this other one out of service. And so then everything just sat for 1.5 years. And now I've worked with them a lot, getting the interface right and everything. And now they say we can do it. So we're planning to do that in October. So that's our next project.
Hurry up and wait, government stuff.
Exactly.
Yep.
Okay.
Well, I guess we're done.
Okay, well, that is just about a wrap. Of a few closing comments. Last year at this point, we ended up in a fairly lengthy discussion about how we wanted to take the AltAs workshop into the future. And this year's agenda is a direct result of that discussion that started and the work that Mel and I put into getting the speakers together for this year. I'm really pleased with the way it turned out, and I hope everyone else is too. If you have comments about that you'd like to share now, that's great. If you want to send me an email for things you don't want to share right now, that's great too, because we are looking to continue to make this a more useful, more interesting, and to a broader audience of people. So I think we've taken a good step in that direction. And Rob has something to say.
Well, I'll just say that This is probably the highest dynamic range conference I've ever been to. We had everything from a little cardboard finder or a lens cut with a flat on it to speckle interferometry. You know, it was like
Spherical trigonometry too.
spherical trigonometry. Thank you.
Yeah.
Yeah, that's right. That too. So a lot of variety, and that made it interesting. Yeah.
Okay, good. I'm taking that as a positive comment.
Absolutely.
Okay.
Yep.
Very good. Okay. Anyone else here would like to make a comment? Put you on camera. Okay. All right. Well, maybe that's it. Unless there's there's a chat.
I'll make a comment on Zoom. As one of the participants, I was very, very pleased to be able to deliver my talk on basically all the little stuff that got me into ATMing. And I was very pleased to see you guys listening intently. So I just want to thank you for the invitation and for the response I got. And I enjoyed the rest of the talks too. I really felt like this was a great year. I enjoyed it a lot.
All right, excellent. That's great. That's good to hear. And I personally, I put a lot of time into this. And at this point, I'm really tired. Even though I've enjoyed everyone's presentation. So it's nice to hear stuff like that. And Pierre sent a little message. Thank you. Great workshop. Enjoyed all the presentations. So, all right. I think we're probably on the right track. Hopefully this will continue to improve next year and years beyond. And I hope some of you who have been on Zoom the whole time can actually come here to Portland to attend in person at some point. That would be great. I mean, Alan has come all the way from Boston. He wins the furthest travel this year, and we should have a prize for that.
Yeah.
We had a guy come from Germany a couple years ago. Yeah, so we should have a prize for that. Some cheap little trinket.
Barbecue.
Yeah, well, yeah, there you go. And the barbecue is good. It's worth coming just for the barbecue. And speaking of the barbecue, I have been the barbecuer since the very first workshop, which was really, I think, 19 years ago. Even though this is the 17th version. In a couple of years we didn't do it. But anyway, so I've been the barbecuer. So I was chief cook and bottle washer and moderator and organizer. And this year I decided I just didn't want to barbecue anymore. So for people who do come in person, just putting this out there, if you volunteer to barbecue, you do not have to pay. So, and that saves you $5 per meal. So the more you barbecue, the more you save. How can you beat that deal? So anyway, so I'm gonna wrap it up there. And thanks for all. Oh, one more thing. Yesterday we hit a new high for attendance. Not here in person, but in total. We had 15 people here in person. We had 15 people on Zoom, and we had at least 20 people watching the YouTube live stream, and perhaps more. So that puts us around 50 people, which is, I think, probably close to double what we've had as a maximum in the past. So I'm taking that as a positive signal as well. So until next year, we'll clear skies. Yeah, I like that. Clear skies. Happy telescope making. Happy sketching. Happy spherical trigonometry. And we're going to